Good morning, Namaskar, Suprabhat. How are you? I think preparation is going well. So, as you know, today we are here to revise the basic concepts of this subject, and in this session we are not going to discuss any question, but I will try to revise all the concepts related with GATE examination. So, all the important concepts we are going to discuss. We have planned this session roughly for 4 to 5 hours. It's not time limited, it depends upon your interest as well as it depends upon how much time I take to revise all the concepts. So, we'll try to cover everything. What is going to be the important parameters, or important formulas, or important concepts, everything is going to be discussed here, right. So, let us begin with the very basic thing. As you know, the name of the subject, electronic devices. So, this is electronic devices we are going to discuss, right. The very first concept which I would like to tell you, that is a energy band gap. Energy band gap, which is also known as forbidden energy gap, right. We all know that this forbidden energy band gap is a function of temperature. Eg is function of temperature, Eg at 0 Kelvin minus beta into T. This is your relationship, right. You need not to write all these relationships. So, what I will suggest, you keep on listening to me. This video you can see later, and you can refer your notes also, and in notes you can highlight these points which I am telling you. So, take a highlighter and take the class notes and keep on highlighting whatever points I am mentioning, right. You know, this is energy band gap as temperature T Kelvin, right. So, it is energy band gap at temperature T Kelvin, right. Tk means T Kelvin. You can write it completely like this. Dear friends, this Eg naught is energy band gap at 0 Kelvin. Energy band gap at 0 Kelvin. This beta is known as material constant. It is constant for a particular material, but material to material its value will differ. And then this parameter T is nothing but temperature in Kelvin. Temperature in Kelvin. I need not to tell you, still I would like to, that is temperature in Kelvin is equal to temperature in centigrade plus 273. You should be knowing this conversion, because sometimes the temperature is given in centigrade, then you need to convert it in Kelvin. This would be the standard formula. We know room temperature. Throughout the subject we would be using room temperature concept. So, room temperature in centigrade scale it is 27 degrees centigrade, or in Kelvin scale it is 300 Kelvin. So, this is the room temperature. The values of these parameters Eg naught and beta for two important semiconductor materials, that is silicon and germanium. You should remember these values. So, if I talk about silicon and germanium, so let us first talk about silicon, because that is very important. So, for silicon, this value, for silicon the value of beta is 3.6. This value beta is 3.6 into 10 raised power minus 4, and Eg naught is 1.21 electron volt, right. This is for silicon. If you put these values and try to solve this relation, so for silicon this relation becomes Eg at any temperature T, this is 1.21 minus 3.6 into 10 raised power minus 4, 10 raised power minus 4 T. If you put T in Kelvin, this will come into electron volt. And if I put a T 300 Kelvin, then this value Eg at 300 Kelvin comes out as 1.1 electron volt. This you need to memorize. These all values you need to memorize for examination. If you recall previous year GATE examination paper, this value has been frequently asked. 2 times I think it has been asked, and in engineering services it is frequently asked at room temperature what is the value of band gap in silicon. So it is roughly around 1.1 electron volt. If I do same thing for germanium, then for germanium it becomes, for germanium, if you see for germanium, the beta value is 2.23 into 10 raised power minus 4. Beta is 2.23 into 10 to the power minus 4, and Eg naught is equal to 0.785 electron volt. So if I write this equation, then Eg at any temperature T is 0.785 minus 2.23 into 10 to the power minus 4 T. If T is in Kelvin, then this will come into electron volt. Electron volt. And if I put T is equal to 300 Kelvin, T is equal to 300 Kelvin, that is at room temperature, then Eg at 300 Kelvin is equal to roughly around, not exactly, it is equal to 718, that is roughly around 0.72 electron volt. So these all values are for germanium. You should memorize this, right? So this is all about energy band gap. If I summarize this, this is for energy band gap. I would like to advise, since still there are more than 10 days for EC examination, so you can keep on taking picture, क्योंकि दोबारा आप वीडियो नहीं देख पाओगे, इतना समय आपके पास है नहीं. So आप स्क्रीनशॉट लेते रहे, क्योंकि YouTube पर है तो स्क्रीनशॉट लेना इजी भी है. तो मैं किनारे हट जाया करूंगा, जैसे ही मैं एक स्लाइड कंप्लीट करूंगा आप स्क्रीनशॉट ले लीजिए, सारे फार्मूले आपके एक साथ हो जाएंगे, आपके लिए easy हो जाएगा. Someone is asking, sir, will mass capacitor be covered today? Yes, I will try to cover each and everything. I have been given 5 hours. So if you have patience and you will stay with me, then I will try to cover each and everything. मैं सारे टॉपिक कवर करने की कोशिश करूंगा, right? Not only mass capacitor, each and everything I will try to cover here. Right. So let's see. One more thing which I didn't discuss, that is 1 electron volt. 1 electron volt. As you know, electron volt is the unit of energy, and it is the amount of energy acquired by electron to move through 1 volt potential difference. So this can be written as 1.6 into 10 to the power minus 19 joule. 1 electron volt and joule are converted like this. One more mutual अंडरस्टैंडिंग हमारे और आपके बीच में होगी. चार्ज ऑफ इलेक्ट्रॉन या मैग्नीट्यूड ऑफ इलेक्ट्रॉन चार्ज को मैं स्मॉल q से रिप्रेजेंट करूंगा. Some of the books used to represent it by small e, but I will represent it by small q. Magnitude of electron charge. Magnitude of electron charge. I will represent it by small q. This is just magnitude. It is 1.6 into 10 to the power minus 19 coulomb. इसे आप E से भी रिप्रेजेंट कर सकते हैं. यू कैन रिप्रेजेंट इट बाय स्मॉल E एज वेल. हो सकता है एग्जाम में स्मॉल E से भी मिल जाए, बट मैं जो रिप्रेजेंट करूंगा वो स्मॉल q से रिप्रेजेंट करूंगा. थ्रू आउट अवर डिस्कशन एवरीवेयर व्हेनेवर आई एम राइटिंग स्मॉल q, इट मींस I have written 1.6 into 10 raised power minus 19. This is all about the first concept. So let us move on to the next concept. We know the classification of materials based upon energy band diagram. That's very simple thing. Materials are classified in 3 broad categories. If energy band gap is very wide, then that material is known as insulator. The energy band gap should be greater than 3 or 3.5 electron volt. It should be greater than 3 electron volt. Then it will be known as insulators. Insulators are the materials in which valence band is almost filled and conduction band is almost empty. They don't have free electrons, so these materials are basically electrically non-conducting, and that's why they are known as insulators. Some common examples of insulators are silicon dioxide, aluminum dioxide, basically Al2O3, alumina, hafnium dioxide, HFO2, etc. These all are the examples of the insulators. Diamond is also insulator, although diamond is nothing but carbon is in fourth group. You see, in fourth group silicon and germanium are also there. Silicon and germanium are semiconductors, but diamond is insulator. The reason behind this, diamond has energy band gap which is greater than 5.5 electron volt, so it is a very wide energy band gap, and because of this wide energy band gap, diamond becomes insulator. Dhyan rahe, diamond is insulator, but there is another allotrope of carbon, that is graphite. Graphite is a conductor. Graphite has sp2 hybridization. So in 3D basically, in 2D basically, 3 carbon atoms are making the coplanar bond, and the fourth electron is relatively free, and which makes van der Waals force between 2 coplanar layers. So that free electron contributes into the electricity. So graphite is basically electrical conductors. Now if I talk about conductors, so conductors are those materials which have very narrow energy, which have negligible energy band gap. Conductors do not have any energy band gap. Their valence band and conduction band overlap. So energy band gap is 0 in these materials. Basically metals are the examples of conductors. In conductors, the electrical conductivity is very high. You know, silver is the best electrical conductor, that I have told you in the class. So I am wanting to recall all these points so that we can begin today's discussion. And then if I go for semiconductors, semiconductors are those materials which have narrow energy band gap. Means the band gap is greater than 0 electron volt, but it is less than 2 electron volt basically. So the band gap is somewhere in the range of 1 electron volt. Like you have seen for germanium it is 0.72 electron volt at room temperature, and for silicon it is 1.1 electron volt. So because of narrow band gap in these materials at high temperature, electrons move from valence band to conduction band, and due to this reason valence band become partially filled and conduction band also become partially filled. In conduction band you have large number of free electrons, as well as in valence band, because of partial filling, these electrons can also move, which contribute to a particle which is known as hole. Concept of hole I have introduced in the class. So in these materials you will have two kind of charge particles, one free electron in the conduction band and another holes into the valence band. Holes are positively charged particles which move into the valence band, and electrons are negatively charged particles which move into the conduction band. And this way these materials have electrical conductivity which is greater than the insulator but less than the metals. So this is the classification of these materials. Let us move on to the next part, and next is classification of semiconductors. Briefly let us see that. So semiconductors are classified in two ways. Semiconductors, first one is intrinsic semiconductor. Intrinsic semiconductor. It is the purest form of semiconductor. It is the purest form of semiconductor. Purest form of semiconductor. It is the purest form of semiconductor. So this will also known as pure semiconductor. It is known as pure semiconductor. We know that the pure semiconductor has very small conductivity at room temperature, so it is less useful. Then we have another that is known as extrinsic semiconductor. So extrinsic semiconductor. Extrinsic semiconductors are those semiconductors in which we are adding a small amount of impurity to increase its conductivity. So since we are adding impurity, so it is impure semiconductor. It is impure. You should be knowing all these terms. It is impure semiconductor. And this impure semiconductor, we are adding some small amount of impurity, and because of that impurity, its conductivity we are changing. This process of adding impurity is known as doping, and such semiconductors are also known as doped semiconductors. These are also known as doped semiconductor. Now based upon our choice of dopant, we have two types of doped semiconductors. These are, the first one is N-type semiconductor, N-type semiconductor, and the second one is P-type semiconductor. Briefly let us revise these concepts because these concepts are sometimes utilized in the questions as well. And since I am doing this session for both GATE as well as engineering services, so I am keeping in mind all those concepts which can be used in engineering services as well, because just after the next week, on 11th you have GATE and on 17th you have engineering services. So we have to keep in mind both as well. Now, if I talk about this, so fifth group impurities are added. Fifth group impurities are added. What are fifth group impurities? The examples of fifth group impurities are phosphorus, arsenic, antimony, etc. Right? These impurities are known as donor type impurities. These are known as donor type impurities. And they give one electron. So this way you see electrons become majority charge carriers. Electrons are majority charge carriers. And holes are minority charge carriers. Electrons are majority charge carriers and holes are minority charge carriers. They are minority charge carriers. If I want to represent this material, then I will be representing it something like this. This is our semiconductor piece, and here we have donor ions. Donor are giving their electron, so after giving their electron they become positive ion. So each of these donors are having a positive charge, so this positive ion. Each of them are giving one electron, so electron is represented by solid dot. So these are the electrons, so each of them is giving one electron. There are few holes also, very less in number, but there are few holes. So here we are representing hole by this circle. This is hole, and electron by this dot. This is electron, and this is your donor ion by the positive charge. Donor ion, positive charge in circle. This is the representation of n-type semiconductor. Now if I do all these things similarly, then p-type, उसके बाद आप इसका screenshot ले लीजिएगा. So in p-type I can say कि we are adding third group impurities. Third group impurities are added. Impurities are added. Third group impurities are added. इसमें हमारे पास बोरान, एल्युमिनियम, गैलियम, इंडियम, etc. These are the examples of third group impurities. These are known as acceptor type impurities. इन्हें हम acceptor type impurity कहते हैं. Acceptor type impurities. These are known as acceptor type impurities. And these acceptor type impurities will accept an electron from the valence band, and hence in valence band one extra hole would be created. So holes are majority charge carriers. Holes are majority charge carriers. Holes are majority charge carriers, and electrons are minority charge carriers. Electrons are minority charge carriers. These are minority charge carriers. Electrons are minority charge carriers. If I talk about the representation of these materials, then we will have this. Oh, sorry, where it has gone. So this is semiconductor. We have acceptors. They are accepting one electron from semiconductor, so they will have negative ion. So these are acceptor ions. Corresponding to each acceptor ion, we have a hole. So we have a hole, and there are few electrons also. They are minority carriers. So this is your electron, which is being represented by solid dot. This is hole, which is being represented by circle, and these are negative ions they are known as acceptor ions. So this is about N and P type semiconductor. I'm trying to put into one slide. So you first take a pic from here to here, right? उसके बाद मैं इसे दिखा दूंगा, right? Interaction of semiconductor with light would be much appreciated. Everything would be covered. Don't worry, Arif Khan. Don't worry. Each and everything would be covered. We have sufficient time. I have started in the way you may have felt that I am not going to leave anything. You just keep patience. We have been allotted a time from 9 to 5. Sorry, 9 to 2, not 5, 9 to 2. So we have 5 hours. In 5 hours, I will summarize each and every formula, each and every concept we are going to discuss here. Don't worry about that. बिल्कुल चिंता ना करें. अगले 4.5 घंटे में हम लगभग सब कुछ जितना कुछ EDC में है लगभग सब कुछ रिवाइज करेंगे. गुड मॉर्निंग एवरीबॉडी. गुड मॉर्निंग. It's very cold here in Delhi today. Up to yesterday weather was relatively better, but today again things turned out another way. बहुत ही ज़्यादा ठंड है आज. बिल्कुल सुबह उठने का मन नहीं हो रहा था. We have taken this epic. Let's move on. Dear friends, if doping level is very high, then semiconductor is if you have moderately doped semiconductor, I am not telling the range of doping, that's not important. Moderately doped semiconductor, usually the range of moderately doped semiconductor is when you are adding impurity 1 in 10 to the power 6 or 1 in 10 to the power 7 or 1 in 10 to the power 8. So basically the range is from this one impurity atom in 10 to the power 6 to 10 to the power 8 atoms of the semiconductor. Yeah, one part of impurity in 10 to the power 6 to 10 to the power 8 part of the semiconductor. Then such semiconductor is known as moderately doped, and usually it is represented by P or N type, right? If doping level is less than this, let us suppose you dope 1 into 10 to the power 11, right? So out of the 10 to the power 11 part of the impurity, out of the 10 to the power 11 part of the semiconductor, you are adding only one part of impurity. So impurity content is very less. Then such kind of semiconductor is known as lightly doped semiconductor. It will be known as lightly doped semiconductor. So reference is basically what? Reference is your moderately doped. So with respect to this, if doping content is less, then it will be known as lightly doped semiconductor. These lightly doped semiconductors are represented as P minus or N minus. They are represented as P minus or N minus. Let us suppose doping content is high. You are adding large amount of doping. Suppose out of the 1000 atoms of the semiconductor, you are adding 1 atom of the impurity, or out of the 1000 parts of the semiconductor, you are adding 1 part of the impurity. So 1:10 to the power 3. If the doping is in this range, then you say it heavily doped semiconductor. Heavily doped, sometimes also known as highly doped semiconductor. Both are same thing. Highly doped semiconductor. This should be represented as P plus or N plus, right? This plus and minus sign denoting what? The relative doping level. माइनस का मतलब मॉडरेट के कंपैरिजन में डोपिंग कम है, एंड प्लस का मतलब मॉडरेट के कंपैरिजन में डोपिंग ज्यादा है. ठीक है, सो इट इज जस्ट टू कंपेयर द डोपिंग लेवल. लेकिन ध्यान रहे, दिस इज आल्सो न्यूट्रल. everything, any doped semiconductor is neutral, whether it is p type or n type, it is electrically neutral. So इस माइनस या प्लस साइन से ये नहीं मान लेना है कि सेमीकंडक्टर पर कोई साइन है. नो, सेमीकंडक्टर इज इलेक्ट्रिकली न्यूट्रल. ये माइनस या प्लस हम लगा रहे हैं जस्ट टू डिनोट द लेवल ऑफ डोपिंग. माइनस डिनोट्स द डोपिंग लेवल इज लेस एज कंपैरिजन टू द मॉडरेटली डोप्ड सेमीकंडक्टर, एंड प्लस इज डिनोटिंग दैट डोपिंग लेवल इज हाई एज कंपैरिजन टू द मॉडरेटली डोप्ड सेमीकंडक्टर. राइट, एक क्वेश्चन गेट में इस पर पूछा गया कि एक हैवली डोप्ड पी टाइप सेमीकंडक्टर को कैसे रिप्रेजेंट करेंगे. सो पी प्लस से रिप्रेजेंट करेंगे उसे. लेकिन कई बार आपको एग्जाम में जैसे दो आपके पास मॉडरेटली डोप्ड सेमीकंडक्टर हैं और उनमें कंपेयर करना है, तो जिसकी डोपिंग ज्यादा होगी उसे P प्लस और जिसकी कम होगी उसे P रिप्रेजेंट कर देगा, या जिसकी ज्यादा होगी उसे P और जिसकी कम होगी उसे P माइनस रिप्रेजेंट कर देगा. तो उसका कतई ये नहीं मतलब नहीं समझना चाहिए कि यहां पर हम हैवली डोप्ड पहुंच गए हैं या लाइटली डोप्ड में है. नहीं, हो सकता है कि विद इन द मॉडरेटली डोप्ड भी उसे अगर दो लेवल में कंपेयर करना है तो ऐसा रिप्रेजेंट किया जा सकता है. सो इट इज जस्ट अ वे टू कंपेयर द टू डोपिंग लेवल्स एंड टू रिप्रेजेंट अकॉर्डिंगली. अगर मैं यहां पर बात करूं, सो द मटेरियल रिमेन्स ऑलमोस्ट इंट्रिंसिक, रिमेन्स intrinsic, yeah, behaves like intrinsic semiconductor, right? This is your extrinsic semiconductor. This is actually your extrinsic semiconductor. So during the entire course of discussion we are going to study this extrinsic semiconductor. This extrinsic semiconductor is known as non-degenerate semiconductor. Non-degenerate semiconductor. Actually, if the crystal structure is influenced, yeah, that is changing heavily, then we say degenerate structure. But because of very less amount of doping, the changes in crystal structure can be neglected, and we can assume that crystal structure of doped semiconductor is more or less same as the crystal structure of the semiconductor, intrinsic semiconductor. So that's why it is known as non-degenerate semiconductor. But if doping level is very high, then crystal structure of doped semiconductor will differ, significantly differ as comparison to the crystal structure of the intrinsic semiconductor, and such semiconductor will be known as degenerate semiconductor. So these semiconductors are known as degenerate semiconductors. These are known as degenerate semiconductors, right? Dear friends, in our course we are mainly going to focus on this semiconductor. हम प्रमुखतः इसे ही पढ़ेंगे, हमारे सिलेबस में यही सेमीकंडक्टर हमको पढ़ना है. सो वी हैव टू फोकस अवरसेल्फ ऑन नॉन डीजेनरेट सेमीकंडक्टर. ज्यादातर चीजें इसी से जुड़ी हैं. तो अगर कुछ ना कहा जाए और सिर्फ एक्सट्रिंसिक सेमीकंडक्टर लिखा हो तो उसका मतलब बाय डिफॉल्ट आप समझ करके चलेंगे कि हम लोग बात कर रहे हैं डीजेनरेट सेमीकंडक्टर की. वी आर टॉकिंग ओनली अबाउट डीजेनरेट सेमीकंडक्टर. अनय शुक्ला इज सेइंग दैट सर चाय पी लीजिए, क्लास वाली फीलिंग आ जाए. बिल्कुल चाय पियेंगे, लेकिन अभी क्या हुआ कि मैं सुबह सुबह थोड़ा सा लेट हो गया. आपने देखा होगा 9:10 हो गया. सो आई एम ट्राइंग टू कंपनसेट दैट 10 मिनट. उसको कंपनसेट करने की कोशिश कर रहे हैं. उसके बाद फिर करेंगे, यूजुअली जैसे क्लास में रहते हैं वैसे ही करेंगे, सारा कुछ रिवाइज करेंगे, आप चिंता ना करें. इनफैक्ट जो आपको 1 हफ्ते रिवीजन में लगता है या 3 दिन तो एटलीस्ट एक सब्जेक्ट में लग जाता है रिवीजन में, वो 3 दिन का काम मैं 5 घंटे में कराऊंगा. ये मेरा आपसे वादा है, आप चिंता ना करें. और एकदम प्रॉपर रिवीजन करेंगे हम लोग. अब एक क्वेश्चन आया था, उसके पॉइंट ऑफ व्यू से डिस्कस कर लेते हैं. दैट इज हाईली प्रोबेबल आल्सो. डोपिंग इन गैलियम आर्सेनाइड या डोपिंग इन कंपाउंड सेमीकंडक्टर. सो लेट्स डिस्कस दैट एज वेल. डोपिंग इन कंपाउंड सेमीकंडक्टर. डोपिंग इन कंपाउंड सेमीकंडक्टर. कंपाउंड सेमीकंडक्टर. बेसिकली जो हम एग्जाम्पल ले रहे हैं उसे गैलियम आर्सेनाइड का एग्जाम्पल ले रहे हैं. यही इंपॉर्टेंट है और एग्जाम में भी इसी में पूछा जाएगा. नाउ वी हैव 3 चॉइसेस. गैलियम इज 3rd group element, so its immediate neighbors are 2nd and 4th group, so we can add both 2nd as well as 4th group. Arsenic is fifth group element, so immediate neighbors are fourth group elements as well as sixth group elements. So we can add fourth and sixth. So now we have three choices to add dopant atoms in gallium arsenide. First, second group, then we have a fourth group, and then we have sixth group. So let us try to see one by one कि इनसे क्या होने वाला है. So सबसे पहले second group impurities, second group impurities. Second group impurities. What are second group impurities? The popular is zinc, cadmium, etc. जिनकी वैलेंसी 2 है, ठीक है. So if I talk about second group impurities, कैसे याद रखेंगे? We are going to develop a non-degenerate semiconductor. हम लोग क्या जनरेट करेंगे? नॉन डिजेनरेट सेमीकंडक्टर. सो क्रिस्टल स्ट्रक्चर शुड नॉट चेंज. सो क्रिस्टल स्ट्रक्चर इज नॉट चेंजिंग. इट मींस व्हाट? जिस भी एटम को रिप्लेस कर रहे हैं वो जिस तरह से बॉन्डिंग कर रहा था, आने वाली इंप्योरिटी भी उसी तरह की बॉन्डिंग करने का प्रयास करे ताकि क्रिस्टल स्ट्रक्चर सेम रहे, नेबर्स के साथ उसका इंटरेक्शन सेम रहे. सो नाउ इफ यू सी वी हैव गैलियम आर्सेनाइड, राइट? So this second group impurity is the neighbor of gallium. So it replaces gallium atoms. It replaces gallium atoms. ये किसको replace करेगा? Gallium atoms को. अब gallium has 3 electrons. So let's suppose originally it would have been in 3 bonds. ऐसा मान लेते हैं, just assume करते हैं. I'm not going into the depth of crystal structure. It has 3 electrons, so it would be sharing with the 3 neighbors. Now this is being replaced by what? We are replacing this by a zinc. Zinc has only 2 electrons. So 2 electrons will make these 2 bonds, let us suppose, but one is incomplete. So in order to complete this bond, it will take 1 electron from the semiconductor and will complete it. So it is accepting electron, so it is working like acceptor. It is accepting electron, so it is working like acceptor. And since it is accepting electron from the semiconductor, so an extra hole will be created in semiconductor. So now I can say that it function as acceptor type impurity. It function as acceptor type impurity. Acceptor type impurity. रिजल्टिंग सेमीकंडक्टर इज पी टाइप सेमीकंडक्टर. जो सेमीकंडक्टर बनेगा वो आपका पी टाइप सेमीकंडक्टर बन करके तैयार होगा. दिस वुड बी पी टाइप सेमीकंडक्टर. सो क्वेश्चन बनता है कि व्हेन जिंक इज एडेड इन गैलियम आर्सेनाइड देन व्हाट विल हैपन. सो व्हेन जिंक इज एडेड इन गैलियम आर्सेनाइड, जिंक विल रिप्लेस गैलियम एटम्स, राइट? And it will function as a acceptor type impurity, and the resulting semiconductor is a p type semiconductor. Clear? Crystal clear, right? Next आते हैं, let us suppose we are adding 6th group impurity. Let us suppose we are adding 6th group impurity. 6th group impurities are added. Group impurities. Can you tell me some examples of 6th group impurities? Yes, some popular examples are selenium, tellurium, etc. Right? These are the examples. Now let us suppose I talk about selenium. So let us see here. What is selenium? Selenium is 6th group, right? And in gallium arsenide, you see arsenic is 5th group. So this will try to replace its immediate neighbor. So immediate neighbor yani arsenic will be replaced. So it replaces arsenic atoms. It replaces arsenic atoms, right? Now let us see. Arsenic has 5 electrons, so it is having 5 electrons like this, like this, like this, like this, like this. Let us suppose it is sharing with the 5 atoms. Just imagine 5 electrons, so it would have been sharing one electron with the neighbors, something like that we are trying to imagine. Actual crystal structure I am not discussing. I am not interested even in that. Although that is known as zinc blende crystal structure in material science, I talk about that crystal structure. But here I am not interested in that. Just see, just try to visualize. Now this is being replaced by what? It is being replaced by selenium. Selenium has 6 electrons. It has 6 electrons. So out of these 6, 5 would be utilized, to make the structure as it was earlier. And you have one extra electron. This electron is what? Extra. So this extra electron would be donated to the semiconductor. If it is donating, then it will be known as donor. So it will function as donor type impurity. And since it is donating one extra electron to the semiconductor, so in semiconductor electrons will become majority carriers. So semiconductor will become N-type semiconductor. So now I can summarize that it function as acceptor type impurity. It function as acceptor type impurity. Sorry, donor type. Extremely sorry. It function as donor type impurity. Donor type impurity. And resulting semiconductor is N-type semiconductor. Resulting semiconductor is N-type semiconductor. The resulting semiconductor is N-type semiconductor. So this is when we are adding the 6 group impurity in this particular material. Now let us go for the last type of impurity. 4th group impurities are added. 4th group impurities. 4th group impurities are added. कौन से 4th group है? Silicon and germanium. Carbon we cannot add. Carbon is very small. So very small होने की वजह से वो interstitial places पर जाएगा. We want substitutional impurities. So we will not use carbon. We are going to use only silicon or germanium. ये interstitial क्या है, substitutional क्या है, ये सारी कहानी हम लोग मटीरियल साइंस में करते हैं. आपने पढ़ा होगा मुझसे मटीरियल साइंस, तो वहां पर हमने ये कथा की है, यहाँ जरूरी नहीं है. आइए इस पर बात करते हैं. These are able to replace both gallium as well as arsenic atoms. These are able to replace both gallium as well as arsenic atoms. Such impurities are known as amphoteric. Such impurities are known as amphoteric. Those which are capable of replacing both, they are known as amphoteric. Now you see, let us suppose this silicon is replacing gallium. So gallium has 3 electrons and it would be replaced by silicon. So when silicon is replacing, silicon has 4 electrons. So out of these 4, 3 will be utilized to make the bonds and 4th one is extra. So this extra electron it will donate, and if it is donating, then it will work like donor. And if it is working like donor, then N-type semiconductor will be formed. So if silicon is replacing gallium atoms, then it function as donor type impurity and resulting semiconductor is N-type semiconductor. So you can see if silicon या germanium is replacing या acquiring gallium positions, replacing gallium atoms, then they function as donor type impurity. Donor type impurity, and resulting semiconductor is N-type, and resulting semiconductor is N-type. ठीक. Let us suppose अब हम लोग क्या करें कि गैलियम की बजाय आर्सेनिक को रिप्लेस करें. So arsenic has 5 electrons. Let us suppose this kind of 5 bonds is making with the neighbors. Now it is being replaced by silicon. Silicon has only 4 electrons. So in order to make the structure like arsenic is making, it has to accept 1 electron from the crystal. So since it is accepting electrons, so it will function like acceptor. And if it is functioning like acceptor, 1 extra hole would be created here and the resulting semiconductor will become p-type. So you can say that if if silicon or germanium is replacing arsenic atoms, then it function as, they function as acceptor type impurity. Acceptor type impurity. They function as acceptor type impurity, and resulting semiconductor is p टाइप. यही गेट में पूछा जाता है, पूछा गया भी था. सो दिस वन इज इंपॉर्टेंट क्योंकि यहां कई बार लोगों को कंफ्यूजन हो जाता है. अब ये एक स्लाइड में तो नहीं आएगा, सो पहले आप थोड़ा सा छोटा करते हैं, अगर देखने की कोशिश करें. देखें आ रहा, यस, कॉपी कर लें. I mean take the pic, not copy. Don't copy, just take the picture. Good. This is very important concept and lots of people get confused in this also. So in order to avoid the confusion, I have used these pictorial notations. Right? This is not the actual crystal structure. ये actual crystal structure नहीं है, just आपको समझाने के लिए मैं चाह रहा हूँ कि आप visualize करें कि किस तरह से चीजें हो रही होंगी और उसके हिसाब से आपको याद रखना easy हो जाएगा. ठीक है? You may have taken this pic. Now you can take this one also. चलिए. So up till now we have covered doping and doped semiconductors, all that. Move on to the next. Next, concept of electric field intensity. What is electric field intensity? Let us see. Electric field intensity. I will be representing it as E or sometimes like this also. In one of the heading I will be representing like this, otherwise like this. Let us suppose we have a semiconductor material. This is our semiconductor, and we are adding voltage across it, something like this. We are connecting a source. Let us suppose this source is like this. Suppose we define axis like this. This is x-axis, right? This point is x is equal to 0, and this point is the length of the semiconductor is L. So this point is x is equal to L. You know, my dear friends, this is high potential. Plus sign denotes high potential. So this side is at high potential, and this side denotes at low potential. Let us suppose phi potential I am representing as a function of x, and I represent potential as phi x, potential as a function of x, that is phi. Yeah, you can write it as phi x, right? I am representing here just phi, हमारे आपके बीच की mutual understanding. So the value of phi, that is potential at this point, is phi is equal to 0 here, and the value of potential here is phi is equal to V naught, right? Dear friends, what is the electric field intensity? Electric field intensity is defined as negative of the potential gradient. Gradient means slope. So if phi is function of x, then d phi upon dx is representing the slope. So negative of this slope represents electric field intensity. So if you see this minus d phi, delta phi, so 0 minus v naught upon delta L, that is, yeah, delta x, L minus 0. This minus plus v naught by L. What is v naught? V naught is nothing but the potential difference. It is what? V naught minus 0, right? This is what? V naught minus 0, that is the potential difference across this high potential to low potential. So how will you calculate the electric field? पूरी सब्जेक्ट में कहीं भी अगर आपको इलेक्ट्रिक फील्ड कैलकुलेट करना है तो कैसे कैलकुलेट करेंगे? आप उस स्पेसमेन के अक्रॉस पोटेंशियल डिफरेंस कैलकुलेट करके और उसे लेंथ से डिवाइड कर दीजिए. सो दिस बेसिकली डिफाइंड एज वोल्टेज per unit length, या potential difference per unit length. This is the concept, right? So जहां भी आपको, let's suppose आपको इस लेंथ में कैलकुलेट करना है, आपको कहीं बीच में कैलकुलेट करा रहा है, ठीक, तो इसके क्रॉस पोटेंशियल डिफरेंस कैलकुलेट कर लीजिए और इस लेंथ से डिवाइड कर दीजिए, यू विल गेट द इलेक्ट्रिक फील्ड. Electric field is always directed from high potential to low potential. So the electric field intensity is always directed from high to low potential. So you can write this point also. So electric field intensity is electric field intensity is directed from high potential to low potential, from high potential to low potential. It is directed from high potential to low potential. ठीक, so direction आपको पता करनी है, तो you see where is high potential and where is low potential, it will always be directed from high to low potential. And magnitude आपको पता करना है, तो कैसे कैलकुलेट करेंगे? Try to calculate the potential difference across the length and divide it by the length. So potential difference per unit length, that will give you the electric field intensity. Unit generally volt per centimeter I will be using in our subject, volt per centimeter. The unit for this electric field intensity we are going to use is volt per centimeter, that is volt per meter, but in our subject the length unit I will be taking as centimeter, so volt per centimeter. Now dear friends, you see some important thing. Force experienced by a charge due to electric field is Q into E. Suppose I talk about electrons, so for electrons the charge is negative, right? So the force is minus Q into E. Minus sign indicates that the force experienced by the electrons is opposite to the electric field direction. So electric field is directed from high to low, so electron will experience force from low to high. So electrons will always travel in this direction. So electrons travel from low potential to high potential. मैं लिखाऊंगा नहीं, सुनते चलिएगा मुझे यहाँ से. I am concluding that कि force experienced by the electron is against the direction of electric field. So electric field is directed from high to low potential. So electrons will be moving from low to high. So under the influence of electric field, electrons will always move from low potential to high potential. Similarly, if I talk about holes, so for holes what we are having? For holes are having positive charge. So for holes you can say it is plus Q into E, right? So this positive sign indicates that the force experienced by holes is along the direction of the field. So force on holes is along the direction of field. Now you see dear friends, field is from high to low. The force experienced by the holes is also from high to low. So holes would be moving like this, right? So under the influence of an electric field, a hole will be moving from high potential to low potential. Similarly, under the influence of an electric field, the electron would be moving from low potential to high potential. Everything related with the electric field is represented here. You see this, then we would be moving forward. ये आप देखिए, उसके बाद हम आगे चलेंगे. Ankit is saying, hello sir, seeing you after long time, skipped giving mock today just because of this session. Thank you Ankit to be here and you will not regret your decision. आप अपने decision को बिल्कुल भी regret नहीं करेंगे, क्योंकि हम चाहेंगे कि सेशन को इतना प्रोडक्टिव बनाया जाए कि आपने जो स्किप किया है उससे एटलीस्ट कम नहीं, कम से कम उतना या उसके बराबर तो फायदा आपको मिले ही. अगर ज़्यादा ना हो सके तो कम से कम उतना फ़ायदा तो मिले ही जितना कुछ आपने स्किप किया. थैंक यू टू बी हियर. लेट्स मूव ऑन. कीप ऑन आस्किंग आल्सो इफ यू वांट टू आस्क एनीथिंग. जो कंसेप्ट चल रहा उस कंसेप्ट में अगर कोई आपको डाउट है, कुछ है, तो आप पूछ भी सकते हैं. बिल्कुल चिंता ना करें कि हम आपके डाउट नहीं लेंगे, ऐसा कुछ सोचने की ज़रूरत नहीं है. आई विल बी मोर देन हैप्पी टू टेक योर डाउट्स. चलिए आगे चलते हैं. अब कुछ कंसेप्ट्स जो बहुत डेप्थ में ना जाकर के उनको सरफेस पर डिस्कस करेंगे, जैसे ड्रिफ्ट वेलोसिटी. ड्रिफ्ट वेलोसिटी यूजुअली आई विल बी रिप्रेजेंटिंग इट बाय वीडी, राइट? It is the velocity acquired by the charge carriers. It is the velocity acquired by charge carriers under the influence of an applied electric field. It is the velocity acquired by charge carriers under the influence of applied electric field. It is the velocity acquired by the charge carrier under the influence of applied electric field. किसी इलेक्ट्रिक फील्ड के इन्फ्लुएंस में चार्ज कैरियर्स के द्वारा जो वेलोसिटी एक्वायर होगी उसे हम लोग ड्रिफ्ट वेलोसिटी कहेंगे. सो दिस ड्रिफ्ट वेलोसिटी इज यूजुअली गिवन एज म्यू एन इनटू ई, राइट. लेकिन इसके साथ कुछ प्रॉब्लम है. क्या प्रॉब्लम है अभी देखेंगे हम. पहले टर्म से समझें. सो दिस बी डी इज ड्रिफ्ट वेलोसिटी, ई इज इलेक्ट्रिक फील्ड, दिस म्यू एन इज नोन एज mobility of electron. Everything I am discussing for electron, that will be equally valid for holes also. So mobility of electrons, this is mobility of electrons. क्या होता है mobility अभी हम लोग बात करेंगे, लेकिन उससे पहले देख ही लेते हैं. Mobility, what is mobility? It is defined as drift velocity per unit applied electric field. Drift velocity per unit applied electric field. It is defined as drift velocity per unit applied electric field. It is defined as drift velocity per unit applied electric field. इसकी यूनिट क्या हो जाएगी? सेंटीमीटर स्क्वायर पर वोल्ट सेकेंड, राइट. BD सेंटीमीटर पर सेकेंड एंड वोल्ट पर सेकेंड, सेकेंड हो जाएगा तो सेंटीमीटर स्क्वायर per volt second. This is the unit, या meter square per volt second. That is the unit of mobility. Mobility denotes the quickness of movement of charge carrier under the influence of an applied electric field. So this is the definition of drift velocity and mobility. But इससे अपना काम नहीं चलेगा. जरा एक कर्व देखते हैं. I am drawing this curve for silicon. So if I draw this curve for silicon, you see here. This is drift velocity. I am writing it in centimeter per second, and this is electric field. I am writing it also in volt per centimeter. It is volt per centimeter. Now initially the drift velocity increases linearly with applied electric field and mobility remains constant. But this is true only for the low electric field region. Values approximately up to 10 to the power 3 volt per centimeter. This region of electric field is known as low electric field region. Low electric field region. Electric field region. In this low electric field region, the relationship between electric field and drift velocity is linear. That's why sometimes also known as linear region. It is known as linear region. Now if we increase the electric field, then with increase in electric field, now the average collision time will also change. Up to this moment we are assuming that average collision time is independent of electric field. But now if electric field will become very high, then average collision time will also change with the electric field, and because of which collisions will start becoming rapid, and hence increase in drift velocity will become slow. Now it will increase sublinearly. So up to this point the increase is sublinear. This is 10 to the power 4, right. After this point the drift velocity will become constant and it will saturate. It will become constant and it's saturated. This saturates near about 10 to the power 7. You will not use this value in exam, actually that value would be given, but roughly around 10 to the power 7. So here you see this region, the variation is sublinear, basically parabolic. Sublinear region, and here the drift velocity has become constant, so this region is known as saturation region. This is known as saturation region. Now you see my dear friends, this value of the electric field, yeah, this region where the electric field is greater than 10 to the power 4, this is known as high electric field. High electric field region. Few conclusions. First conclusion, in low electric field region, drift velocity linearly increases with the applied electric field, and in high electric field region, drift velocity saturates with respect to electric field. तो ये जो relation है BD is equal to mu1 into E, I will advise कि use into the linear region. इसे सिर्फ linear region में ही use करेंगे आप, क्योंकि लीनियर रीजन में ही जब मोबिलिटी आपकी कांस्टेंट है तो उस समय ड्रिफ्ट वेलोसिटी इज द लीनियर फंक्शन ऑफ द इलेक्ट्रिक फील्ड. बाकी रीजन में आपकी मोबिलिटी भी वेरी कर रही है, सो दिस रिलेशन इज नॉट एडवाइजेबल टू बी यूज्ड. सो इसके कोई भी क्वेश्चन को करने से पहले रीजन ऑफ इलेक्ट्रिक फील्ड पता करना बहुत जरूरी है, क्योंकि अगर आप देखें इस रीजन में है तो किसी भी वैल्यू ऑफ इलेक्ट्रिक फील्ड के लिए ड्रिफ्ट वेलोसिटी कांस्टेंट होगी. आपने अगर कहीं इस रिलेशन से कैलकुलेट किया तो हो सकता है कि आपको सम डिफरेंट वैल्यू मिले व्हिच इज ग्रेटर देन द सैचुरेशन वेलोसिटी, जो कि संभव नहीं है. ठीक है, तो इसलिए इसको देखना बहुत जरूरी है. अब एक और चीज यहां से अगर हम मोबिलिटी वर्सेस इलेक्ट्रिक फील्ड की बात करें तो क्या होगा. सो लेट्स मेक अ ग्राफ बिटवीन मोबिलिटी वर्सेस इलेक्ट्रिक फील्ड. दिस इज इलेक्ट्रिक फील्ड, वोल्ट पर सेंटीमीटर, सॉरी हाँ ठीक है, एंड दिस इज मोबिलिटी mu1, दैट इज सेंटीमीटर स्क्वायर पर वोल्ट second. ठीक, the same two regions I will mark. The first one is 10 to the power 3. This is our low electric field region. Low electric field region. Electric field region. Right. This is low electric field region, and then this region. This is 10 to the power 4. This one is high electric field region. This is high electric field region. इसे हम लोग high electric field region कहेंगे. Now you see in low electric field region, drift velocity is linear function of electric field, so mobility is constant. So for this reason, the value of mobility will remain constant. This is constant. mu1 is constant. mu1 is equal to constant. This constant value at room temperature is different for different materials. Those who are going for engineering services, so उनके लिए मैं एक डेटा दे रहा हूँ. Not advisable to be used in numerical problems, but engineering services में कई बार डायरेक्ट वैल्यू पूछ लेते हैं. So it is roughly around 1350 सेंटीमीटर स्क्वायर पर वोल्ट सेकेंड फॉर सिलिकॉन. अगर हम बात कर रहे हैं फॉर सिलिकॉन इलेक्ट्रॉन की मोबिलिटी, एंड फॉर होल्स इट इज रफली अराउंड 500 सेंटीमीटर स्क्वायर, 500 सेंटीमीटर स्क्वायर पर वोल्ट सेकेंड. एग्जैक्ट वैल्यू नहीं है, रफली एट रूम टेम्परेचर यू विल रिमेंबर दिस वैल्यू. फॉर जर्मेनियम अगर हम लोग बात करें इसकी, सो फॉर जर्मेनियम mu1 इज रफली अराउंड, नॉट एग्जैक्ट वैल्यू, अप्रॉक्सीमेटली 3800 centimeter square per volt second, and mu p is roughly around 1800 centimeter square per volt second. Those who are going for some public sector examination and for engineering services, they need to remember this values. गेट के लिए जरूरी नहीं है, गेट में आपको वैल्यू दी रहेगी, और अगर एग्जाम में किसी क्वेश्चन में मोबिलिटी की वैल्यू दी हुई है तो उसी वैल्यू को आप यूज करेंगे, इस वैल्यू को यूज नहीं करेंगे. दीज आर द टिपिकल वैल्यूज ऑफ मोबिलिटी एट द रूम टेम्परेचर. वन वेरी कॉमन थिंग व्हिच यू कैन ऑब्जर्व फ्रॉम दीज टू एग्जांपल्स, दैट इज मोबिलिटी ऑफ इलेक्ट्रॉन इज always greater than the mobility of hole. mu1 denotes mobility of electron and mu p denotes mobility of hole. So mobility of electron is always greater than the mobility of holes. Now this is valid only for this reason. Now in this reason, if you see, the drift velocity increases sublinearly, so this will also start decreasing. So it decreases sublinearly. So here mobility becomes function of mu1 becomes function as e to the power -1/2. राइट, मैं इसे यहां लिख दे रहा हूं इस रीजन के लिए. mu1 becomes e to the power -1/2. राइट, mobility varies like this. इस पर क्वेश्चन बनते हैं. सो यू नीड टू फाइंड आउट कि इलेक्ट्रिक फील्ड के किस रीजन में है और उसके हिसाब से मोबिलिटी का इलेक्ट्रिक फील्ड के साथ क्या वेरिएशन है. देन इफ यू गो फॉर द हाई इलेक्ट्रिक फील्ड रीजन, ड्रिफ्ट वेलोसिटी विल कांस्टेंट, एंड इफ ड्रिफ्ट वेलोसिटी इज बिकमिंग कांस्टेंट, देन मोबिलिटी विल बिकम लाइक दिस. मोबिलिटी इज inversely proportional to electric field. This sometimes I also write like this, mu n is directly proportional to e to the power minus 1. Right. So this is about the mobility versus electric field, mobility versus drift velocity versus electric field. These relations you will be requiring during solving questions. Please go ahead. अर्शदीप, लग रहा आप लेट ज्वाइन किए हैं सर. मास कैपेसिटर तक जाएगा या सिर्फ चैप्टर? अरे पूरा जाएगा यार, आपको पूरा चारों ब्रांच रिवाइज, चारों ब्रांच कह रहे हैं, आपको तो पूरा 10 सब्जेक्ट रिवाइज कर ले. ठीक है, ईडीसी पूरा करेंगे, डोंट वरी, पूरी करेंगे. आप बैठे रहिएगा बस. हाँ, आप जल्दी भाग जाएंगे तो लाइव सेशन है, ये कौन सा क्लास का सेशन है, तो फिर मैं भी उठ करके चला जाऊंगा. ठीक, लेकिन अगर आप बैठे रहेंगे तो हम पूरा रिवाइज करेंगे. देखो, फर्स्ट चैप्टर में ही ज्यादा टाइम लगेगा क्योंकि बाकी चैप्टर्स में फार्मूले उतने ज्यादा होते नहीं है, कंसेप्ट उतने ज्यादा है नहीं. सो फर्स्ट चैप्टर इज गोइंग टू टेक लॉट्स ऑफ टाइम एंड आफ्टर दैट वी आर नॉट गोइंग टू टेक दैट मच टाइम. उसके बाद उतना समय नहीं लगेगा. कुछ चाय वाय पिला दो भाई. देखो, बच्चों तक को पता है, चीनी कम रखना. चलिए आगे चलते हैं. अब जब मोबिलिटी की बात कर ही रहे हैं तो मोबिलिटी वर्सेस टेम्परेचर की भी बात कर लेते हैं. सो मोबिलिटी वर्सेस टेम्परेचर, ऐसे बात करें, स्कैटरिंग मैकेनिज्म्स लिख लेते हैं. स्कैटरिंग mechanisms. In semiconductor we bother about two scattering mechanisms. First scattering mechanism is this is lattice scattering, या इससे पहले impurity scattering देख लेते हैं. The first one is impurity scattering. Impurity scattering. So scattering of electron due to impurity atoms. Impurities are what? Donors, acceptors. So because of these impurity atoms, whatever is the scattering, that is known as impurity scattering. उसे हम लोग impurity scattering कहेंगे. अंकित कुमार कह रहे हैं कि there is a relationship between mobility and effective mass. There is a relationship between mobility and effective mass. जी 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 जी, अभी बात करेंगे अंकित, चिंता ना करें, उस रिलेशनशिप के बारे में भी बात की जाएगी. थोड़ा सा पेशेंस रखें, मैं अभी जो टॉपिक शुरू किया हूं इसको पहले कंप्लीट कर लें. ठीक. सो दिस इम्प्योरिटी स्कैटरिंग इज बिकॉज ऑफ द डोनर्स आर एक्सेप्टर एटम्स, जो है उनके कारण अगर इलेक्ट्रॉन स्कैटर हो रहा तो उसकी बात कर रहे हैं. डोमिनेंट एट लो टेम्परेचर्स, डोमिनेंट एट लो टेम्परेचर्स, usually below 100 Kelvin, usually below 100 Kelvin. Although for material to material it will differ, but usually we talk about below 100 Kelvin. So it is dominant at low temperature. And what happens? This mu, I'm writing it because of impurity, so mu I, right? Mobility because of impurity scattering. This is directly proportional to T to the power 3/2 upon Ni. What is Ni? Ni is impurity. Ni is impurity concentration. Impurity concentration. So with increase in impurity concentration, mobility will decrease, and with increase in temperature this mobility will increase. ठीक, इसकी मैकेनिज्म मैं क्लास में समझाया हूं कैसे क्या होती है, उसमें हम नहीं जाएंगे. राइट, लेट अस सपोज यू हैव टेकन अ सेमीकंडक्टर इन व्हिच impurity concentration is constant. So if impurity concentration is constant, then mu I will become directly proportional to T to the power 3 by 2. This relation is useful. We will be using this in future also. This is impurity scattering. Now we are going to talk about lattice scattering. Lattice scattering is because of the atomic vibration. Lattice scattering, स्कैटरिंग की स्पेलिंग गलत हो गई, सही करते हैं, SCATRING, lattice scattering. This is due to atomic vibration. It is due to atomic vibration. You know, it is because of atomic vibration, right? So if it is because of atomic vibration, temperature is going to be crucial. So dominant at high temperature, dominant at high temperature. High का मतलब यहाँ बहुत high नहीं, high का मतलब greater than 100 Kelvin, T greater than 100 Kelvin. So at room temperature, the dominant mechanism would be lattice scattering. At room temperature, if nothing is said and he is talking about room temperature, then at room temperature this would be dominant. Then you can say here, lattice scattering के कारण mobility mu L is inverse, it is directly proportional to T to the power minus 3 by 2. So with increase in temperature, mobility will decrease. So at low temperatures, with increase in temperature, mobility will increase, and at high temperatures, with increase in temperature, mobility will decrease, right? Effective mobility, if you talk about overall mobility, let us suppose you consider both mechanisms simultaneously, then effective mobility, mu effective is equal to 1 upon mu due to impurity plus 1 upon mu due to lattice. Or you can write it as mu effective is equal to mu L into mu I upon mu L plus mu I, right? This is the effective one. यहाँ पर हम लोग log स्केल पर मोबिलिटी वर्सेस टेम्परेचर के बीच में ग्राफ बनाते हैं. हाउ डज दिस ग्राफ लुक्स लाइक? इट इज योर log scale, right? So basically this is log of mu and this is log of temperature, right? So on the log scale it looks like this. This is, and then sorry, what happened? Oh no. ये कैसे हो गया? क्या करेंगे इसको? आइए, हाँ ठीक है. Now you see, so this graph is like this. Okay, this is denoting your lattice scattering. Lattice scattering. So in lattice scattering, what happens? Mu L is directly proportional to T to the power minus 3 by 2, and this is denoting your impurity scattering. In impurity scattering, what happens? Impurity scattering. So impurity scattering, mu I is directly proportional to T to the power 3 by 2. So if I combine these two curves, it actually goes like this. This inverted parabola, right? This one is our actual graph. This inverted parabola is the graph for the overall mobility versus temperature on log scale. So this is we are going to discuss. Let's please see this. Please go ahead. Scattering mechanisms, write down. Rishabh Yadav is asking, sir, how two scattering mechanisms can occur simultaneously? Why not, dear? दोनों simultaneously कैसे नहीं हो सकती? आप देखें, let us suppose you have a intrinsic semiconductor, and in that intrinsic semiconductor you have added some impurity. So if you have added some impurity, so that impurity will try to scatter electron. That impurity is in the material, and whenever electron is coming under the influence of that impurity, it will scatter that. Simultaneously, this material is kept at some temperature, let us suppose at room temperature. So because of that temperature, atomic vibration is taking place, and whenever an electron comes into contact of that atomic vibration, it will get scattered. So there are chances that either the electron is being scattered by impurity, or it is being scattered by the atomic vibration. अब probability का concept लगा दीजिए. The probability of being scattered due to the atomic vibration, or probability of being scattered due to impurity. So overall probability will be P1 plus P2, right? Add these probabilities and then solve it. मैंने क्लास में इसको derive कराया है 1 by tau c करके and probability के term में. So probably you go to your notes and you will find it there. वहाँ पर हम इसको derive कराते हैं. यहाँ obviously derive कुछ भी नहीं करेंगे, right? Hope you got the point. Rishabh, शायद समझ में आ गया होगा. अगर नहीं समझ में आया तो क्लास नोट्स में जाइए, वहां हमने इसको डेराइव भी कराया हुआ है. ठीक, गो फॉर इट. नाउ EK डायग्राम, EK डायग्राम, EK diagram. Dear friends, what is K? As per de Broglie, the wavelength is h by p, where p is momentum, it is wavelength, and this is momentum. Momentum is what? Mass into velocity, you know it very well. And this is Planck's constant. It is Planck's constant. ये क्या है? प्लांक का कांस्टेंट. h की वैल्यू हम सभी जानते हैं. h इज इक्वल टू 6.626 इंटू 10⁻⁻34 जूल सेकेंड. आपको याद रहना चाहिए. दीज आर द यूनिवर्सल कांस्टेंट, यू शुड बी नोइंग देम. आप सभी ने EMT पढ़ा होगा. EMT में यू डिफाइन अ टर्म वेव नंबर, दैट इज k. ठीक. सो k इज 2 पाई बाई lambda. This k is nothing but wave number. Here we will be naming it as momentum vector also. Why? That would be obvious very soon. Now if I put the value of lambda, then k is equal to 2 pi upon h by p. So I simplify this, p into 2 pi upon h. So I can write it as P is equal to h by 2 pi into k. H is constant, h by 2 pi is also constant. So P is equal to h bar into k. Yeah, this one. So this h bar is known as reduced Planck constant, given like this. So you see k and p are interrelated by a constant, so both represent momentum, nothing else. So k को हम लोग यहाँ momentum की तरह treat करके चलेंगे. We will be treating it like momentum, although it is wave number, not exactly the momentum. Momentum is mass into velocity. K is 2 pi by lambda. So when you know k, if you multiply by h bar, then you will get momentum. Relation is in front of you. How is the tea? Can you taste it? How is it? Let's go for this. Now you see, if I develop a relationship for a free electron, I have discussed all those concepts. So when electron is free from the influence of its parent nucleus, then its energy should be 0 or positive. So minimum energy is 0. Now whatever energy you will give to this electron, it will take that energy and will start moving. So all the energy of the free electron will get converted into the kinetic energy. Let us suppose the effective mass of electron is Mn, right? So Mn star I am saying. So Mn star के term में अगर हम energy of electron लिखें, this is not electric field, this is energy of electron, energy of electron, right? This is equal to half into Mn star into V square, half mv square, where V is the velocity of electron and Mn star is effective mass of electron. This is Mn star is effective mass of electron, effective mass of electron. It is the effective mass of electron. Now you see, this can also be written as Mn into V is momentum, so you multiply by Mn and divide by Mn, it will become momentum square by 2Mn. So E can be written as P square upon 2Mn star. These relations you should be knowing. You can use them in numerical problems, right? Now P is equal to H bar into K, so E can be used as H bar square into K square divided by 2Mn star. This is the energy versus K. You see here, effective mass in a particular material would be constant for the electron. Material to material its value will be different, but for a particular material it should be constant. Although that's also not true, that depends upon several other factors. Well, let's assume it's constant. And K is a momentum vector. So E versus K, if you draw, it is nothing but y is equal to x square. Y is equal to x square is a parabola. So the EK diagram will look like this. It will look like parabola, something like this. Let us suppose I am drawing for the electrons. So E, electrons are here in the conduction band. Let us suppose it is EC. So this will look like this for the electrons. It is the EK diagram for electron. For holes, there is nothing difference. Electron has negative charge, holes have positive charge. So everything will become inverted. So if I talk about holes, let us suppose this is the valence band. So for holes, this go something like this. This parabola is going to be like this. So this denotes conduction band and this denotes valence band. Right? This is the EK diagram, not the exact one. Exact one I am going to make just in a moment. You see, just the concept आप देखिए. अब यहाँ से मैं अगर इसे differentiate करता हूँ, let's differentiate this with respect to K. So dE upon dK, this comes out as H bar square 2Mn star into 2K. 2 will get cancelled, d2E upon dk2, again you differentiate this, so it is H bar square upon Mn star. So if I talk about Mn star, then this Mn star is equal to nothing but H bar square upon d2E dk2, right? This is your effective mass of electron, which depends upon the second derivative of EK diagram, and that is inversely related. So this denotes basically slope. If it has high slope, then this value would be high. So high slope means narrow parabola like this. So slope is high. If this value is high, effective mass would be less. So for such parabola, the effective mass would be less. But let us suppose the parabola is like this, shallow. Then if it is shallow, then slope would be lesser. If slope is lesser, then effective mass would be higher. So effective mass of the electron will depend upon the slope of the parabola in the EK diagram, right? You first note down this, then I have to discuss few things and then we would be moving towards the next concept. Please do it. पिछले कुछ दिनों से मैं आप में से बहुत सारे लोगों की क्वेरीज नहीं ले पा रहा था. अनुराग पर भी एक्टिव कम था ग्रुप पर, हालांकि मैंने कुछ आपके सीनियर्स को बोल रखा है टू रिप्लाई योर क्वेरीज एंड दे आर डूइंग enthusiastically. Thanks to them also. They are ES qualified students and they are replying, they are responding to the queries. फिर भी अगर किसी की कोई क्वेरी रह गई हो और मैं ना रिप्लाई कर पाया हूं तो उसके लिए क्षमा प्रार्थी हूं और दोबारा भेजिएगा, कोशिश करेंगे रिप्लाई। कई बार क्या होता है कि आप लोग बहुत लेंदी क्वेश्चंस भेज देते हो, अब पेन पेपर लेकर के उनका सॉल्यूशन कर पाना मुश्किल है, ठीक है। तो छोटे मोटे कंसेप्ट तो मैं वॉइस रिकॉर्ड करके भेज देता हूं, बट बहुत बड़ा क्वेश्चन अगर हो जाता है तो थोड़ा मुश्किल हो जाता है। चलिए आगे चलते हैं, लेट्स मूव ऑन टू द नेक्स्ट कंसेप्ट। अच्छा, मैं ईके डायग्राम फॉर गैलियम आर्सेनाइड, ईके डायग्राम फॉर सिलिकॉन वो सब नहीं बना रहा हूं क्योंकि वो कंसेप्ट थोड़ा गेट के लिए उतना इंपॉर्टेंट नहीं है, डायरेक्ट इनडायरेक्ट बैंड गैप वगैरह में नहीं जा रहा हूं, ठीक। यहां केवल एक छोटी सी चीज जो मैं बातचीत करना चाहता हूं। Now effective mobility is nothing but Q tau C upon Mn star, right? So here Mn star is effective mass of electron and tau C is average collision time. It is average collision time. You should be knowing this, average collision time, and Q is magnitude of electronic charge. So this is your mobility of electron. So mobility of electron is inversely proportional to the effective mass of electron. डायरेक्ट इनडायरेक्ट बैंड गैप को नहीं जा रहे हैं क्योंकि गेट में मैंने उस पर क्वेश्चन उतने देखे नहीं हैं और ES के लिए जो नोट्स में दिया हुआ है उतना ही सफिशिएंट है, तो एक बार नोट से रिवाइज कर लीजिएगा। लेट्स मूव ऑन टू द नेक्स्ट कंसेप्ट, या अगर लास्ट में समय रहा तो रिवाइंड करा दीजिएगा, तो मैं डायरेक्ट इनडायरेक्ट को भी ले लूंगा। हालांकि मैंने पहले से मूड बनाया था कि उसके कंसेप्ट को नहीं डिस्कस करेंगे बिकॉज दैट्स नॉट मच इंपॉर्टेंट फॉर, या कर लें जैसा बताइए आप लोग, जल्दी बताइए, क्विकली रिस्पॉन्ड। डू यू वांट डायरेक्ट एंड इनडायरेक्ट बैंड गैप सेमीकंडक्टर टू बी डिस्कस्ड और वी शुड बी मूविंग टुवर्ड्स द नेक्स्ट टॉपिक? राइट, चलिए आगे चलते हैं। मूव ऑन, गुड, मूव ऑन, थैंक यू थैंक यू थैंक यू, गुड गुड गुड, लीव इट सर, वेरी गुड, वेरी, अरे क्या बात है, आप सभी बड़े लवली टाइप स्टूडेंट होते चले जा रहे हो, यही तो चाहता हूं मैं, ऑब्जेक्ट ओरिएंटेड। गुड, नेक्स्ट आई विल बी गोइंग फॉर सीक्वेंस, तो आपको पता ही होगा, ठीक है। सो आई विल बी गोइंग फॉर the concept of density of state and Fermi direct distribution, right? So let's go for the density of state या Fermi direct distribution, दोनों में से किसी पर भी चाह सकते हैं। तो सबसे पहले Fermi direct statistic पर बात कर लेते हैं। Good, Fermi direct statistic कितना इंपॉर्टेंट है मुझे कहने की जरूरत नहीं है, ठीक। ये अगर आप इलेक्ट्रॉनिक्स इंजीनियर हैं तो अपने आप खुद ही समझते होंगे, स्टैटिस्टिक्स, ठीक। यहां पर बनी हुई फाउंडेशन आगे के 30-40 मिनट हम लोग यूज करेंगे और डेफिनेटली एक क्वेश्चन पोजीशन ऑफ फर्मी एनर्जी लेवल से एग्जाम में पूछा जा रहा है। प्रीवियस कई सालों का पैटर्न आप उठा करके देखिए। सो देयर इज ऑलवेज वन क्वेश्चन रिलेटेड विद द पोजीशन ऑफ फर्मी एनर्जी लेवल इन वेरियस सेमीकंडक्टर्स। सो दिस इज वेरी इंपॉर्टेंट कंसेप्ट, सो लेट अस ट्राई टू डिस्कस दिस ब्यूटीफुली एंड ट्राई टू रिवाइज ईच एंड एवरी की कंसेप्ट हियर। फर्मी डायरेक्ट स्टैटिस्टिक ये पाउलीज एक्सक्लूजन प्रिंसिपल पर बेस्ड है। पाउलीज एक्सक्लूजन प्रिंसिपल, पाउलीज एक्सक्लूजन प्रिंसिपल सेज दैट कि no two electrons can have all the 4 quantum numbers to be exactly same। किन्हीं दो इलेक्ट्रॉन की चारों क्वांटम नंबर सेम नहीं हो सकती हैं। तो मैं अगर चारों क्वांटम नंबर से किसी इलेक्ट्रॉन की स्टेट को डिफाइन कर रहा हूं, सो आई कैन, स्टेट मीन्स द वैल्यू ऑफ एनर्जी। सो बेसिकली जो इलेक्ट्रॉन के पास एनर्जी होती है उसे एनर्जी स्टेट कहते हैं, ठीक। अभी आगे के टॉपिक में मैं बात करूंगा, अभी सिर्फ स्टेट पर फोकस रखें। या आप ऐसे समझ सकते हैं कि जिस चेयर पर इलेक्ट्रॉन बैठा होगा उस चेयर को स्टेट कह रहे हैं। तो अभी स्टेट का मतलब इतना ही समझे, आगे चलते हैं। तो किसी एक स्टेट पर कोई इलेक्ट्रॉन होगा तो उस स्टेट को डिस्क्राइब करने के लिए वी नीड 4 क्वांटम नंबर्स, and these 4 quantum numbers for 2 electrons cannot be same। इसका मतलब किसी एक स्टेट पर सिर्फ एक ही इलेक्ट्रॉन हो सकता है, दो इलेक्ट्रॉन नहीं हो सकते हैं, ठीक। सो फर्मी डायरेक्ट स्टैटिस्टिक इज बेस्ड ऑन दिस प्रिंसिपल दैट एट अ पर्टिकुलर स्टेट देयर कैन बी ओनली वन इलेक्ट्रॉन। तो आपके पास कोई एक स्टेट है, दिस इज योर स्टेट, राइट, दिस इज योर स्टेट। सो इस स्टेट पर सिर्फ एक ही इलेक्ट्रॉन हो सकता है। सो देयर आर टू पॉसिबिलिटीज फॉर दिस स्टेट। One possibility is either this state is occupied by the electron, and another possibility is this state is empty of electron, right? So this state is occupied by electron. State is occupied by electron. Occupied by electron. Yeah, state is filled by electron, ऐसे भी होता है. And state is empty of electron. State is empty of electron. It is empty of electron. ये electron से empty है, ठीक. So whether it is occupied by the electron or it is empty of electron. So you have only two possibilities. Now if you have two possibilities, it means you have random variable. If you have random variable, then you can use the concept of probability. So we would be talking in terms of probability. Basically we would be trying to develop a probability function, right? So that function is known as Fermi direct statistic. The particles which follow Fermi direct statistic, they are known as fermions, right? ये भी एक बार engineering services में पूछा गया है. So the particles which follow Fermi direct statistic, they are known as fermions. So electrons and holes, these all are nothing but the fermions. Right. So what does this statistic says? It statistic says that कि f of e is equal to 1 upon 1 plus e to the power e minus ef divided by kt. Right. क्या है ये सारे टर्म्स जरा देखते हैं. This is your Fermi direct statistic. This function f is known as Fermi function. It is known as Fermi function. इसे हम लोग Fermi function कहते हैं, ठीक. आइए जरा यहां सारे टर्म्स की बात करते हैं. इट इज वेरी इंपॉर्टेंट रिलेशन. सेवरल न्यूमेरिकल प्रॉब्लम्स कैन बी फॉर्म्ड ऑन दिस. व्हाट इज दिस f ऑफ e? दिस इज, it gives us probability of finding an electron at energy state E at temperature T Kelvin. So it gives probability of finding an electron at energy state E at temperature T Kelvin. So here the temperature is in Kelvin. Please keep in mind. So now what we have defined? We have defined Fe. Fe is probability of finding an electron at energy state E. So E is energy state and T is temperature. So किसी temperature T पर किसी energy state E पर energy of electron. So क्या बचा अभी? EF बचा and K. K is known as Boltzmann constant. This K is Boltzmann constant. It is Boltzmann's constant. It is Boltzmann constant. This K is nothing but 1.38 into 10 to the power minus 23 joule per Kelvin. But in our subject we don't use joule per Kelvin. मतलब we generally do not use. We can use, इसमें कोई problem नहीं. We use the unit of energy, that is electron volt. So if you convert this into electron volt, how much value we are going to get? 8.62 into 10 raised power minus 5. So 8.62 into 10 raised power minus 5 electron volt per Kelvin. Right? You should be knowing both of these relations because अगर जूल में एनर्जी दी हुई है तो you will be using this. अगर एनर्जी इलेक्ट्रॉन वोल्ट में है you will be using this. The most important parameter is EF. What is EF? EF is known as Fermi energy level. It is known as Fermi energy level. इसे हम लोग नाम देंगे Fermi energy level. So let's go for this. Fermi डायरेक्ट स्टैटिस्टिक. पहले ये इक्वेशन देख लीजिए, देन इसके फर्मी लेवल की बात करेंगे, फर्मी एनर्जी लेवल. What is Fermi energy level? We would be talking. So I can define Fermi energy level in two ways. Let's go for definition of Fermi energy level. Fermi energy level. If I talk about at T is equal to 0 Kelvin, at T is equal to 0 Kelvin. So at T is equal to 0 Kelvin, it will be, you see, KT will become 0. So if E minus EF is non-zero, then non-zero by 0, that is infinity. But if E minus EF is positive, then plus infinity, and if E minus EF is negative, then minus infinity. So you will have two different cases, but I am not going to solve each and everything. So I can write it, EF is that energy level below which all the energy states are occupied by the electrons, and above which all the energy levels are empty of electrons. All the energy levels are empty of electrons. Below which all the energy states are occupied by the electrons, and above which all the energy states are empty of electron. And pictorially you can see, okay, let us suppose this is our band diagram, right? So in band diagram, this is valence band and this is conduction band. So you have lots of energy states here in valence band and here in conduction band. You don't have any energy state in the forbidden gap, but EF can be in the gap. EF is just a concept, it's not actual energy state, right? So it is just a theoretical concept. So let us suppose it is EF. So now if you are at 0 Kelvin, at T is equal to 0 Kelvin, so below the EF, whatever energy states, so these energy states are below the EF, so all these energy states are occupied by the electrons. So all these states are filled, right? And if you go beyond this, so all these energy states should be empty. So these energy states are empty. Above EF, all these energy states are empty. So at 0 Kelvin, all the energy states below EF are occupied by the electrons, and all the energy states above EF are empty of the electron. You should be knowing this, important concept है. Now, अगर मैं EF पर बात करूं कि what is the probability of finding an electron at EF, so जरा एक ग्राफ की मदद लीजिए. You see here, this is F of E, right, and this is E, right? So we are somewhere here. This is our EF. If I say we are wanting to draw a graph for T is equal to 0 Kelvin, Fe versus E. So if we are below EF, this entire range is what? E less than EF. So if we are below EF, all the states are occupied by the electron. It means probability of finding an electron at any state is what? 1. So this is 1. Up to this point we have 1, right? Now if I go above this, let us suppose I am going here, this is E greater than EF. So for E greater than EF, all the energy states are empty. All the energy states are empty means probability of finding an electron is 0. So probability of finding an electron is 0. So 0 means it would be like this. It would be like this, right? So this graph is what? Discontinuous. It is discontinuous at x is equal to 0. There is a sharp discontinuity. So for a graph which is discontinuous as x is equal to 0, x is equal to EF कह लीजिए आप. So how can you find the value at x is equal to EF? Take the average of these two values. So if I want to get the probability of finding an electron at EF, FEF, it would be before this 1, after this 0, divided by 2 because we are taking average, so 1 by 2. So probability of finding an electron at Fermi energy level is 1 by 2. Probability of finding an electron, probability of finding an electron at EF is 0.5 या 50%. This we have seen everything at T is equal to 0 Kelvin, right? Now let us suppose we talk about at non-zero temperature. So at non-zero temperature, T does not equal to 0 Kelvin. So at T does not equal to 0 Kelvin, if you see at E is equal to EF, if I write this equation, so FEF we can write 1 upon 1 plus e to the power EF minus EF upon KT. Now KT is non-zero, K is non-zero, T is non-zero, so KT is non-zero. So this term will remain non-zero. Now EF minus EF is 0. 0 by non-zero is 0. So e to the power 0 is 1. So this entire term will become 1. So it is 1 by 2, that is 0.5. So at any non-zero temperature, EF would be that energy level at which probability of finding electron is 0.5. But you see, my dear friend, what happens practically? Practically what happens at non-zero temperature, some electrons are moving from here to here, right? Some electrons are moving from here to here. So above EF few states would be occupied by the electron and below EF few states would be empty of the electrons. So we should have a representation for this thing. So what happens, let us suppose we want to show this. So हमारे पास कुछ ऐसा हो जाएगा. मैं उसकी मैथ में नहीं जा रहा हूँ, क्लास में बहुत डेप्थ में हम लोग इसकी मैथमेटिक्स करते हैं. This is 0.5, this is 0.5, this is 1, this is 0. So this graph we have drawn for T is equal to 0 Kelvin. Let us suppose we go for some temperature T1. So for some temperature T1, what will happen? Initially it would be 1, then the probability will keep on decreasing, and at EF it will become 0.5. Then it will go like this, and then finally it will become almost 0, like this, right? It is at any temperature T1. T1 is non-zero temperature. Dear friends, you see, what does this indicate? This indicates 1 minus Fe. You see, this is representing 1 minus Fe. So if Fe is the probability of being filled, then 1 minus Fe is probability of being empty. So some of the states below EF are empty of the electron, and this denotes some of states are filled above this. Above EF, some of the states are occupied by the electron. Now if you increase the temperature, what will happen? Some more electrons will be going for the high energy states, so some more states would be empty. So if you are increasing the temperature, it is going something like this. So it goes like this, some more states will become empty, right? And some more states will become filled, so it is going like this. So it is at temperature T2, and obviously T2 is greater than T1, right? बाकी इसकी डेप्थ क्लास में काफी कुछ किया गया है, अभी बस इतना ही जानना आपके लिए काफी. This is all about the concept of Fermi energy level at various temperatures and the graph of Fe versus E versus temperature, right? You see, immediately take the pic of this, take the picture of this. अर्थ में क्वाजी फर्मी लेवल की बात करूंगा. सर फॉर गेट एग्जाम ये सारे कांस्टेंट्स की वैल्यू याद होनी चाहिए, अनय शुक्ला कह रहे हैं. अनय बेटा अनय शुक्ला कह रहे हैं कि गेट के लिए ये सारे नहीं, लेकिन कुछ कांस्टेंट जैसे के और एच या एप्सिलॉन नॉट, ये 3-4 तो ऐसे हैं जो याद रहने चाहिए। एक इलेक्ट्रॉनिक्स इंजीनियर इनको अफोर्ड नहीं कर सकता कि ना याद रहें। देन मुदित पूछ रहे हैं कि कामेश सर नहीं लेंगे क्या मैराथन? सर कामेश सर भी इस मैराथन में नहीं, बेटा सेशन पूरा मैं ही ले रहा हूँ, ठीक है। और एक टीचर सफिशिएंट है रिवाइज कराने के लिए, उसमें 2-2 लोग रिवाइज करा करके क्या करेंगे? सो आई एम टेकिंग द एंटायर सेशन, ठीक। रिवीजन ही तो करना है इसमें, तो 2 लोगों की जरूरत तो नहीं फील किया गया, राइट। सो रिप्लाइड मुदित योर क्वेरी आल्सो। प्रांजल अभी बीजेटी तक पहुंचने दीजिए। आइए, सो प्रोबेबिलिटी ऑफ फाइंडिंग अ होल अगर आपसे कोई पूछे तो क्या हो जाएगा, देखिए जरा। प्रोबेबिलिटी ऑफ फाइंडिंग अ होल एट एनर्जी स्टेट E at T Kelvin. So it will become 1 minus f of E. F of E is the probability of finding an electron. So 1 minus f of E is be the probability of finding absence of electron. Absence of electron is nothing but hole. So probability of finding a hole is like this. If you want to solve this, sometimes it would be required. So you can do like this: 1 upon 1 plus e to the power E minus EF upon KT, right? So if you solve this, it becomes out as 1 plus e to the power E minus EF upon KT minus 1 divided by 1 upon 1 plus E minus EF divided by KT. माइनस माइनस कट जाएगा, ये कॉमन लेकर के आप सिंप्लीफाई करेंगे। सो इट इज 1 upon 1 plus e to the power minus E minus EF divided by KT. दिस इज द प्रोबेबिलिटी फाइंडिंग अ होल, ठीक। तो अगर आपसे होल की प्रोबेबिलिटी पूछा जाए, आप डायरेक्टली इस रिलेशन को यूज कर सकते हैं, राइट। शैल वी गो अहेड? Two point here we are going to discuss that is very important. That is Boltzmann approximation, right? So Boltzmann approximation of Fe and Boltzmann approximation of 1 minus Fe. 1 minus Fe is this, right? This is what 1 minus Fe, and Fe we have written. So first point is, if E minus Ef is greater than Kt. We are taking a condition where E minus Ef is greater than Kt. How much greater? E minus Ef is at least 3 times greater than Kt. Then f of E approaches, Boltzmann term. Then f of E approaches Boltzmann term, right? So you see, dear friends, what happens if you write f of E is equal to 1 upon 1 plus e to the power E minus Ef upon Kt. If E minus Ef is very large as comparison to Kt, this term would be very high as comparison to 1. If it is very high as comparison to 1, 1 can be neglected, and this can be written as 1 upon e to the power E minus Ef upon Kt. So we can write it as f of E is approximately e to the power minus E minus Ef divided by Kt. This is your Fe. It is Boltzmann approximation. This is known as Boltzmann approximation. Boltzmann's approximation of Fe, and this approximation is valid only if E minus Ef is greater than at least 3 times Kt. 3 गुना KT से ज्यादा हो तभी आप इसे अप्लाई कर सकते हैं, अदरवाइज आप अप्लाई नहीं कर सकते हैं। सिमिलरली अगर मैं कहूं कि EF माइनस E, सो इफ EF माइनस E इज ग्रेटर देन KT, या दूसरे शब्दों में EF माइनस E इज at least 3 times greater than KT, then 1 minus Fe approaches to Boltzmann term, approaches to Boltzmann term, Boltzmann's term, या Boltzmann approximation, जो भी लिखना चाहे. So it comes out as 1 minus Fe we have written like this. It was written as 1 upon 1 plus e to the power minus E minus EF upon KT, which you can write 1 upon 1 plus e to the power, ये minus से multiply कर दो, EF minus E upon KT. So if you see, now this term would be very large as comparison to 1, so this can be neglected and you can write it as 1 minus F of E. This is approximately equal to, इसको ऊपर लेकर के चले जाइए, माइनस EF minus E upon KT. This is your 1 minus Fe. This is Boltzmann approximation. This is Boltzmann's approximation, and this Boltzmann approximation is valid only if EF minus E is at least 3 times greater than KT, otherwise ये valid नहीं होगा. So these are the few important points related with the Fermi function. You please note down this. किसी ने क्वाजी फर्मी एनर्जी लेवल का कंसेप्ट पूछा है. मैं जब लाइट इंसिडेंट कराऊंगा सेमीकंडक्टर पर तो उस समय याद दिलाना, तो क्वाजी फर्मी लेवल डिस्कस कर लूंगा. हालांकि उससे गेट में कभी कोई क्वेश्चन नहीं पूछा गया. When I will put light on the semiconductor, then you please remind me and I will discuss quasi Fermi level. सिर्फ आपको जानने के लिए, जानकारी के लिए. That's not important for the exam. That never has been asked in gate. Shall we go ahead? Right. आगे चलते हैं. Now next concept जो मैं डिस्कस करना चाहता हूं, that is density of states. Density of states. Density of states, popularly known as DOS. What is this? It refers to the number of states per unit volume per unit energy. It refers to the number of states per unit volume per unit energy. States are nothing but the solution of Schrodinger wave equation. States are solution of Schrodinger equation. अब Schrodinger equation वगैरह क्या है यहां भी उसकी बात नहीं करेंगे, ठीक है. So these are nothing but the solution of Schrodinger equation. If I calculate these states for the semiconductor material, I am directly writing the formula, not interested in the derivation. So this is represented as a function of energy. So number of states per unit volume per unit energy as a function of energy can be represented as n of E से represent कर रहे हैं. This is represented as 4 pi 2 mn star to the power 3 by 2 upon h cube into root E minus EC. This is for conduction band. So conduction band is from EC to infinity. So it is EC to infinity, right? In valence band, this can be represented like this. In valence band it can be represented like this, 4 pi mn की बजाय क्या हो जाएगा, होल का इफेक्टिव मास 2 mp स्टार to the power 3 by 2 upon h cube root here EB minus E, and this balance band starts from minus infinity and it is up to EB. ठीक, you know what are these EC and EB? This, you see the band diagram of the semiconductor. This is your valence band, so the top edge of valence band is EB. This is your conduction band, so the bottom edge of this is conduction band. If you are in this range, this is the forbidden gap. So in the gap you don't have any allowed energy states. So from EB to EC you are in the gap, and for that gap states are 0, right? So this is the formula for the density of states. Please write down this. In the forbidden gap you don't have any state. You see, if you want to draw the curve between energy E and density of state DOS, that is N of E. So this curve comes out something like this. This is your valence band, let us suppose EV, and this is your conduction band, let us suppose EC. So it is parabolic like this, and it is parabolic like this. So this is directly proportional to E minus EC, and this is directly proportional to EB minus E, right? Let's go for this, right? Density of states. दीपक क्या पूछ रहे हैं आप? At the room temperature, the density of state is on the order of 10 to the power 19 per centimeter cube in silicon. Silicon is our main material, semiconductor material. So in silicon semiconductor at room temperature, the density of states is on the order of 10 to the power 19 per centimeter cube at room temperature. Okay? Now, so we have done this density of state and all that. Now please let's try to write carrier concentration, charge carrier concentration, charge carrier concentration, charge carrier concentration. We have two types of charge carriers. This is our semiconductor. In semiconductor, if we are in valence band, this is EV, and if we are in conduction band, this is EC. So in valence band we are interested in holes, and conduction band we are interested in electrons, right? So I'm not going to derive, I'm directly writing these relationships. So this electron concentration, which is usually represented as small e, right? This is nothing but the number of electrons per unit volume in conduction band. Number of electrons per unit volume in conduction band, right? This electron concentration is given as N is equal to Nc e to the power Ec minus Ef upon kT. This is your electron concentration. Here we have a very important term, and that is Nc. Ec, you know, conduction band H, Ef Fermi energy level, K Boltzmann constant, T temperature. All these terms have been introduced, so मैं उनकी बात नहीं कर रहा हूँ. Nc is known as effective density of states in conduction band. Effective density of states in conduction band, right? Effective density of states in conduction band. This NC is given as 2 into 2 pi mn star kt upon h square to the power 3/2. सॉरी, इसकी वैल्यू डेंसिटी ऑफ स्टेट्स नहीं, इफेक्टिव डेंसिटी ऑफ स्टेट की वैल्यू 10 टू द पावर 19 पर सेंटीमीटर क्यूब होता है. मैंने गलती से डेंसिटी ऑफ स्टेट कह दिया था, सॉरी फॉर दैट. एक्चुअली डेंसिटी ऑफ स्टेट और इफेक्टिव डेंसिटी ऑफ स्टेट में अंतर समझिए. इफेक्टिव डेंसिटी ऑफ स्टेट इज नंबर ऑफ स्टेट्स पर यूनिट वॉल्यूम एट अ गिवन टेम्परेचर इन द कंडक्शन बैंड. If you are talking about NC, so NC is nothing but the number of states per unit volume in the conduction band at a given temperature, whereas density of states is number of states per unit volume per unit energy, right? So ये independent of energy, इसको हम क्या करें, entire conduction band में per unit volume कितनी number of states हैं at a given temperature, those are known as effective density of states. So this relation you have to remember. इसके basis पर questions हर एग्जाम में पूछे जाते हैं, गेट में भी, इंजीनियरिंग सर्विसेज में भी, एवरीवेयर. 2 is equal NC is equal to 2 pi mn star kt upon h square, where mn star is effective mass of electron, k Boltzmann constant, T temperature, h Planck's constant, NC is effective density of states in conduction band. This is your electron concentration. Please take the pic of this, then we would be moving for the hole concentration immediately. Very important relation. दीपक सिंह, हेलो, क्या पूछ रहे हैं दीपक जी? Shall we go ahead? Good. Hole concentration. Let's move on for the hole concentration. So if I talk about hole concentration, it goes like this: hole concentration, hole concentration. It is represented as P, and this is number of holes per unit volume, number of holes per unit volume, in valence band. Number of holes per unit volume in valence band. Now you see, dear friends, this is given as P is equal to NV e to the power minus EF minus EB upon KT. You know all these terms. EF is Fermi energy level, EB is valence band edge, top edge of the valence band, K Boltzmann constant, T temperature. The new term is NB. This NB is effective density of states in valence band. Effective density of states in valence band. Effective density of states in valence band. So if I talk about NB, this NB becomes equal to 2 into 2 pi mp star kt upon h square to the power 3/2. Please remember this relation, it is important, and you may get questions on this also. 2 into 2 pi mp star kt upon h square to the power 3/2. So this is your hole concentration. So we have discussed a hole concentration and electron concentration relationship. Now move on to the next. कुछ लिखते भी रहिए आप लोग. अंकित कुमार, आई डोंट थिंक ऐसा कोई क्वेश्चन. आप मुझे क्वेश्चन भेजिएगा, क्योंकि यदि आपसे 2 डिस्क्रीट स्टेट्स के बीच का डिफरेंस पूछा जा रहा है, देन यू हैव टू सॉल्व श्रोडिंगर इक्वेशन इन टर्म्स ऑफ n, दैट इज द प्रिंसिपल क्वांटम नंबर, एंड दैट प्रिंसिपल क्वांटम नंबर में आप 2 डिफरेंस करके एंड देन यू कैन कैलकुलेट दैट डिफरेंस. सो आई डोंट थिंक ऐसा क्वेश्चन पूछा जाएगा, क्योंकि सोल्यूशन ऑफ श्रोडिंगर वेव इक्वेशन इज नॉट इन आवर सिलेबस. हमारे सिलेबस में उससे जुड़े हुए क्वेश्चन नहीं पूछे जाते हैं. ठीक है, तो आप मुझे क्वेश्चन भेजिएगा. हो सकता है किसी और चीज से रिलेटेड हो और आप ना समझ पाए हो. अंकित, लेट्स मूव ऑन टू द नेक्स्ट कंसेप्ट. I would like to put one more important thing here, that is NB upon NC. what is NB upon NC? You see 2 into 2 pi mn star kt upon h square to the power 3 by 2 divided by 2 into 2 pi mp star kt upon h square to the power 3 by 2. You see 2 cancel, this 2 pi cancel, kt cancel, h square cancel. So this relation comes out as NB upon NC. This comes out as mn star to the power mp star to the mn upon mp star to the power 3 by 2. This should be the relationship. ये हमारे पास रिलेशनशिप हो जाएगी. NB upon NC is equal to this. इसकी जरूरत लगती है हमें गेट के कुछ क्वेश्चंस में. We would be requiring this, so let's discuss this. Move on to the next. Next one is intrinsic semiconductor. I want to discuss all these relationships for intrinsic semiconductor. So intrinsic semiconductor. We know that in intrinsic semiconductor N is equal to P is equal to Ni. First relation. Number of electrons per unit volume is equal to number of holes per unit volume, and that is known as intrinsic charge carrier concentration. This Ni is known as intrinsic charge carrier concentration. This is known as intrinsic charge carrier concentration, Ni. Now you see, dear friends, what happened. If I want to calculate this Ni, I will put those relations and then multiply and then try to calculate. So this comes out as Ni square comes out as Nc Nv e to the power minus Eg upon Kt, which you can write Ni is equal to root Nc Nv e to the power minus Eg upon 2 Kt. This is your intrinsic charge carrier concentration. But here Nc and Nb are function of temperature as well as Eg is also function of temperature. So you should be putting these values in terms of temperature as well. So अगर मैं इसको solve करूँ further, so I will have Ni square is equal to A naught, a material constant, T cube e to the power minus Eg naught upon Kt, which can be written as Ni root A naught T to the power 3 by 2 e to the power minus Eg naught upon 2 Kt. This is the value of Ni. What are these terms here? A naught is a material constant which is independent of temperature. It will be different for different materials, but for a particular material its value is constant with respect to temperature. It is independent of temperature. So A naught is material constant. It is material constant. And what is Eg naught? Eg naught I have already defined, energy band gap at 0 Kelvin. Energy band gap at 0 Kelvin. Band gap at 0 Kelvin. So dear friends, if you see Eg naught is also constant for a particular material. Let us suppose you talk about silicon. So for silicon its value is 1.21 electron volt. Or you talk about germanium. So for germanium its value is 0.785 electron volt. So this value is also constant. So from this expression what we can conclude, this is constant, this is constant, this is constant. So Ni is purely a function of temperature. For a particular material Ni is function of temperature, and that too a non-linear function of temperature. So with increase in temperature the value of Ni will increase. Material to material it will depend upon band gap also. If you compare two different materials, let us suppose you compare silicon and germanium, then it is function of band gap also. But in a particular material, let us suppose I talk about silicon. So in silicon it is the function of only temperature. In a particular material it is a function of temperature only, right? So इस पर बेसिस एक क्वेश्चन गेट में पूछा गया है, बहुत पहले पूछा गया था, सो मैंने सोचा कि वो भी आपके सामने क्लियर हो जाए. लेट अस सपोज राइट डाउन दिस प्लीज. Go for the next topic. The typical values for Ni at room temperature, अगर आप सिलिकॉन के लिए बात करें तो it is 1.5 into 10 to the power 10 per centimeter cube, और अगर जर्मेनियम के लिए बात करें तो it is roughly around 2.4 into 10 to the power 13 per centimeter cube. So typical values of Ni at T is equal to 300 Kelvin. Typical values, these are not the value. ये अगर एग्जाम में दी नहीं है तो आप यूज नहीं करेंगे इन्हें. Ni is 1.5 into 10 to the power 10 per centimeter cube. ये सिलिकॉन के लिए है, फॉर सिलिकॉन, एंड Ni इज इक्वल टू 2.4 इंटू 10 टू द पावर 13, 2.4 इंटू 10 टू द पावर 13 पर सेंटीमीटर क्यूब फॉर जर्मेनियम के लिए है, राइट. आप देखें जैसे बैंड गैप बढ़ रहा, बैंड गैप कम हो रहा है तो Ni की वैल्यू बढ़ रही है. सो मटेरियल टू मटेरियल इट विल बी द फंक्शन ऑफ बैंड गैप एज वेल. But in a particular material, since Eg naught is constant, so in a particular material it is purely function of temperature. I hope that is clear to you. Let us move on to the next concept. Intrinsic Fermi energy level. Let's talk about intrinsic Fermi energy level. It is the position of Fermi energy level in intrinsic semiconductor. So intrinsic Fermi energy level, usually denoted as EI or sometimes EFI. EI or sometimes EFI. So the position of Fermi energy level in an intrinsic semiconductor is known as intrinsic Fermi energy level. So this intrinsic Fermi energy level is calculated as EI is equal to, it is calculated as EC plus EB, EC plus EB divided by 2 plus KT by 2 ln NB upon NC. All these terms you know very well. EC plus EB divided by 2 plus KT by 2 ln NB upon NC. This EC plus EB by 2 is nothing but E mid gap. So it is mid gap energy level plus KT by 2 upon ln NB upon NC, right. So this is the another version of this relation. Just few moments before you have seen NB upon NC is equal to MP star upon Mn star to the power 3 by 2. So if I put this here, then this will become MP star upon Mn star power to the power 3 by 2. 3 by 2 will be multiplied, so it will be 3 by 4. So it is E mid gap. It is E mid gap plus 3 by 4 ln MP star upon Mn star. If you go for the PYQ, previous year question bank, then you will find several questions on this relationship. इनमें से किसी पर भी आपको तमाम सारे क्वेश्चन मिल सकते हैं. Here E mid gap is nothing but EC plus EB by 2. So E mid gap is E mid gap, this is equal to EC plus EB by 2. This is equal to EC plus EB by 2. Please go for this. आप लोग हैं? Please respond. Good. Very good. Now few terms, few more things we would be discussing, then we would be returning for the Fermi energy level in extrinsic semiconductors as well. So the first thing which I want to discuss is mass action law. Mass action law. What is this? This is nothing but N into P is equal to Ni square, which is constant at constant temperature. Product of electron and hole concentration is equal to the इंट्रिंसिक कैरियर कंसंट्रेशन का स्क्वायर ऑफ इंट्रिंसिक कैरियर कंसंट्रेशन, एंड इंट्रिंसिक कैरियर कंसंट्रेशन इज अ फंक्शन ऑफ टेम्परेचर, सो एट अ कांस्टेंट टेम्परेचर इट्स वैल्यू वुड बी कांस्टेंट. व्हाट इज द प्रॉब्लम विथ दिस रिलेशनशिप? You should know valid only under thermal equilibrium condition. Thermal equilibrium condition. Please keep in mind it is not valid in non-equilibrium condition. It is valid only under equilibrium condition. ये सिर्फ इक्विलिब्रियम की कंडीशन में वैलिड है. ये बहुत इंपॉर्टेंट पॉइंट है. यू कैन नॉट यूज दिस रिलेशन इन नॉन इक्विलिब्रियम. कल परसों किसी ने ग्रुप पर मुझसे क्वेश्चन पूछा था कि सर यहाँ पर अप्लाई नहीं हो रहा है, इट इज वायलेटिंग मास एक्शन लॉ. हाउ? So actually the question was related when light was putting on the material, and when light falls on the material then it goes to the non-equilibrium condition. So it's not valid in non-equilibrium condition, it is valid only in equilibrium condition. The second most important point is it is not applicable for degenerate semiconductors. It is not applicable for degenerate semiconductors. ये degenerate semiconductors के लिए भी applicable नहीं है. It is not applicable for degenerate semiconductor. So it is applicable only for the non-degenerate semiconductor. Intrinsic के लिए तो valid ही रहेगा, और intrinsic के साथ साथ non-degenerate के लिए valid रहेगा. So you will be using this only for non-degenerate semiconductors. Non-degenerate semiconductors. Non-degenerate semiconductors के अलावा आप किसी अन्य सेमीकंडक्टर के लिए इसका यूज नहीं करेंगे. ठीक है? It is valid only for the non-degenerate semiconductors. This is mass action law. Mass action law के दो पॉइंट आप ध्यान रखेंगे. पहला, it is applicable only for under equilibrium condition. Second point, it is applicable only for the non-degenerate semiconductor. It is not valid for the degenerate semiconductor. I have already told you degenerate means heavily doped semiconductor and non-degenerate means moderately doped semiconductor. Valid for the lightly doped also, because lightly doped are nothing intrinsic. Intrinsic के लिए Ni into Ni is equal to Ni square. Now next point of which I would like to discuss is that is compensated semiconductor. Compensated semiconductor. This is the next point, that is compensated semiconductor. Both types of impurities are added into same region of semiconductor. Both types of impurities are added into same region of semiconductor. Semiconductor के same piece में you are adding both types of impurities. Both types of impurities are added into same region of semiconductor. Means you have this semiconductor, right? And in this semiconductor you are adding donors as well as you are adding acceptors. Then such resulting semiconductor is known as compensated semiconductor. So the compensated semiconductor is one which have both types of impurities, acceptors as well as donors simultaneously. Such semiconductors is known as compensated semiconductor. Nehal Bhardwaj is saying today's target is GATE examination. दीपक कह रहे हैं गेट का एग्जाम कैसे निकालें? PYQ से हो जाएगा. अगर PYQ हो जाए तो गेट एग्जाम हो जाएगा. अच्छे से प्रीवियस ईयर क्वेश्चन बैंक आप कर लीजिए तो गेट एग्जाम अच्छा होगा, क्योंकि क्वेश्चन तो 70-80% क्वेश्चन तो एज इट इज जैसा प्रीवियस ईयर में आते हैं उसी तरह से आते हैं. ठीक. नेक्स्ट पॉइंट. नाउ यू सी, लेट अस सपोज Na is acceptor concentration. Concentration means you know number of acceptors per unit volume, so it is acceptor concentration. Then if I talk about Nd, so Nd is donor concentration, so it is donor concentration, right? You know my dear friends, N is free electron concentration, या electron concentration, number of electrons per unit volume. in the semiconductors, and P is hole concentration. Hole concentration. No matter whatever impurity you are adding, overall semiconductor will remain electrically neutral. So that is known as compensation principle. So you can say overall semiconductor is electrically neutral, overall semiconductor is electrically neutral. If overall semiconductor is electrically neutral, then we will have total positive charge per unit volume, Very important principle to solve several questions. Total positive charge per unit volume, it should be equal to total negative charge per unit volume. Total negative charge per unit volume. Then the semiconductor would be neutral. What would be total positive charge? It is P plus donors has given their electron and they have become positive, and N electron plus acceptors has taken electron, so they have become negative. This is known as charge compensation principle या charge neutrality principle. Charge compensation या charge neutrality principle. Charge compensation या charge neutrality principle. This is charge compensation या charge neutrality principle. Please do this. Very important. फोर फेब, अब तो टाइम भी कम है, कैसे हो पाएगा? अब अगर अभी तक कुछ नहीं किया है तो अब क्या हो पाएगा? ठीक है, 10 दिन में मैं झूठी दिलासा दूं, ठीक नहीं है। अगर आप पहले से कुछ अच्छा पढ़े हैं तब कुछ होगा। अभी बस इतना कर सकते हैं कि 10 दिन में 1 या 2 सब्जेक्ट कोई पकड़ लीजिए और उन्हीं 1-2 सब्जेक्ट में जितना कुछ कर पाइए उतना करिए। एंड क्योंकि पूरे साल भर नहीं पढ़े हैं तो बहुत ज़्यादा एक्सपेक्टेशन रखना भी खुद से ठीक नहीं है। ठीक, तो 10 दिन में 1-2 सब्जेक्ट में से जितना 10-15 नंबर स्कोर कर सकें उतना करिए। Done. Let's go ahead. Move on to the next. Let us suppose I talk about N-type semiconductor, which is compensated. So we have 3 possibilities basically. If Na is greater than Nd, then compensated P-type semiconductor. Then compensated P-type semiconductor. P-type semiconductor. And if Nd is greater than Na, then compensated N-type semiconductor. Then it is compensated N-type semiconductor. It is compensated N-type semiconductor. And if Na is equal to Nd, then fully compensated semiconductor having characteristics like intrinsic semiconductor, having characteristics like intrinsic semiconductor, having characteristics like intrinsic semiconductor. It is not intrinsic because you have added the impurities, and once impurities are added then it will not remain intrinsic, but its character will be like intrinsic semiconductor because it is fully compensated. So number of electrons will be equal to the number of holes, and that happens in intrinsic semiconductor. So from charge carrier point of view, if you see, it is just like intrinsic semiconductor. Now I am talking about N-type and P-type one by one. So let us suppose आपको screenshot लेना होगा. Please take the screenshot immediately. Please do it quickly. जोश धीरे धीरे हल्का हो रहा है आप लोगों का, और हमारा जोश आप पे डिपेंड करता है। यदि आपकी एनर्जी कम हो गई तो मेरी तो ऑटोमेटिकली खत्म हो जाएगी। अनय शुक्ला जी कह रहे हैं सर अभी फुल एनर्जी है। गुड, सो कीप कंटिन्यू विद दिस एनर्जी। आगे चलते हैं। Now let us suppose I talk about n-type semiconductor. So if I talk about n-type semiconductor, so in n-type semiconductor what will happen? Let's summarize all the relationships here for n-type semiconductor. For n-type semiconductor, if it is compensated semiconductor, then Nd must be greater than Na. Now you see we have two relations, Np is equal to Ni square, this is one relation, and P plus Nd is equal to N plus Na, this is another relation, right? From this relation, from this equation 1, P is equal to Ni square can be put into this relation. So if I put this, it comes out as Ni square upon N plus Nd is equal to N plus Na, and hence it can be written as a quadratic equation N square minus Nd minus Na into N minus Ni square is equal to 0. This is a quadratic equation in N, right? If you solve this quadratic equation to get the value of N, then you will have N is equal to Nd minus Na, right? Plus minus, I am discarding the minus sign, why that I have mentioned in the class, not interested here to mention, Nd minus Na ka square plus 4 Ni square divided by 2a. So you can write it as N is equal to Nd minus Na by 2 plus under root, this becomes Nd minus Na by 2 ka square plus Ni square. This is the standard relationship to calculate electron concentration in a compensated semiconductor, compensated n-type semiconductor, right? But for most of the cases, this Nd minus Na would be very large as comparison to the Ni. So if Nd minus Na is far greater than Ni, that you have to compare from the numerical values given. So if this is applicable, then this term would be very large as comparison to this term. So Ni square can be neglected, this root N square will cancel, this will get added. So N is approximately equal to Nd minus Na. But please, this relation is approximation, and this approximation is valid only if Nd minus Na is greater than Ni. So you have to compare this effective doping greater than Ni. If you compare this Ni and this relation is satisfied, then you can use this. If let us suppose both are comparable, both are almost same, let us suppose it is 10 to the power 13, it is also 10 to the power 13, then you cannot use this, then you have to use this, right? So while using this, be cautious. ऐसा नहीं कि blindly use कर लेंगे, कई बार एग्जाम में इस बात का यूज कर लेते हैं कि आप इस कंसेप्ट को जानते हैं नहीं जानते और उसके अकॉर्डिंग क्वेश्चन फ्रेम कर देते हैं. Let us suppose if I say acceptor impurity is 0, if Na is 0, right? Yani it is non-compensated n-type semiconductor, only donors are added. So you can say only donors are added, only donors are added. So if only donors are added, then you will have what? Then you will have N is equal to Nd by 2 plus under root Nd by 2 ka square plus Ni square. Right? This is where we are considering donors only, right? Let us suppose donor concentration is Nd is far greater than Ni, If this condition satisfies, then Ni square can be neglected and N is approximately equal to Nd. Please be cautious. This is valid only if Nd is greater than Ni. If that is not true, then you cannot use this. You have to use this. So this is electron concentration. If you have calculate hole concentration, so calculate electron concentration with any method, and then hole would be Ni square. Then whole will be equal to Ni square divided by Nd. Whole up Ni square divided by N. N इनमें से किसी रिलेशन से कैलकुलेट करिए एंड Ni square by N आप ऐसे कर सकते हैं. ठीक. Now I want to calculate the position of Fermi energy level in N-type semiconductor. So how can we calculate position of Fermi energy level? N is equal to Nc e to the power minus Ec minus Ef upon Kt. So I will have e to the power Ec minus Ef upon Kt is equal to Nc by N, and from this we can have Ec minus Ef is equal to Kt ln Nc upon N. This is one relation. N value you can put from above calculation, जो पीछे हमने calculation किया है. N can be approximately equal to Nd, or N can be approximately equal to Nd minus Na. Whatever is the case, accordingly you can put the value of N. Dear friends, one more thing which you need to know. N can also be written as N is equal to Ni e to the power Ef minus Ei upon Kt. This is also a very important relationship. Ni के टर्म में अगर आप देखना चाहें, here Ef is the Fermi energy level of N-type semiconductor and Ei is the Fermi energy level of intrinsic semiconductor. So Ef minus Ei denotes the difference between the Fermi energy level of N-type semiconductor and intrinsic semiconductor, and I is intrinsic carrier concentration. So from this, if I want to solve, then Ef minus Ei is equal to Kt ln N upon Ni. Right. The value of N can be equal to Nd minus Na, or it can be equal to Nd, depending upon the approximation and depending upon the case whether it is compensated or non-compensated semiconductor. So you can put all these values. Now here few terms, if you increase the temperature, then Fermi energy level is going towards the intrinsic Fermi energy level. So it is moving away from the conduction band and going towards the intrinsic Fermi energy level. If you are increasing the doping concentration, then it moves towards the conduction band edge. Those all things you can verify from these relationships. So उनसे गेट में डायरेक्टली क्वेश्चन कुछ नहीं बनने वाला है. So I am not going to discuss all those things. लेकिन आप इन रिलेशन से देख सकते हैं. This is all about N type semiconductor. सब कुछ समराइज हो गया N type के लिए. P type के लिए अभी ऐसे ही देख लेंगे. Please start taking the screenshot. अनय शुक्ला कह रहे हैं कि सर मेडी जी की टेस्ट सीरीज में ईडीसी के क्वेश्चंस थोड़ा अच्छे लेवल के होते हैं, क्या पीआईक्यू इजीली हो जाता है? टेस्ट सीरीज में कुछ क्वेश्चंस में फंस जाते हैं. जानबूझ करके थोड़ा सा लेवल ऊपर रखा जाता है ताकि जो क्लास में आप कर चुके हैं, पीआईक्यू कर चुके हैं, वो तो चीज़ें आप बहुत कंफर्टेबल हो ही गए हैं, तो थोड़ा सा उससे एक स्टेप ऊपर जा करके चीज़ों को प्रयास करें, तो उससे डिमोटिवेट नहीं होना है. दैट इज एक्चुअली द एवरीथिंग इज कॉम्प्रिहेंसिव, एक दूसरे को कॉम्प्लीमेंट करने के लिए है कि कुछ चीज़ें जो समय की सीमा की वजह से क्लास में नहीं डिस्कस हो पाती है वो टेस्ट सीरीज के थ्रू पुट करने का प्रयास किया जाता है. सो रादर देन बीइंग डिमोटिवेटेड, लेट्स ट्राई टू लर्न फ्रॉम टेस्ट सीरीज क्वेश्चंस फ्रॉम अदर, या कई बार मैं अलग से क्वेश्चंस प्रोवाइड करता हूं, तो उन सब चीजों से लर्न करने की कोशिश करिए. बाकी थोड़ा सा डेप्थ में क्वेश्चन जानबूझ करके रखे जाते हैं, खासतौर पर जो एडवांस लेवल टेस्ट होते हैं उसमें विलिंगली वी ट्राई टू पुट अ लिटिल बिट good questions, sometimes conceptually, yeah, sometimes calculative. Sonam, it's good marks, you need not to worry, just maintain it. सर मेडी जी कोर्स ले लेना के लिए कोई कोड है क्या? नहीं बेटा, ऐसा कोई कोड वगैरह नहीं होता है यहाँ, ठीक है. आप वेबसाइट पर जाकर के डिटेल्स देख सकते हैं www.medigi.in पर. Now Now let's repeat everything for the p type semiconductor, क्योंकि जरूरी नहीं है कि क्वेश्चन n से ही पूछा जाए, p से भी पूछा जा सकता है. So now it's very good mark. If you are consistently getting this marks in test series, it is good marks. Just maintain it. Try to overcome the silly mistakes. Conceptually आप फिर ठीक हैं, थोड़ा सा silly mistakes को भी जो calculation error वगैरह हो रही हैं उनको overcome कर लेंगे तो 5-6 नंबर और बढ़ जाएंगे. Move on to the next, p-type semiconductor. Let us suppose if I talk about p-type semiconductor, then what will happen? P-type semiconductor. So p-type semiconductor. If I talk about p-type semiconductor, it means acceptor concentration would be greater than the donor concentration, right? So we have again those two equations, Np is equal to Ni square. We have Np is equal to Ni square, and from here, this is equation 1. From here we can calculate N, which is Ni square upon P, and then we have another equation, P plus Nd is equal to N plus Na. This is our equation number 2. Let's put the value of N in this equation and try to make a quadratic equation. So P plus Nd is equal to Ni square upon P plus Na. So this will have P square minus Na minus Nd into P minus Ni square is equal to 0. If you solve this quadratic equation, you are going to get something like this. P is equal to Na minus Nd plus under root Na minus Nd square plus 4 Ni square divided by 2. I can write it like this also. P is equal to Na minus Nd divided by 2 plus under root Na minus Nd by 2 square plus Ni square, right? Now you see, dear friends, if Na minus Nd is greater than Ni, you must have to compare this. Then you can write P is approximately equal to Na minus Nd. इसे तभी यूज करेंगे जब ये कंडीशन सेटिस्फाई होगी, otherwise you are not going to use this, otherwise you are going to use this. So please be aware in the question, be careful in the question कि क्या दिया हुआ है उसके accordingly. If Nd is equal to 0, it means what? Only acceptors are added. Only acceptors are added. If only acceptors are added, then this relationship for P can be written as, this relationship for P becomes Na by 2 plus under root Na by 2 square plus Ni square. This is your P. This is the value of P, right? If Na is far greater than Ni, if Na is greater than Ni, then P is approximately equal to Na, right? So you know all these rules. Suppose you want to calculate electron concentration, then Ni square upon P, and P you can calculate from all these relationships and put that value, and you can calculate the whole concentration, sorry, electron concentration. Now let us suppose I want to calculate Fermi level. So position of Fermi level, P is equal to Nb e to the power minus Ef minus Eb upon Kt. So from this relation we will have Ef minus Eb is equal to Kt ln, and this is Nb upon P. This is Nb upon P. This is first relation. P value you can put from the relations which you have. P is approximately equal to Na, yeah, P is approximately equal to Na minus Nd, whatever is the case you can put accordingly. Now suppose I want to calculate P in terms of Ni, then P is equal to Ni e to the power Ei minus Ef upon Kt. So if I simplify this, it comes out as EI minus EF is equal to KT ln P upon Ni, right? P value you can calculate from the relations which we have discussed already. So from here you can calculate the difference of intrinsic Fermi level and Fermi level of the p-type semiconductor. Here you can calculate the difference of Fermi level in p-type semiconductor and valence band S. So both of these relationships can be used as per the case in the question. And please copy this from here, not copy, just take a screenshot, do it. नहीं ऐसा नहीं है अर्स की नहीं होते, मतलब थोड़ा डिफिकल्ट लगेंगे बट ऐसा नहीं है कि एकदम से नहीं होंगे, ठीक। और मैं ना टेस्ट का एनालिसिस का एक तरीका बताता हूँ. यू शुड सी द रिलेटिव रैंक. सो व्हाट एवर रैंक यू आर टारगेटिंग इन द फाइनल एग्जामिनेशन, इफ यू आर गेटिंग रैंक क्लोजर टू दैट, सो इसका मतलब आपका परफॉर्मेंस ठीक चल रहा है. क्योंकि अल्टीमेटली व्हाट मैटर्स, इफ द पेपर इज डिफिकल्ट, इट इज डिफिकल्ट फॉर एवरीवन, सो स्कोर विल कम डाउन एंड रिलेटिव रैंक विल रिमेन सेम. सपोज द पेपर इज इजी, देन इट इज इजी फॉर एवरीवन, सो स्कोर विल गो अप and score means marks will go up, but the rank will remain same. So ultimately what you need to compare is not how many marks you are getting, rather what is your relative rank. That is important. So try to improve your rank in test series, not the marks. So this is all about the position of Fermi energy level etc. कुछ इसमें छूटा हो, किसी को अगर कुछ याद आ रहा हो, कुछ और डिस्कस करना है तो बताइए, कर लेते हैं. अदरवाइज आई थिंक मेरी तरफ से इतना ही था फर्मी एनर्जी लेवल के कंसेप्ट में. सो वी हैव डिस्कस्ड एवरीथिंग रिलेटेड विद द फर्मी एनर्जी लेवल एंड चार्ज कैरियर कंसंट्रेशन. आई होप इफ आई डोंट फॉरगेट. अभिजीत क्या पूछना चाह रहे हैं? Whenever an electron meets with a hole, then recombination will take place. So obviously electrons will come down to the valence band, and when they come down to the valence band, they will meet with the hole and recombination will take place, because holes are in valence band, right? So recombination will always take place in valence band. असो क्वेश्चन यहां मैं नहीं करवाना चाह रहा हूं, इस पे क्वेश्चन स्ट्रेट फॉरवर्ड. अगर आप करना चाहते क्वेश्चन तो आई विल एडवाइज, लास्ट ईयर इन 2023 द क्वेश्चन ऑन दिस कंसेप्ट वाज गुड क्वेश्चन. ईसी माइनस ईएफ पर एक अच्छा क्वेश्चन दिया गया था. सो लास्ट ईयर द क्वेश्चन व्हिच वाज आस्क्ड इन गेट 23, प्लीज डू दैट क्वेश्चन. यू हैव टू यूज दिस रिलेशन एंड देन यू कैन डू दैट. इन दैट क्वेश्चन एक्चुअली donor concentration was given, so n can be approximately equal as nd. So you put here nd, so it becomes EC minus EF, and that becomes KT ln NC upon nd. And please do that question. ठीक, बहुत अच्छा क्वेश्चन है, उस क्वेश्चन को करिएगा. एंड देन इफ यू आर एबल टू डू दैट, मीन्स द कंसेप्ट इज क्लियर, राइट? Otherwise you can refer the solution I have given in PYQ as well. Here also you can use P is equal to approximately Na, but Na should be greater than Ni. That must be followed, right? Shall we go ahead? Let's move on to the next concept. No, Ars, you are wrong. Nd is what? Nd is donor concentration. So donor concentration is amount of dopant to which we are adding. It depends upon us how much dopants we are adding. So at a given temperature, the amount of the dopant will be provided by us. So it doesn't depend upon temperature. It is not the function of temperature. It is the amount of impurity which we are adding, right? Okay. Now, drift current density. Drift current density. The next concept is drift current density. J से denote कर रहा हूं मैं अभी इसे, right? We know that from Ohm's law, J is equal to sigma into E, where sigma is known as conductivity. It is known as conductivity. It is reciprocal of resistivity 1 upon rho, and rho is nothing but resistivity. You should be knowing these two fundamental quantities, very important. So it is resistivity. Dear friends, you see, this equation can be written as J is equal to NQ mu n, conductivity due to electrons, plus PQ mu p, conductivity due to holes, multiplied by electric field. This is the general relationship for current density in a semiconductor, irrespective whether it is n-type or p-type. This is the general relationship. Now you see, dear friends, here the term sigma is equal to NQ mu n plus PQ mu p. This is reciprocal of resistivity. So this is the expression for the conductivity of semiconductor, general expression for conductivity of semiconductor. For any types of a semiconductor, it is valid for intrinsic, it is valid for extrinsic, it is valid for any type of semiconductor, n-type, p-type. For every semiconductor, it is the general relation. Sigma is equal to NQ mu n plus PQ mu p. You know all these terms. N is electron concentration, mu n is mobility of electron, mu p is mobility of hole. Yes, sir. If you are saying NC and NB, that's correct. Good. And then Q is magnitude of electronic charge. Now you see, dear friends, for each and every semiconductor, we are interested to discuss this. So let us discuss for intrinsic semiconductor. If I talk about intrinsic semiconductor, then what happens? Very important concept. GATE ने इस पे कई बार question किया हुआ है. So let's try to discuss. In intrinsic semiconductor, sigma will become sigma I. I denotes just intrinsic, right? And N is equal to P is equal to Ni. So if I put this value, it is Niq mu n plus Niq mu p. So Niq we can take common. So sigma I is equal to Niq mu n plus mu p. This is reciprocal of rho I, where rho I is intrinsic resistivity. It is the conductivity of intrinsic semiconductor. Conductivity of intrinsic semiconductor. Conductivity of intrinsic semiconductor. We need to go a little bit depth of this concept. We know that Ni is function of temperature as well as mobility is also function of temperature. So let's try to find out conductivity as a function of temperature. Manasvi is asking, sir, can we find probability from mobility? Probability from mobility, what you are wanting to know? If you have relationship, mobility relationship, then directly probability, I don't think so. You need further some more information also. Directly from mobility we can't say about probability. Mobility is what? That is velocity, right? That is nothing but the drift velocity. Next, you need some more relations also. आप question भेज देना मुझे, देख लेंगे क्या है. We have Ni is equal to root A naught T to the power 3 by 2 e to the power minus Ez naught upon 2 kt, right? One more thing which we are having, mu n is directly proportional T to the power minus 3. Let us suppose we are at higher temperature, near about room temperature. So we are ignoring the impurity scattering. We are focusing only on the lattice scattering. If nothing is said, that then we will assume by default that material is near about room temperature. And near about room temperature, we have a dominant mechanism of scattering, that is lattice scattering. So because of lattice scattering, mobility varies as mu n is directly proportional T to the power minus 3 by 2. So you can write it as mu n, some proportionality constant. Let us suppose mu n naught, I will write some constant, it is independent of temperature. You can write ABC, whatever is that, minus 3 by 2. Similarly, we have mu p also, mu p t to the power minus 3 by 2, and then you will have mu p, some constant mu p naught t to the power minus 3 by 2. So if you solve all these, you put all these values, let's solve. It will take just 1 minute because it is very important point. So from this we will have sigma I ni. Ni is root a naught t to the power 3 by 2 root a naught. Ni is this root a naught t to the power 3 by 2, and then it is minus eg naught upon 2 kt into q into mu n naught t to the power minus 3 by 2 plus mu p naught t to the power minus 3 by 2. T to the power minus 3 by 2 you take common, then it will be added, so it will become t to the power 0. T to the power 0 is 1, root a naught is constant, q is constant, mu n naught plus mu p naught is constant, so this all entire term will become constant. So on solving you will have sigma I, some constant c1, let us suppose, e to the power minus eg naught upon 2 kt, right? This is your sigma I. If you increase the temperature, it is constant, this value will decrease. So with increase in temperature, this value, this temperature is increasing, this is decreasing, so E minus x will increase, and then this entire term is increasing. So with increase in temperature, conductivity will increase. That we can conclude from this relation. If I talk about rho I is 1 upon sigma I. So it is 1 upon C1 e to the power minus Eg naught upon 2k. If you simplify this relationship, then it comes out as rho I is equal to 1 by C1, new constant C2 e to the power, this is minus Eg naught, so it is Eg naught divided by 2k, right? Very important. Let's take the log of both sides. So if I take the log of both sides, log rho I is equal to log a plus b is log a plus log e to the power Eg naught. Basically I am taking natural log ln 2kt, right? You simplify this relationship, it is ln rho I is equal to ln c2 plus, this comes out as log e to the power something is that value itself, so Eg naught upon 2k into 1 upon t. Now I want to plot a curve. That curve I am wanting to plot between, at x-axis I am wanting to take temperature 1 by t, and here I am wanting to take log of rho I, ln rho I. So y is nothing but this term is y, this term is x. So it is nothing but y is equal to mx plus c, where m is slope, this is m, that is slope, and this is your constant c. So it is a straight line something like this, right? And slope of this straight line is Eg naught upon 2k. गेट में एक बार आपसे क्वेश्चन पूछा गया, यू हैव बीन गिवन अ ग्राफ बिटवीन लॉग रो आई वर्सेस 1 बाय टेम्परेचर, एंड द ग्राफ इज ऑलमोस्ट अ लीनियर ग्राफ, एंड ही आस्क कि व्हाट यू विल डिटरमाइन फ्रॉम दिस ग्राफ. तो स्लोप ऑफ दिस ग्राफ विल गिव यू Eg naught by 2k. K is known to us, so you can calculate Eg naught. So from the slope of this graph you can determine the band gap of semiconductor. So answer of that question was band gap of semiconductor. So such kind of questions can be framed. So I want to discuss this question, and that's why I have been doing all this calculation. Please go ahead. We started from here. Please do it quickly. आसिफ नदीम जी पूछ रहे हैं आज कहां तक डिस्कस होगा. जहां तक आप चाहो. कहां तक चाहते हो बताओ आसिफ जी, आपकी इच्छा. Deepsika, I do remember your name. Good. How are you? How is the life going on? Asif is saying up to mass capacitor. चलो कोई नहीं, तो इस चैप्टर के बाद मास कैपेसिटर ही कर लेते हैं. ये तो लगभग खत्म होने वाला है चैप्टर. Please do it. That's great. Deepsika, you didn't invited me to Northeast, the beautiful place. I'm just joking. Let's move on to the next topic. Now, conductivity of n-type semiconductor. Conductivity of extrinsic semiconductor I write, and then parallelly I will write for both extrinsic semiconductor. So, conductivity of extrinsic semiconductor. Let's divide the board in two equal parts. So, let us suppose left side I am writing n-type and right side I am writing p-type. So, it is n-type and it is p-type. It is p-type. Right? You see, my dear friends, the general expression for n-type I am writing as nq mu n plus pq mu p. It is valid in both. For p-type we can write it sigma p. So, nq mu n plus pq mu p. If doping level is comparable to the intrinsic carrier concentration, then majority and minority carriers will be comparable, and then you cannot ignore any one of them. Then you have to calculate total conductivity because of electron as well as because of holes. Here also you have to consider both majority as well minority. So before jumping to any conclusion, the important thing which is required is you need to compare whether the doping is comparable to Ni or it is greater than Ni. So let us suppose here Nd is greater than Ni. Yeah, Nd minus Na. If it is compensated, you can write Nd minus Na. I am assuming that it is non-compensated. And here let us suppose you have Na greater than Ni. So if this is the case, then majority carrier concentration would be very large, right? So in that case, basically we have N is far greater than P. So contribution of this minority carriers would be negligible, and we can say that sigma N is approximately equal to nq mu n, and if it Nd is greater than Ni, then it can also be written as Ndq mu n. If it is compensated, then it is Nd minus Na. You can use this relationship, but you will be able to use this relationship under this condition. ये बड़ा ध्यान रखिएगा. Similarly, if you have Na greater than Ni, then this term would be very large as comparison to this term. So you can neglect this term and you can say that sigma p is approximately equal to pq mu p, and under this condition p is approximately equal to Na, so you can use Naq mu p, right? Resistivity is reciprocal of these two. So if you want to calculate rho p, then it is reciprocal of sigma p, and similarly rho n reciprocal of sigma n. So you can calculate like this. Right? If it is compensated, then p will be replaced by Na minus Nd, p will be replaced by Na minus Nd. So please take the screenshot of this. Sir, there is very very nice detailed lecture taken by you already on mass capacitor, and it is available on your MADG channel. If you today do revision of PN junction and BJT, it will help a lot. Thank you. बात में तो आपके लॉजिक है. भूमित कुमार कह रहे हैं कि मास कैपेसिटर का लेक्चर मैंने ले रखा है, तो अगर मैं पीएन जंक्शन और बीजेटी करूं तो ज्यादा बेहतर है. ऐसा करते हैं ना, सब कर लेते हैं, आप बैठे रहो, ठीक है, हमको कौन सा जल्दी है, ठीक, सारा ही कर लेंगे, 2 की बजाय 3 बज जाएगा, क्या फर्क पड़ता है, ठीक है, नहीं करेंगे आज लंच, ठीक. दीपक सिंह कह रहे हैं कैसे क्रैक करेंगे, एक ही मूल मंत्र है, पढ़ना पड़ेगा बस, ठीक है, और कुछ नहीं, जस्ट यू हैव टू स्टडी. दीपशिका इज सेइंग ऑलवेज वेलकम सर. थैंक यू. Whenever I'll come, I'll contact you. Next, let us move on. Conductivity of extrinsic semiconductor से आगे चलते हैं. Let us suppose I talk about minimum conductivity in semiconductor. So minimum conductivity, how we are going to calculate? So it is irrespective of p-type or n-type semiconductor. So minimum conductivity we are wanting to, we are not writing everything, let's write this much only, right? Minimum conductivity. Right? Minimum conductivity will take place. I am not deriving, I am writing directly the relationships. So for what value of electron and hole concentration will take place? So if n is equal to ni under root, if n is equal to ni under root mu p upon mu n, then minimum conductivity will take place. So this is the expression to calculate electron concentration, expression to calculate electron concentration when conductivity is minimum, conductivity is minimum in both, and it is valid for both n and p both, चाहे n टाइप सेमीकंडक्टर हो या p टाइप, दोनों के लिए सेम एक्सप्रेशन आएगा. फॉर n टाइप एंड p टाइप सेमीकंडक्टर, दोनों में. ठीक, मैं ये कहना चाह रहा हूं इस सेंटेंस में कि दोनों के लिए वैलिड है. इट इज वैलिड फॉर बोथ. Similarly, if I want to calculate hole concentration, then this P is going to equal to Ni root mu n upon mu P. This is P. And it is expression to calculate hole concentration, expression to calculate hole concentration when conductivity is minimum. When conductivity is minimum. जब conductivity minimum हो आपको hole concentration calculate करना हो तो you can do. It is also valid for both n type and p type. दोनों के लिए सही है, irrespective of the type. Now if I want to calculate minimum conductivity, so this minimum conductivity sigma minimum is 2 Ni q under root mu n mu p is equal to 1 upon rho max. Don't try to memorize this. यदि आप ये दोनों रिलेशन जानते हैं तो जनरल एक्सप्रेशन आप कंडक्टिविटी में इनकी वैल्यू पुट करके सॉल्व करिए, you will get this only. So this is minimum conductivity, and minimum conductivity is nothing but reciprocal of maximum resistivity, so you can get this relation. Please take the picture of this. So this is all about minimum conductivity. Let's move on to the next. Concentration at edge of depletion region. Yeah, sure. We will discuss each and everything. And in PNP, concentration of electrons, concentration of electron holes while biasing, with biasing. Why not? Let's see all these things. Let's try to see. देखते हैं कितना किया जाता है. अभी तो जोश रखिए ही to do entire syllabus. Hall effect I am not discussing because it is very lengthy topic and not important for GATE. For engineering services it is important, so I will advise the folks who are going for engineering services, please refer the notes, each and everything I have given there. And for prelims, don't go for the derivation. I have done all the derivation in the class, that's not important. For prelims, for mains it is very important, right? So for prelims, whatever conclusions we have drawn at the end, refer that conclusion in Hall effect. Let us go for the next, that is diffusion current density. So diffusion current density, diffusion current density, diffusion current density. I'm writing it separately for electrons and holes. So for electrons, diffusion current density can be written as like this: Jn diffusion, and that is equal to q dn upon dx. Whereas dn upon dx is the concentration gradient. So gradient means slope. So d dx of slope. It means here the concentration is a function of distance. So basically you will have like this. It is n of x and this is x. So let us suppose you have concentration like this, right? So you will have this kind of concentration. dn upon dx is non-zero, then only you get this relationship. Dear friend, you see electrons will be moving from high concentration to low concentration. So it is electron diffusion. Electron diffusion is towards the negative x-axis, but the current you will get towards the positive x-axis because this slope is positive for this graph. So for this graph slope is positive, then current is along positive x-axis. So diffusion के opposite में current होगी. So this would be the direction of electron current density. This is for electrons, right? For holes, if you talk, and for this case only, if you change the slope of the concentration, then accordingly things will change. Now, let us suppose if I write for holes, then what will happen? For holes, we will have for holes Jp diffusion, for holes Jp diffusion is minus q dp upon dx, where p is function of x, right? So let us suppose you have this is xp and x. So now p is function of x. So you have something like this kind of hole concentration. So for this case, obviously holes are diffusing in this direction from high to low concentration. So it is hole diffusion. And you see this minus sign is indicating that current is also in the same direction. So the whole diffusion current density is like this, right? It is valid for this case. If you change the slope, then accordingly things will change, right? You need not to worry about that. While calculating, what you have to do, just calculate the slope. जो भी दिया हो, जितनी भी slope की value आ रही positive negative, वो value put करके and solve कर लीजिए. ये expression ध्यान रखिए और slope calculate करिए. जो भी slope की value आई वो put करके और solve कर लीजिए. Current की direction accordingly adjust हो जाएगी. ठीक? So you need not to worry about that. This is the diffusion current density. Please note down. Here we have one term, dn and dp. What are dn and dp? Let us see. That is very important term. dn is known as diffusion coefficient of electrons. Diffusion coefficient, diffusion constant भी कहते हैं इसे, diffusion coefficient of electrons. And dp is known as diffusion coefficient of holes. इसे diffusivity भी कहते हैं. So dp is diffusion coefficient of holes. Diffusion coefficient या diffusion constant of holes. These are related as something like this. dn upon mu n is equal to dp upon mu p is equal to kt by q, which is nothing but bt. bt is thermal voltage. So let's see. This relation is very important relation, very favorite for GATE exam, that is Einstein relation. It is known as Einstein relationship. It is known as Einstein relationship. And here Vt is Kt by Q. This is known as volt equivalent of temperature, या popularly thermal voltage. Thermal voltage. If we put the values of K and Q and solve it for temperature, so at 300 Kelvin, that is room temperature, Bt is approximately 26 millivolt. So if nothing is mentioned in the question about Bt, then you can take it as 26 millivolt. That comes out roughly around 0.0258, that is 25.8 millivolt. 25.8 millivolt can be approximated as 26 millivolt. So you can use this 26 millivolt, and this relation is a very important relation. This frequently you get questions. Pranav, I have not gone through the questions. so commenting would not be easier for me, right? And obviously if it is written that important question, then those questions must be from the important topics. Now let us suppose we talk about total current density. What is total current density? Done? Am I audible now as well as visible? Am I visible now? There was some internet connection problem, so it is start. There was some problem with the connection, and the team tried to resolve it, so it took few minutes. So I was offline for that time. This was the heading which we were discussing, that is total current density, and that total current density can be written like this. Please take the screenshot and let's move on to the next topic. Now I hope the issue has been resolved. Thank you for your patience, right? Thank you. Let's go ahead. Now in GATE you find several times a question, that is calculation of built-in electric field in a graded semiconductor. Graded semiconductor means the semiconductor in which doping concentration varies as a function of distance. It is not same throughout the material, it is non-uniformly doped semiconductor. So in a non-uniformly doped semiconductor, under equilibrium condition, a built-in electric field is produced. So how to calculate that built-in electric field? If the material is under equilibrium, then it means there is no excitation, no input has been given. And if no input has been given, then there should not be any current. So under equilibrium you should not have any current. And if there is no current, then drift and diffusion should oppose each other, and because of which net current through the material should be zero. So we would be using this concept that net current density under equilibrium condition is zero to calculate the built-in electric field. So put a heading, calculation of built-in electric field. Calculation of built-in electric field in non-uniformly doped that is graded semiconductor under equilibrium. This we are calculating at equilibrium. Concept of built-in electric field comes into picture under equilibrium. So under equilibrium total current density is zero. Under equilibrium condition total current density is zero. Under equilibrium condition total current density is 0. Total current density is 0. So let us suppose, again I am trying to see p and n type simultaneous type semiconductor, and if it is p type semiconductor. So in p type we will take the whole current, and in n type we will take the electron current, because in p type whole concentration will be almost equal to the acceptor concentration, and in n type it is almost equal to the donor concentration, and those acceptor and donor concentrations are known to us, so we are wanting to calculate in that term. Although the total current would be 0 whether it is because of the electrons or it is because of the holes. So here also you can use for the electrons, and here also you can use for the holes, but I am doing the most popular method that would be simple to understand. So here let us suppose we say Jn is equal to 0. This Jn is nothing but Jn drift plus Jn diffusion. Similarly here we say that Jp is equal to 0, that is Jp drift and plus Jp diffusion, right? Let's solve this. Jn drift is what? Now n is function of x, so let us suppose nx, and this is q mu n, and e will also be the function of x, so ex, n q mu n, tick, plus q dn, and this is n as a function of x dx is equal to 0. Let us suppose these are varying with x. X is your coordinate, basically the distance you can say. Here you can write p of x and q mu p, this is drift current, minus diffusion, you know minus के साथ आता है इसमें, dp dp of x dx is equal to 0. So from this relation let us try to calculate these values. This q will get cancelled out, and you know dn is what? In place of dn we can put mu n into vt, so mu n will also cancel out. So if I solve for ex, it will come out as e of x is equal to minus vt upon n of x, ये इधर चला जाएगा, and it is mu n cancel हो जाएगा, vt हो जाएगा, d n of x dx. If doping concentration is far greater than the intrinsic concentration, then n of x can be written as nd of x, so you can put this value and you can solve. Similarly here also you see this q and q will cancel out, then this dp can be written as mu p into vt from Einstein relation, and b can have sorry यहाँ मैंने e नहीं लिखा, I have forgot to write e here. Please write down one more term. It can be written as p of x q mu p e of x minus, right? So this q and q cancel. So if you solve this, here this mu p will cancel, and on solving it comes out as e of x is equal to, ये minus उधर जाके plus हो जाएगा, so it is vt p of x and it is dp of x upon dx, right? So this is the relation you can use to calculate the built-in electric field, and here p of x you can approximate it as Na of x. So if acceptor concentration is given, you can use this. So don't try to memorize the relation, just remember what total current density is equal to 0. If it is n type, so equate the electron current density to 0 and calculate, and if it is p type, then equate the whole current density and make it make the calculations. So you can do this. This is about the calculation of built-in electric field. Please go ahead. Do it. Calculation of built-in electric field. Are you there? आप लोग हैं या चले गए, भाग गए? इंटरनेट कनेक्शन रीस्टोर करने में कुछ समय लग गया था. अगर आप लोग चले गए हो तो फिर सेशन बंद कर दें. Acha, are you there? Okay. So, you know, those who have taken my class, you know, I get energy from you. So, you need to be active in my class so that I can take class for longer duration. Let's move on to the next point. Dear friends, let's revisit electric field intensity again. Electric field intensity. Suppose we have one electron and that is free electron. So this free electron is where? It is in conduction band. This is EC. So the free electron is here. So energy, it is equal to EC. So energy of electron, that is equal to EC, right? And this energy should be equal to charge of electron, that is minus Q, into the potential. Let us suppose the potential of electron at this point is phi. So phi is what? Potential. We know in our entire discussion I represent potential by phi. So charge of electron multiplied by the potential, that will give us the energy of electron at this potential. So this energy is nothing but equal to EC. If electron is free, it is in conduction band, and in conduction band minimum energy of electron is EC, let us suppose. So from this we are having phi is equal to minus EC by Q, right? Very important discussion I am going to do from this. Now you see electric field intensity. Electric field intensity. What is electric field intensity? I represent it by like this, E. यहाँ पर क्योंकि E से energy we denote करते हैं, E से electric field. So in order to avoid any confusion, I am representing electric field like this, because here I have to use energy also. So you should not get confused. It is just a notation, nothing else. So electric field is minus d phi upon dx, right? I can simplify this, minus d dx of, and this is phi, that is minus EC by Q. So minus minus plus, and it becomes E is equal to 1 by Q dEC upon dx. What is d dx of EC? It is nothing but the slope of conduction band. So if there is a slope in conduction band, it represents presence of electric field in the material. And if the slope is 0, then there is no electric field in the material. So presence of slope in conduction band represents non-zero electric field through the material. And if there is no slope, means d dx of EC is equal to 0, then you can say that there is no electric field across the material. We know that conduction band and valence band are parallel to each other, and intrinsic level is midway of these two. So EC, EI and EV are parallel to each other. If three lines are parallel to each other, their slope would be equal. So, and d dx of EC is nothing but the slope. So since EC, EV and EI are parallel to each other, so you can write like this. So electric field can be calculated 1 upon Q dEC upon dx, या 1 upon Q dEV upon dx, 1 upon Q dEI upon dx. So आपको इन तीनों में से किसी की भी स्लोप पता हो, you can calculate the electric field in the semiconductor. You see, 2 years back there was a question in which the slope in valence band was given, and he asked what is the electric field. So if slope in valence band is given, then you can use 1 by Q dEV upon dx and you can calculate the electric field. So slope in conduction band or slope in valence band or slope in intrinsic Fermi level represents the presence of electric field through the material, right? Please do it. Take the screenshot of this, then I will move forward. Yes, yes, it is restarted. First time we got some problem in live class at YouTube, otherwise usually it doesn't happen. Shall we go ahead? भाई यार एक आध चाय वाय और पिलाओ, थक रहे हैं। चाय हर घंटे तुम पिलाते रहा करो, क्लास लंबी जाएगी, लंच नहीं करेंगे। डन, गुड। अब एक चीज देखिए, लेट अस सपोज वी हैव सेमीकंडक्टर अंडर इक्विलिब्रियम। दिस इज आवर सेमीकंडक्टर, सपोज आई टेक एन टाइप सेमीकंडक्टर, ठीक। सिमिलरली यू कैन टॉक अबाउट पी टाइप आल्सो। So if I take n type semiconductor, let us suppose it is n type semiconductor, and this is under equilibrium. Under equilibrium means there is no external voltage applied across it. So potential difference throughout the material is 0. So I can assume potential here 0, here 0, at every point potential is 0. So phi is equal to 0 and phi is equal to 0, everywhere it is 0. Yeah, even if it is at constant potential, then d phi would be 0, you can say, right? But let us suppose I am assuming that phi is equal to 0. Now you see, if I draw the Venn diagram of this, right? If I draw the Venn diagram, right? So Venn diagram would be something like this. Since there is no electric field, potential is constant. Basically, phi 0 ki bajay you can write it constant, right? You can write it as constant. So if you write it as constant, then d phi upon dx is equal to 0. If d phi upon dx is equal to 0, then electric field is equal to 0. So there will not be any slope. If electric field is 0, then it means what? dEc upon dx is equal to 0. So there is no slope in conduction band. So conduction band is like this, right? Now suppose you want to draw the balance band. How the balance band would be? EC and EB are parallel. So once you draw the EC, then it is easy to draw EB. They are parallel to each other. How you will draw EI? EI is also parallel. So it is also parallel. And it is. How you will draw EF? EF will be like this. It is EF. It is EF. Okay? EF is somewhere in between EI to EC, any place depending upon grouping, it is between. अच्छा, एक और बात यहाँ पर, dEf upon dx is equal to 0. It means no current is flowing through the material. No current is flowing through the material. Flowing through the material. And if dEf does not equal, dEf upon dx does not equal to 0, then current is flowing through the material. Current is flowing through the material. Try to understand two beautiful things here. Slope in conduction band represents presence of electric field in the material, and slope in Fermi level represents current through the material. जरूरी नहीं है कि इलेक्ट्रिक फील्ड हो तो करंट होगा भी. इलेक्ट्रिक फील्ड या पोटेंशियल डिफरेंस कैन एग्जिस्ट इवन अक्रॉस ओपन सर्किट, एंड इन ओपन सर्किट यू कैंट हैव करंट. Like under equilibrium condition, you see you have built-in potential, so it means you have electric field, but you don't have current. So if you draw the band diagram, since you have built-in electric field under equilibrium in a non-uniformly doped semiconductor, so you will have some slope in the conduction band. But Fermi level should not have any slope under equilibrium condition because there is no current. So current, if you have to see, then you have to see slope in Fermi level. And if you want to see the electric field, then you have to see the slope in conduction band or valence band or intrinsic level, right? This EF is Fermi energy level of doped semiconductor. EI is Fermi energy level of intrinsic. EI is parallel to EC, but EF is not parallel to EC. It's not necessary to be parallel to EC. It depends upon the applied voltage. उस पे भी depend करेगा ही. उसके accordingly चीजें बदलेंगी, बाद में देखेंगे. ठीक. So this is the band diagram under equilibrium condition. Band diagram under equilibrium condition. Band diagram under equilibrium condition. Under equilibrium condition. You have some band diagram under equilibrium condition, right? You please do it. Take the screenshot of this. Simple thing. It's a simple thing. Then we'll moving forward to discuss the next point. सर आपने चाय कम नहीं किया अभी तक, आपके घर पता है. अंकित is saying I missed attending your class सर, बहुत मज़ा आता है. That's great, thank you अंकित. मानवी, हाँ चाय कम नहीं हो पा रही, गंदी आदत है. वैसे कम किया है बट अभी क्योंकि पढ़ाते वक्त ना कुछ थकान लगती है, तो हाउ कैन यू ओवरकम दिस, समथिंग लाइक दैट. खैर फर्जी बहाने बना रहा हूँ मैं. चाय वास्तव में अभी भी ज़्यादा ही पीता हूँ. आइए देखते हैं. लेट अस टेक अनदर एन टाइप सेमीकंडक्टर. आई एम टेकिंग अनदर एन टाइप सेमीकंडक्टर. This is n type, right? Similarly, you can talk about p type also. Let's take n type, and I'm applying some voltage across it. So if there is some voltage, some potential difference, it means there is some electric field across this material. We can calculate that electric field V naught by L, something like that, right? Let us suppose this is our reference potential. So at reference potential, I'm taking reference potential as ground. This is our low potential. This is low potential, and here we have high potential. This side is at high potential. So if reference potential is at 0, then obviously this side will go at V naught. So it is V naught. I'm wanting to draw the band diagram of this semiconductor under the influence of this applied voltage. Dear friends, if you calculate the energy of conduction band, always when you have to draw the band diagram, first of all try to draw the conduction band edge. Once you draw the conduction band edge, whether it is n type or p type or any semiconductor material, for every semiconductor material, first draw the conduction band. Take an electron and considering that electron, calculate the energy and try to draw the conduction band. Once you are able to draw the conduction band, then valence band will be parallel to the conduction band. So you can easily draw the valence band. So never try to start with valence band. You may lead to the wrong conclusion and you may do the mistake, right? So always try to do by considering electron and try to draw a conduction band as first, whether it is n type semiconductor or p type, for both of the cases. Now you see, dear friends, if I calculate EC here, EC is what? Minus Q into phi, so it is minus Q into 0, so it is 0. But if I calculate EC here, what is EC is minus Q into V naught, so you see. What does it indicate? It indicates that at this edge the energy of electron is 0 and at this edge the energy of electron is minus QB naught. So let us suppose this is 0 line. So if it is 0 line, so it is the reference line, right? So this side the energy of electrons should be less than 0. How much less than? If you go upside it would be greater than 0. If you come downside it would be less than 0. How much less than 0? Q V naught. And since you have applied some voltage, so there must be some slope. So if I connect these two lines, let us suppose I connect them like this. This is the conduction band edge on the application of voltage. This side 0 energy, this side minus QB naught. So this side is QB naught down as comparison to this side. So this would be your EC. You connect these 2 points, this is EC. Now EB is parallel to EC. So EB is parallel to EC. It is EB. EI is also parallel. मुझसे parallel line बन नहीं रही है. You will assume them as parallel. It is EI. Since it is a closed circuit, some current would be flowing, so EF will also have slope, so it is also parallel. EF का concept आगे chapter 2 में देखा जाएगा. Leave it as of now. अभी EF पर bother नहीं करेंगे. So this is the band diagram for the n-type semiconductor when you have applied voltage like this. Few important points you need to observe here. What are those points? On the energy band diagram, higher potential is represented downward. This is high potential and this is low potential. On the energy band diagram, higher potential is represented downward. Lower potential is represented upward. First point. Second point, since there is an electric field, so there is a slope in the energy band diagram. So slope in band diagram represents presence of electric field across the material, right? Next you see, electrons will move from low potential to high potential, मैंने आपको बताया है. So it means electrons will move down the hill. They will move down the hill. So you may have read a sentence in books, electrons love to move downhill on the band diagram, because upside you are representing low potential, downside you are representing high potential. Electrons always move from low to high potential. It means they will be moving down the hill. Hill means slope, so they would be moving down the hill, right? Similarly, holes would be moving like this. Holes move from high to low potential, so holes would be moving like this. Holes are in balance band, so they would be moving uphill. So on the energy band diagram, holes love to move uphill, electrons love to move downhill. This is all about the band diagram. Let us suppose you change the voltage polarity, then what will happen? Suppose plus here, minus here. So this side will go high potential. If this side will go high potential, it will go downward. This side will go low potential, it should go upward. So the slope will change, rest of the things will remain same. If it is p type, then nothing will change. Only what will happen? Fermi energy level will be somewhere in between EI and EV. So you get questions on this concept. That's why I thought that you should know this concept. Let us suppose it is built-in electric field. You don't have applied any potential, and you just have built-in electric field across the material. So then what will happen? Then EF will become constant. So it will not have slope, it will become constant, but EC will have slope like this. So you can have all those variations, and I thought that okay, I have discussed each and everything. Please go ahead. Very beautiful concept, this concept of energy band diagram. Beautiful concept है. In fact, I used to say in the class कि अगर आपको concept of energy band diagram समझ में आ गया, तो इसका मतलब ये है कि आप अब पूरी की पूरी electronics engineering समझ गए हैं. You don't have problem in the entire electronics engineering. Electronics engineering से मेरा मतलब EDC, electronic devices कह लूँ, ज़्यादा proper होगा. Shall we go ahead? चलिए आगे चलते हैं. Let's move on to the next concept. मेरी चाय भी आ गई. Manasvi is saying electrons downhill. Right. Electrons love to move downhill, and holes love to move uphill. Move on to the next concept. Very beautiful concept. Optical generation of excess charge carriers. Optical generation of excess charge carriers. Optical generation of excess charge carriers. You have a semiconductor material. This is our semiconductor material, right? And you are shining light on this semiconductor material. Light means photon, right? So let us suppose this is the band diagram. This is valence band, and this is conduction band, this is band gap, right? If the energy of photon is, what is the energy of photon? H nu. It is greater than the band gap, then an electron hole pair will be created. And if energy of photon is less than the band gap, then this energy would be transmitted. Yeah, you can say that no electron hole pair would be created. Right? So I can write one very important thing. If H nu, yeah, you can write one thing first. Energy of photon is H nu, which is Hc by lambda. Nu is frequency of light, frequency of light. Lambda is wavelength, c is velocity of light in vacuum, velocity of light in vacuum. The value of c you know very well, it is 3 into 10 to the power 8 meter per second. This is energy of photon. Now if this energy of photon is how is the tea? It's good, it's good, it's tasty. Right. Now you see, dear friends, if energy of photon is greater than the band gap, so I can say that if h nu is greater than r equal to hg, या इसी बात को आप लिख सकते हो h c by lambda is greater than r equal to eg, or you can write इसी बात को lambda is less than r equal to hc by eg. You can put the values of h and c, they are known to us. So lambda in micrometer आ जाएगा आपके पास, and this is 1.24. Eg को इलेक्ट्रॉन वोल्ट में पुट कर लो. You remember this relation? This is nothing but we are putting the values of h and c and solving this. So if all these conditions are satisfied, they are nothing but the same, then photon is absorbed. Photon या light is absorbed by the semiconductor and an electron hole pair is created. An electron hole pair is created. Such optically generated electron hole pairs, such optically मतलब light के कारण, optically generated electron hole pairs are known as excess charge carriers. Actually, excess charge carrier is a broad term. डोपिंग और थर्मल फिनोमेना के अलावा अगर किसी भी अन्य फिनोमेना से आप कैरियर क्रिएट कर रहे हैं तो दैट इज एक्सेस कैरियर. जो मटेरियल में हमारे पास कैरियर्स हैं, वो मटेरियल किसी टेम्परेचर पर रखा है तो उसके इंट्रिंसिक कैरियर्स बिकॉज ऑफ दैट टेम्परेचर, एंड यू डू द डोपिंग, सो बिकॉज ऑफ दैट डोपेंट एटम सम कैरियर्स आर क्रिएटेड. इसके अलावा अगर किसी अन्य मैकेनिज्म से कोई कैरियर क्रिएट हो रहे हैं, जैसे यहां लाइट के थ्रू क्रिएट हो रहे हैं, सो दोज विल बी नोन एज excess charge carriers. So if they are generated due to light, then the excess charge carriers due to light, optically generated excess charge carrier. Suppose you apply a voltage and you are injecting some carrier from the supply, so that is the injected excess charge carriers. That is because of the some supply voltage. So there are several mechanisms with the help of which you can create excess carriers in the material. So मैं क्या कह रहा हूं, ध्यान से सुने कि डोपिंग और टेम्परेचर के कारण, या यूं कह लें कि इंट्रिंसिक कैरियर, इंट्रिंसिक आर बेसिकली बिकॉज ऑफ टेम्परेचर, इंट्रिंसिक कैरियर्स और डोपेंट एटम्स के कारण जो कैरियर्स हैं, उनके अलावा अगर कोई भी कैरियर आप जनरेट कर रहे हैं, दैट इज एक्सेस कैरियर. सो हियर ऑप्टिकली जनरेटेड एक्सेस कैरियर्स वुड बी क्रिएटेड. दिस रिलेशन इज वेरी इंपॉर्टेंट फॉर द गेट. Several times you have got question with the calculation of wavelength or band gap depending upon कोई एक चीज दिया होता है, दूसरा पूछता है. If this relationship is not satisfied, let us suppose h nu is less than Eg, या lambda is greater than 1.24 upon Eg, then light will be transmitted through the material and no electron hole pair will be created. Obviously, now the semiconductor is not under equilibrium. Here you are giving light as an input. So if you are putting light on the semiconductor material, then it cannot be said at equilibrium. So if it is not at equilibrium, then mass action law will not be valid, right? So now mass action law cannot be applied. Now in fact I will represent something like this. N naught is electron concentration at equilibrium. Electron concentration at equilibrium. This is the electron concentration at equilibrium. P naught is hole concentration at equilibrium. Hole concentration at equilibrium. This is P naught, hole concentration at equilibrium, right? Suppose you write N. पीछे मैंने NP लिखा है क्योंकि everything we have discussed at equilibrium. Now we have to separate the equilibrium and non-equilibrium. So this suffix O I am connecting just to represent we are at equilibrium. If this suffix is not there, it means we are at non-equilibrium. Non-equilibrium means we are disturbing the system by giving some input, right? That input can be light, that input can be voltage, that input can be anything. So it's not kept without any input. There is some input applied across the material. So now that input is suppose light. Yeah, it can be voltage, anything. So we have electron concentration under non-equilibrium, condition, electron concentration under non-equilibrium condition, and P is hole concentration under non-equilibrium condition. Hole concentration under non-equilibrium condition. Hole concentration under non-equilibrium condition. This is the hole concentration, right? Now you see, dear friends, delta P, if you see, delta P is excess hole concentration. Excess hole concentration. This is the hole concentration per unit volume due to the light or any disturbance which you are applying. Hole concentration, and delta N is excess electron concentration. Although you see here, since electron hole pairs are generated, so usually delta N is equal to delta P, right? Usually delta N is equal to delta P. Now we will have one important relation, that is N is equal to concentration at non-equilibrium N naught plus excess carrier delta N, and P is equal to N naught, sorry, not N naught, it is P naught plus delta P. So concentration at equilibrium plus excess. This is important relation. Here you see, my dear friends, N naught into P naught is equal to Ni square, because N naught and P naught are carrier concentration under equilibrium, and under equilibrium mass action law is valid. But N into P does not equal to Ni square. As I told you, mass action law is not valid under non-equilibrium condition. Mass action law is valid only under equilibrium condition. Take the screenshot of this. इसके ऊपर वाला भी करना होगा आपको. अच्छा, ये तो कर लिया है. हाँ, take the screenshot of this, please. Good, very good. And I answered. Now the semiconductor is at non-equilibrium. Hope you got the answer. Great. Now you see, my dear friend, let us consider N-type semiconductor. Suppose I consider an N-type semiconductor, right? It is our N-type semiconductor. So in an N-type semiconductor, I am giving you one example to illustrate something. Let us suppose intrinsic carrier concentration is 1 into 10 to the power 10 per centimeter cube, and dopant concentration Nd is approximately 1 into 10 to the power 15 per centimeter cube, right? Since Nd is far greater than Ni, so we can approximate electron concentration under equilibrium, that is N naught. N naught is approximately equal to Nd, and that is nothing but 1 into 10 to the power 15 per centimeter cube, right? And n naught into p naught is equal to ni square. So from that, if you calculate p naught is roughly around 20 upon 15, that is 1 into 10 to the power 5 per centimeter cube, right? These are the calculations. Suppose some light is falling on the material. Let us suppose some light is falling on the material. Now if light is falling, then equilibrium will be disturbed and some excess electron hole pairs would be created, right? So let us suppose we are having del n is equal to del p, and that is equal to 1 into 10 to the power 5 per centimeter cube. Okay. I am saying low level injection. Injection means excess carriers are created. They are injected because of some external phenomena. That is the meaning, right? So del n and del p, that is very small as comparison to the doping concentration. Yeah, as comparison to the majority carrier concentration. So if it is n type semiconductor, then del n, del p, that is less than n naught. It is less than n naught. Then I will say that this is low level injection. In our subject, we have to deal with low level injection, so you need not to worry about high level injection. That is not in our syllabus. So we will be dealing mainly with the low level injection. So this concentration is very small as comparison to the majority carrier concentration. That is the meaning of low level injection. Now if I calculate n, what will happen? N is n naught plus del n. So it is 10 to the power 15 plus 10 to the power 5, which is nothing but 10 to the power 15 per centimeter cube. This is n. But if I calculate p, then p is equal to p naught plus del p, that is equal to 10 to the power 5 plus 10 to the power 5, 2 into 10 to the power 5 per centimeter cube. One important conclusion which I want to withdraw from this example is that under low level injection condition, majority charge carrier will remain almost the same. There is negligible change in majority carrier concentration. You see 10 to the power 15 में 10 to the power 5 ऐड करने से कुछ खास फर्क नहीं पड़ेगा. So under low level injection condition, majority charge carrier will remain same. It is almost equal to thermal equilibrium condition. So majority carrier is not disturbing the equilibrium. Who is disturbing the equilibrium? Minority carriers. Minority carrier concentration has increased significantly. It has almost become double, right? So who is culprit to disturb the equilibrium? Minority carriers. So under low level injection condition, these minority carrier concentration is increasing significantly. So that is trying to disturb the equilibrium. If you want to restore the equilibrium, then these excess minority carriers must recombine with the majority carrier. And that's why we talk about the recombination of minority carriers and rate of recombination of minority carriers. In most of our calculation, we would be bothering about that. Because under low level condition, low level injection condition, majority carrier concentration is not changing significantly. So that change in majority carrier concentration we can ignore. So we can say that who is disturbing the equilibrium? Mainly the minority carriers are disturbing the equilibrium. So if these minority carriers recombine, these excess minority carriers recombine, then we can easily restore the equilibrium. So whenever system is disturbed, it moves to the non-equilibrium condition and it will try to restore the equilibrium. When it will try to restore the equilibrium, then excess minority carriers will recombine with the majority carriers, and when this recombination completes, then these excess carriers will get finished and equilibrium would be restored. So we talk about the recombination rate. So recombination rate, recombination rate, R, number of excess carriers per unit volume, per unit volume, per unit time, per unit time, recombining in the material. Number of excess carriers per unit volume, per unit time, recombining in the material. A layman definition. It's not theoretical, it's not a bookish definition, just to understand the things. Number of excess carriers per unit time, per unit volume, recombine in the material. Now suppose I want to write Rn, right? Yeah, let us suppose I want to write Rp. Rp is recombination rate of holes. Recombination rate of holes. It is Rp, recombination rate of holes. So excess hole concentration del P upon tau P, where tau P is known as minority carrier lifetime of holes. Tau P is minority carrier lifetime of holes. Minority carrier lifetime of holes. Carrier lifetime of holes. Minority carrier lifetime of holes. This is our Rp. This is Rp. But Rp की बात कहाँ करेंगे? For n-type semiconductor. Because holes are minority carriers where in n-type semiconductor. So you would be talking about for n-type semiconductor. You will be talking about n-type semiconductor. अगर आपको n-type semiconductor में excess carriers की बात करना है तो you would be doing this. Similarly, if I say Rn, so Rn is equal to del n upon tau n, right? Here Rn is recombination rate of electrons, basically minority carrier electrons. ध्यान रखना, मैं पूरा नहीं लिखा हूं तो भी recombination rate of minority carrier electrons, recombination rate of electrons, and tau n is minority carrier lifetime of electrons, minority carrier lifetime of electrons, carrier lifetime of electrons, lifetime of electrons, minority carrier lifetime of electrons. So this is for electrons, but where it is for, where are the electrons minority carriers? Electrons are minority carrier in p-type semiconductor, so this relation you would be using for p-type semiconductor, for p-type semiconductor, p-type semiconductor, right? This is about the recombination rate of minority charge carriers. Please note down this. करिए फटाफट. अंजलि कैलकुलेट करिए n माइनस पी क्या होगा. जस्ट पुट द वैल्यूज एंड कैलकुलेट n माइनस पी. दैट्स सिंपल मैथमेटिक्स. अब नाउ किसी ने क्वाजी फर्मी एनर्जी लेवल पूछा था. बेटा इफ यू सी नाउ, इफ यू कैलकुलेट द फर्मी, सपोज योर सेमीकंडक्टर इज अंडर नॉन इक्विलिब्रियम कंडीशन. सो इफ यू अंडर नॉन इक्विलिब्रियम कंडीशन, इलेक्ट्रॉन concentration is different than the equilibrium concentration and hole concentration is also different than the equilibrium concentration. So under equilibrium, if you calculate the position of Fermi energy level, it is same for both electron as well as hole. But here, since electron and hole concentrations are changing, electron concentration is almost same. So Fermi energy level for the electrons will be same which it was under equilibrium condition, but hole concentration has changed. So if you calculate the Fermi energy level with respect to the hole concentration, its position will differ than the position earlier it were having during equilibrium. So now here we define separate Fermi energy levels for electrons as well as holes under non-equilibrium condition, and these separate Fermi energy levels are known as quasi-Fermi energy levels. Quasi means temporary. So these are not the permanent energy levels, these are the temporary energy levels only under non-equilibrium condition. So जब तक non-equilibrium condition maintain रहेगी, quasi-Fermi energy levels maintain रहेंगे, यानी different Fermi energy level for electron and different for hole. You can put these values in the relations which we have derived earlier and you can calculate those Fermi levels. But as soon as equilibrium condition is restored, अगर इक्विलिब्रियम कंडीशन दोबारा रीस्टोर हो जाएगी तो क्वाजी फर्मी एनर्जी लेवल फिनिश हो जाएंगे, वैनिश हो जाएंगे, एंड यू विल गेट द कांस्टेंट फर्मी एनर्जी लेवल व्हिच वी कैलकुलेटेड अर्लियर. सो कंसेप्ट ऑफ क्वाजी फर्मी एनर्जी लेवल इज बेसिकली कमिंग इनटू पिक्चर टू शो द नॉन इक्विलिब्रियम कंडीशन, राइट? दैट इज द कंक्लूजन. खैर, क्वाजी फर्मी से कभी क्वेश्चन नहीं आया, सो आई एम नॉट गोइंग टू डिस्कस दैट. लेकिन अगर आपको कैलकुलेट करना हो तो आप इस इलेक्ट्रॉन कंसंट्रेशन के लिए आप यहां से कैलकुलेट करिए, n इज इक्वल टू एन सी टू दी या ni के साथ ही कैलकुलेट कर लीजिए. लेट अस सपोज यू नो ni, सो n इज इक्वल टू ni e टू दी पावर ef माइनस ei अपॉन kt. सो ये जो ef मिलेगा ये क्वाजी मिलेगा, क्वाजी फर्मी लेवल ऑफ इलेक्ट्रॉन, बिकॉज यहां जो आपने इलेक्ट्रॉन कंसंट्रेशन यूज किया है वो इक्विलिब्रियम पर नहीं यूज किया, नॉन इक्विलिब्रियम. ऑल्दो सिंस एन टाइप सेमीकंडक्टर दोनों सेम है, सो यू विल गेट द सेम. लेकिन अगर आप यहां से देखें, यहां से P से कैलकुलेट करें, P इज इक्वल टू ni e टू द पावर ei माइनस ef अपॉन kt, राइट? सो ये जो फर्मी एनर्जी लेवल होगा क्वाजी फर्मी लेवल, क्वाजी फर्मी लेवल ऑफ होल्स. तो अगर आपसे क्वेश्चन पूछ भी लिया जाए तो आप कैलकुलेट. सो नॉन इक्विलिब्रियम कंसंट्रेशन वैल्यू. नाउ दिस विल बी डिफरेंट देन द अर्लियर व्हिच यू यूज्ड टू कैलकुलेट एट इक्विलिब्रियम, बिकॉज दिस कंसंट्रेशन एंड इक्विलिब्रियम कंसंट्रेशन आर डिफरेंट, सो देयर फर्मी लेवल्स वुड बी डिफरेंट. सो दिस इज द क्वाजी फर्मी लेवल व्हिच इज अंडर द नॉन इक्विलिब्रियम कंडीशन, राइट? होप यू गॉट. किसी ने क्लास की शुरुआत में जब हम फर्मी लेवल पर बात कर रहे थे तो क्वाजी फर्मी लेवल पूछा था. नाउ वी आर मूविंग टुवर्ड्स द लास्ट हेडिंग ऑफ दिस चैप्टर, एंड दैट लास्ट हेडिंग इज, मनस्वी पूछ रहे हैं ईडीसी पीवाईक्यू, मोस्ट ऑफ द पीवाईक्यू किस चैप्टर से हैं? बेटा 50% क्वेश्चन चैप्टर 1 से होते हैं और 50% में सारे चैप्टर. Good. So we are going towards the last point of this chapter. अच्छा, यहाँ कुछ एक टर्म जो मैं और डिफाइन कर दूं, जरूरत लगती है. LP is under root dp into tau p. Tau p, you know, minority carrier lifetime for holes, and dp, you know, diffusion coefficient of holes. This is known as diffusion length of holes. Diffusion length of minority carrier hole. यानी होल माइनॉरिटी कहां होगा? एन टाइप में. डिफ्यूजन लेंथ ऑफ माइनॉरिटी कैरियर होल, माइनॉरिटी कैरियर होल, ठीक. इसी तरह से हम एलएन भी डिफाइन कर सकते हैं. ये सब छोटे छोटे टर्म्स हैं, कई बार बन जाता क्वेश्चन, तो क्योंकि सब कुछ कर रहे हैं इस चैप्टर में तो कुछ भी छोड़ेंगे नहीं. इसी तरह से एलएन इज अंडर रूट dn into tau n, and this ln is known as minority carrier diffusion length of electrons. Minority carrier diffusion length of electrons. Minority carrier diffusion length of electrons. Length of electrons. It is the minority carrier diffusion length of electrons. Right? Please note down this also. Take a screenshot. मजा आया या नहीं? मजा आ रहा है या नहीं? Now time to continuity equation, most important and difficult topic, right? अनय शुक्ला लिख रहे हैं. नहीं, डिफिकल्ट नहीं है, थोड़ा मैथ है. हाँ, डेरिवेटिव का सॉल्यूशन अंकित कह रहे हैं कि निकालने में थोड़ा समय लगता है. हाँ, थोड़ा सा लेंदी क्वेश्चन बनते हैं कंटिन्यूटी इक्वेशन पर. मैं ये कहूँगा कि कंटिन्यूटी इक्वेशन का क्वेश्चन जब भी आए एग्जाम में, पहले देखिए स्ट्रेट फॉरवर्ड क्वेश्चन है तो तुरंत अटेम्प्ट करिए, अदरवाइज लास्ट के लिए बचा करके रखिए. आपके पास समय बचे तो अटेम्प्ट करिए, ना बचे तो ना करिए, क्योंकि थोड़ा लेंदी क्वेश्चन तो होता है. ठीक. सो कंटिन्यूटी इक्वेशन, कंटिन्यूटी इक्वेशन मैं डेराइव नहीं करूंगा, इक्वेशन डायरेक्टली लिखूंगा. ठीक. दोनों के लिए अलग अलग कर लेते हैं. फॉर इलेक्ट्रॉन्स, अब कंटिन्यूटी इक्वेशन किसके लिए लिखते हैं? माइनॉरिटी कैरियर्स के लिए, क्योंकि कंटिन्यूटी इक्वेशन हम नॉन इक्विलिब्रियम कंडीशन के लिए डेवलप कर रहे हैं. सो अंडर नॉन इक्विलिब्रियम कंडीशन वी आर मोर बॉदर्ड फॉर द माइनॉरिटी कैरियर्स. सो इलेक्ट्रॉन माइनॉरिटी कैरियर किसमें है? पी टाइप में. सो यदि पी टाइप सेमीकंडक्टर है, सो वी विल बी राइटिंग कंटिन्यूटी इक्वेशन फॉर द इलेक्ट्रॉन्स, और अगर एन टाइप सेमीकंडक्टर है, सो वी विल बी राइटिंग कंटिन्यूटी इक्वेशन फॉर द होल्स. ठीक। सो मैं बोर्ड को दो पार्ट, एक तरफ इलेक्ट्रॉन्स के लिए और दूसरी तरफ होल्स के लिए। दिस इज फॉर इलेक्ट्रॉन्स, दिस इज फॉर इलेक्ट्रॉन्स एंड दिस इज फॉर होल्स, दिस इज फॉर होल्स, राइट। ऑब्वियसली इलेक्ट्रॉन्स के लिए किस में लिखेंगे, अब इलेक्ट्रॉन्स माइनॉरिटी कैरियर किस में होंगे, पी टाइप में, एंड होल्स माइनॉरिटी कैरियर किस में होंगे, एन टाइप में। ये सब आपको क्वेश्चन करने के लिए मैं शॉर्टकट्स बता रहा हूं, बाय आई एम नॉट गोइंग इनटू द डेप्थ, नहीं तो आप इसका वो कट करके एंड देन बोलो कि ये कंसेप्ट वो कंसेप्ट फर्जी कर रहा है। आजकल लोग ना ये शॉर्ट्स काट करके ये सब भी करते हैं। आपको डेप्थ में कंसेप्ट समझता है तो रेगुलर क्लास में बहुत कुछ समझाया हुआ है, उसके नोट्स चाहिए, उन वीडियोज में जाइए देखें। यहाँ क्वेश्चन करने के लिए आपको ट्रिक्स पर डिस्कस कर रहे हैं हम लोग। अब अगर हम इलेक्ट्रॉन्स के लिए कंटिन्यूटी इक्वेशन देखें, so that continuity equation for the electrons comes out something like this: dn upon dt is equal to dn del 2n, sorry, ये पार्शियल डेरिवेटिव होता है, मैं d लिख रहा हूं लेकिन आप ये समझिएगा कि पार्शियल ही है, ठीक है। सो dn d2n अपॉन dx2 प्लस gn माइनस rn, ठीक है। इट इज पार्शियल डेरिवेटिव, इतना आप सभी मैथ समझते हैं। हियर इट इज विद रेस्पेक्ट टू टाइम, हियर इट इज विद रेस्पेक्ट टू डिस्टेंस। इसी तरह से dp अपॉन dt इज इक्वल टू dp d2p dx2 plus gp minus rp. gp is generation rate of holes, rp is recombination rate of holes, gn is generation rate of electrons, rn is recombination rate of electrons, n is electron concentration which is function of x as well as t. So here n is function of x as well as t, x distance and t time। यहां पर भी p is function of x and time। मेरे और आपके बीच की म्यूचुअल अंडरस्टैंडिंग है, पूरा मैं बचने के लिए p लिख दे रहा हूं, बाकी इट इज pxt। Now you see my dear friends, this n can be written as n naught plus del p, right, where n naught is equilibrium concentration. Let us suppose it is a uniformly doped semiconductor. So for a uniformly doped semiconductor, this electron concentration is independent of distance as well as time. So it will remain constant. So if you differentiate this dn upon dt, dn naught upon dt, d del n upon dt, right? So this term will become 0. Similarly, if you differentiate with respect to x, this term will be 0. So this same equation can be modified like this. इसको हम लिख सकते हैं d del n, क्योंकि dn upon dt is nothing equal to d dt of del n. d del n upon dt is equal to dn d2 del n dx2 प्लस gn। व्हाट इज rn? rn अभी थोड़ी देर पहले लिखा था del n upon tau n. This you need to remember. This is the continuity equation for electrons which you need to memorize. ठीक। Similarly, p can be written as p naught plus del p. So p naught is constant with respect to distance as well as time. So if you differentiate, that will become 0, and you can write as d del p dt is equal to dp d2 del p dx2 plus gp minus tau p is rp is del p upon tau p. So this is your continuity equation for holes. You need to memorize it. Dear friends, here you see this del n is nothing but the function of x as well as t. So it will vary as x and t, and this del p is function of x as well as time. So these are the partial derivatives. राइट. सो आप चाहें तो डो भी लगा सकते हैं. पीपल यूज टू राइट लाइक दिस, डो डेल पी अपॉन डेल पी, लाइक दिस यू कैन राइट. एंड सिमिलरली डो टू समथिंग लाइक दैट. मैं उतना मैथ में नहीं जा रहा, यू नो ऑल दोज मैथमेटिकल थिंग्स. होप यू गॉट द पॉइंट विच आई वांट टू टेल, राइट. सो प्लीज यू राइट. हाँ, अब ये नहीं स्क्रीनशॉट लेकर के उसके बाद कहो कि अरे टीचर तो गलत पढ़ा रहा, मेडी जी के टीचर ने ब्लंडर कर दिया. नो, आई एम नॉट डूइंग ब्लंडर. दिस इज म्यूचुअल अंडरस्टैंडिंग बिटवीन मी एंड यू. दिस इज पार्शियल डेरिवेटिव विद रिस्पेक्ट टू टाइम, दिस इज पार्शियल डेरिवेटिव विद रिस्पेक्ट टू एक्स. ठीक, तो जब आप स्क्रीन वो कट कर रहे हो तो ये भी कट करके लगा दीजिएगा साथ में. ठीक है, वो आजकल वायरल करने का बड़ा शौक है लोगों में. हाँ, मानवी चौधरी करण सर, दिस इज एट इलेक्ट्रिक फील्ड 0. We are doing everything at low level injection, and under low level injection we have certain assumptions. What are the assumptions? I am writing. I am speaking, not writing. By default, you would be taking all the questions on low level injection. Under low level injection condition, electric field is considered to be 0. ठीक, सो थ्रू आउट द सेमीकंडक्टर यू विल एज्यूम इलेक्ट्रिक फील्ड इज 0. यानी जिस रीजन में आप कंटिन्यूटी इक्वेशन लगाएंगे वहां इलेक्ट्रिक फील्ड 0 होगी. पहला चीज. दूसरी चीज, इक्विलिब्रियम इलेक्ट्रॉन एंड होल कंसंट्रेशंस आर इंडिपेंडेंट ऑफ टाइम as well as distance. They are independent of time as well as distance. So वो भी मैंने यूज कर लिया. And then third, low level injection condition के लिए del n must be del n and del p must be very less than the majority carrier concentration. ठीक. So these three conditions must be satisfied. Then only you can use this equation. But by default, in all the questions which we are going to get in our examination, they are for the low level injection. So you need not to check that. अमन, बहुत क्वेश्चन मैंने क्लास में कराया है, इस पे बहुत अच्छे क्वेश्चन बनते हैं. ठीक है, 3 केसेस से बनते हैं. मैं तीनों केस समराइज कर दे रहा हूं अभी. देयर आर 3 केसेस एंड आई एम समराइजिंग ऑल दोस 3 केसेस. अब किसी एक को ले लेते हैं. लेट अस सपोज मैं सब कुछ इलेक्ट्रॉन के लिए डिस्कस कर रहा हूं. एक सिमिलरली एवरीथिंग वुड बी फॉर द होल्स, सो आई एम नॉट गोइंग टू रिपीट इट अगेन. ठीक, सो लेट अस सपोज आई एम डूइंग एवरीथिंग फॉर द इलेक्ट्रॉन्स. नाउ केस 1. So case 1, usually in this case the problem would be under no light condition in steady state. ठीक, so the key point for us is in the question you will be given steady state and there would be no light. You have to identify this condition from the statement of the question, या figure या diagram, कुछ ना कुछ help दी होगी. Steady state का मतलब है कि transients have been die out. If the transients have been die out, it means carrier concentration has become constant with respect to temperature. With respect to time. So if carrier concentration is constant with respect to time, so you can say that dN upon dt is equal to 0. Yeah, you can write it as d del n upon dt is equal to 0. And no light means Gn is equal to 0. If it is P, you are writing for holes, everything you can write del P and Gp like that. So I am taking only one example, that is electron, right? So these two conditions are given to you. Now you see your continuity equation. Now your continuity equation is d del n dt, and this is dn d2 del n dx2 plus gn minus del n upon tau n. Since you are in steady state, so in steady state concentration becomes independent of time. So now the del n is only function of x. Del n is only function of x, and this has become 0. So this term you will make 0. If you make this term 0 and no light means this term is also 0. In the question you are saying that no light. बट जरूरी नहीं है कि रिकॉम्बिनेशन रेट 0, क्योंकि कैरियर्स कैन बी इंजेक्टेड ड्यू टू एनी मैकेनिज्म, या पहले से इंजेक्ट हुए हैं और अभी खत्म नहीं हुए हैं, रिकॉम्बिनेशन हो रहा है. सो रिकॉम्बिनेशन रेट यू कैन नॉट से दैट कि नो लाइट देन रिकॉम्बिनेशन रेट इज 0. नो, रिकॉम्बिनेशन रेट डिपेंड्स अपॉन एक्सेस कैरियर. एक्सेस कैरियर्स कैन बी ड्यू टू एनी रीजन, राइट? सो रिकॉम्बिनेशन रेट you have to consider, right? But no light means no generation because of light, so Gn you can make 0. Now if you simplify this equation, it can be written as, ये 0 हो जाएगा, उधर लेकर के जाएंगे, so it is d2 del n dx2 is equal to del n dn and tau n, which can be written as del n and ln square. It is nothing but a second order differential equation. d2y upon dx2 is equal to, मैं इसको एक स्टेप आगे लिख देता हूँ, one more step we go like this, d2 del n dx2 is equal to del n upon ln square, right? It is what? It is a second order differential equation. d2y dx2 is equal to y upon some constant k. इस तरह की इक्वेशन को आपने खुद सॉल्व किया है. सो द जनरल फॉर्म ऑफ सॉल्यूशन फॉर सच काइंड ऑफ इक्वेशन इज del n of x is equal to a e to the power minus x by ln plus b e to the power x by ln, right? Now a and b are the values which a and b need to be determined from boundary conditions, need to be determined from one. अब आपको कुछ बाउंड्री कंडीशंस दी होंगी जिनकी मदद से आप डिटरमाइन करेंगे. In one particular case where the initial concentration is given to you, and let us suppose you have a very long semiconductor. So in a long semiconductor, if x tends to infinity, so if x tends to infinity, this term will become 0 and you can solve accordingly, right? So for that case, this solution comes out something like this: del n of x is equal to del n of 0 e to the power minus x by ln. लेकिन बेटा ये सिर्फ तब है जब आप कह रहे हो कि आपके पास एक लॉन्ग सेमीकंडक्टर है where x tends to infinity पर all the excess carriers are recombining and excess carrier concentration is becoming 0 and initial concentration x is equal to 0 पर दी हुई है. Then you can use this. Let us suppose I change this condition. I say that it is not long semiconductor and I give some value कि x is equal to 2l पर कुछ value है और x is equal to l पर कुछ value है. Then you need to calculate a and b accordingly and you need to solve that. So बड़ा conceptual question बनता है, but ज़्यादातर question इससे solve हो जाते हैं. So मैं उन सब concepts में नहीं जा रहा हूँ, उसके लिए आपको फिर continuity equation के मेरे जो क्लास के लेक्चर्स हैं वो देखने पड़ेंगे, क्योंकि बहुत डेप्थ में पूरे 6 घंटे हम लोग शायद एक क्लास पूरी लेते हैं ना, कितना एक क्लास लेते हैं, तो पूरी एक क्लास 6 घंटे हम लोग डिस्कस करते हैं कंटिन्यूटी इक्वेशन पर, तमाम सारे क्वेश्चन करते हैं. बट दिस इज द फर्स्ट केस एंड इन द फर्स्ट केस वेयर वी आर सेइंग दैट स्टेडी स्टेट बट नो लाइट. स्टेडी स्टेट नो लाइट के लिए जनरल सॉल्यूशन ये आएगा, ए और बी की वैल्यूज आप को निकालने के लिए कुछ हिंट दी होगी. अगर कुछ हिंट नहीं दी हुई है तो आप मान लेंगे कि स्टैंडर्ड केस के लिए सॉल्व किया गया. फॉर द स्टैंडर्ड केस यू हैव दिस सॉल्यूशन ऑफ del n x. चलिए प्लीज टेक द स्क्रीनशॉट. सो हम केस 2 की तरफ जाएंगे. आप स्क्रीनशॉट ले लीजिए, फिर केस 2 की तरफ जाएंगे. हाँ, मोस्ट वेलकम अमन सिंह जी. अमन सिंह जी, आपने मुझसे नहीं पढ़ा है क्या? कंटिन्यूटी इक्वेशन में डाउट है, क्लास नहीं की है मेरी. कोई बात नहीं, जो लोग मुझसे नहीं भी पढ़े हुए हैं सो दे कैन आल्सो रेफर दीज एंड यू कैन सेंड टू योर फ्रेंड्स. जो लोग मेडी जी नहीं कर पाए, क्लास नहीं कर पाए किसी भी कारण से, तो उनको भी मदद मिलेगी. चलिए केस 2. केस 2 जो होगा आपका, केस 2 में हमारे पास नो कंसंट्रेशन ग्रेडियंट एंड नो लाइट का केस मिलेगा. मोस्टली जो केस मिलेगा वो नो कंसंट्रेशन ग्रेडियंट एंड नो लाइट। ये आपको क्वेश्चन से समझना पड़ेगा, क्वेश्चन में कुछ ना कुछ हिंट दिया होगा जिसकी मदद से आप ये निकाल लेंगे। अब नो कंसंट्रेशन ग्रेडियंट, इसका मतलब क्या हुआ, d2 del n dx2 जीरो, ये टर्म जीरो, क्योंकि dy by dx जीरो होगा, स्लोप जीरो होगा, सो उसका सेकंड डेरिवेटिव भी जीरो होगा। और नो लाइट का मतलब gn जीरो होगा। इसी तरह p के लिए gp एंड d2 p का टर्म लिखेंगे। सो इफ आई राइट द कंटिन्यूटी इक्वेशन d del n dt, right, is equal to dn d2 del n dx2 plus gn minus del n upon tau n। एक चीज देखो मित्रों, यहां पर नो कंसंट्रेशन ग्रेडियंट, इट मींस इट इज इंडिपेंडेंट ऑफ डिस्टेंस। इफ इट इज इंडिपेंडेंट ऑफ डिस्टेंस, देन n is now the function of time only. It's not the function of डिस्टेंस, इट इज नाउ द फंक्शन ऑफ टाइम ओनली। ठीक, अब कैरियर कंसंट्रेशन अगर टेम्परेचर पर डिपेंड कर रही तो फिर हम स्टेडी स्टेट में नहीं है। सो वी आर इन ट्रांजिएंट्स, सो वी आर नॉट इन स्टेडी स्टेट। कहीं भी ये नहीं कह रहा कि स्टेडी स्टेट में। तो अगर क्वेश्चन में t इक्वल टू 0, t इक्वल टू 1 यानी टाइम डिपेंडेंट कैरियर कंसंट्रेशन कैलकुलेट करना है, ये भी एक पहचानने का तरीका है कि कैसे पहचानेंगे कि केस 2 है। सो यू कैन गो लाइक दिस, राइट। अब यहां से देखिए, ये 0 हो जाएगा और ये 0 हो जाएगा। ठीक, अब ये दोनों अगर 0 हो गया, सो आपके पास आ जाएगा d एंड del n dt इज इक्वल टू माइनस del n tau n। ठीक, ये फर्स्ट ऑर्डर इक्वेशन है। इसको क्या करिए आप, del n को इधर लेकर के आ जाइए, dt को इधर आइए, इंटीग्रेट कर दीजिए, सॉल्व कर लीजिए। सो ऑन सॉल्विंग यू विल गेट del n t is equal to a e to the power minus t upon tau n. You will get this kind of expression, right? अब ये a आपको निकालना पड़ेगा, a कांस्टेंट है जो आपको निकालना है। सो लेट अस सपोज t इज इक्वल टू 0 पर वैल्यू दी हुई है और आप वहां सॉल्व कर रहे हो। सो यू कैन राइट द जनरल एक्सप्रेशन del n ऑफ 0 e टू द पावर माइनस टी अपॉन टाउ n। ये तब लगाएंगे जब आपको n इज इक्वल टू 0 पर वैल्यू दी हुई हो। अगर n इज इक्वल टू 0 पर वैल्यू नहीं दी हुई है, लेट अस सपोज n इज इक्वल टू 2 सेकंड पर दी हुई है, आपको इसको सॉल्व करना पड़ेगा। और इसका सॉल्यूशन, अब मैं उसकी मैथमेटिक्स में नहीं जाऊंगा, फिर क्लास नोट्स देखिए, वहां पर दिया हुआ है। बट यूजुअली ज्यादातर क्वेश्चन में आपको इनिशियल कैरियर कंसंट्रेशन t इज इक्वल टू 0 पर दी होती है और किसी टाइम t पर मांग लिया जाता है, तो यू कैन यूज दिस रिलेशन। सो दिस यू कैन यूज। अगर इनिशियली आपको t इज इक्वल टू 0 पर नहीं दिया है, लेट अस सपोज सम t इज इक्वल टू 2 माइक्रोसेकंड पर दिया हुआ है एंड फिर कैलकुलेशन करना, देन प्लीज इस इक्वेशन को सॉल्व करिए और यहां से कैलकुलेट करिए, फिर लंबा क्वेश्चन बन जाता है। बट अगर स्टैंडर्ड दिया हुआ है तो यू कैन गो लाइक दिस। दिस इज द सेकंड केस, प्लीज गो फॉर इट। अच्छा, आपने सिर्फ मास्क पर, अमन सिंह कह रहे हैं सर मैंने पढ़ा है बट ईडीसी में सारे टॉपिक आपसे नहीं कर पाया था बिकॉज पहले गलत कोचिंग ली थी, देन आई फॉलो यू फॉर मास्क कैप। अरे कोई बात नहीं, कुछ भी गलत सही नहीं होता है, जब जागो तभी सवेरा। ठीक है, डोंट वरी। जीवन में कोई भी निर्णय गलत सही नहीं होते हैं, परिस्थितियां होती हैं, हम निर्णय ले लेते हैं और जब कभी हमें लगे कि गलत हो गया तो उसको करेक्ट कर लेना चाहिए डिसीजन। दैट्स सिंपल, लाइफ इज सिंपल, मेक इट सिंपल। Third case and then this chapter will be over. Case 3. Case 3. केस 3 कह रहा है कि स्टेडी स्टेट होगी और नो कंसंट्रेशन ग्रेडियंट। आपको ऐसे क्वेश्चन मिलेंगे जो स्टेडी स्टेट में होंगे और नो कंसंट्रेशन ग्रेडियंट। आपको क्वेश्चन के स्टेटमेंट से ये चीज समझना पड़ेगा, डायरेक्टली या इनडायरेक्टली ये मेंशन होगा। अब देखो, अगर स्टेडी स्टेट है तो del n अपॉन dt ये वैल्यू 0 होगी और नो कंसंट्रेशन ग्रेडियंट है, सो d2 del n dx2 ये वैल्यू 0 होगी। ठीक, अगर होल्स के लिए है तो सिमिलरली आप पी के टर्म में लिख लेंगे. सो यू कैन राइट नाउ डी del n dt is equal to dn d2 del n dx2 plus gn minus tau n, right? So this term 0, this term 0. Good. आप भगवान से मनाएं कि यही केस एग्जाम में पूछा जाए. मिनिमम कैलकुलेशन gn is equal to Rn and that is del n upon tau n. Here you will find del n value constant. It is independent of time as well as independent of distance. It will be constant because it is constant with respect to time, that's why this term is 0. It is constant with respect to x, that's why it is 0. So here del n is constant. This statement is saying what? Generation rate is equal to recombination rate, and that is valid under equilibrium condition. Sorry, under steady state, not equilibrium, under steady state. So here under steady state and no concentration gradient case, we have this generation rate is equal to recombination rate, which is del n upon tau n. Similarly, if it is for p type, then it will be Gp is equal to tau p, that is del p upon tau p. So you can go. This was all about chapter 1. चैप्टर 1 में शायद मैंने कुछ नहीं छोड़ा एक्सेप्ट हॉल इफेक्ट. हॉल इफेक्ट से क्वेश्चंस उतने ज़्यादा गेट में नहीं हैं तो मैंने स्किप कर दिया है उसे. ठीक, अब बताएं कौन सा चैप्टर लूँ. अलॉटेड टाइम तो ख़त्म हो गया, 1:45 बज रहे हैं, लेकिन पढ़ेंगे, कोई बात नहीं, देखते हैं कितना क्या. तो अगले 1 मिनट से कम समय में आप कमेंट करें कि मुझे पहले कौन सा टॉपिक लूँ. ठीक है, सो जो टॉपिक आप ज़्यादातर लोग कहेंगे पहले, मैं वही टॉपिक पहले स्टार्ट कर लूँगा. मैक्सिमम क्वेश्चन चैप्टर 1 से आते हैं. ठीक, अगर आपकी 10 नंबर की ईडीसी पूछी गई तो 5 से 6 नंबर चैप्टर 1 से आएगा और 3 से 4 नंबर में बाकी के सारा चैप्टर हो जाएगा. इट इज़ मोस्ट इंपॉर्टेंट टॉपिक. ठीक, ऐसा हम लोग गेस कर सकते हैं. बाकी पेपर बनाने वाले का मन करे वो किसी एक ही चैप्टर से उठा करके कर दे तो उस पर हम कुछ कह नहीं सकते. वी कांट क्लेम एनीथिंग, राइट, बट यूजुअली इट हैपेंस. कौन सा टॉपिक पहले लें? बड़ा मॉस कैप ज़्यादातर लोग मॉस कैप पर ही चल रहे हैं. चलो अच्छा, मॉस कैप शुरू करता हूं और फिर उसके बाद समय देखेंगे. अगर आपकी एनर्जी मेंटेन रही तो बाकी के चैप्टर भी करने की कोशिश करेंगे. लेट्स डू मॉस कैप. मॉस कैप में कंसेप्ट बहुत ज़्यादा नहीं है. ठीक है, सो फार्मूले देखते चलते हैं. बाकी उसकी थ्योरी के लिए पूरा 4 घंटे का एक वीडियो पड़ा हुआ है, तो मास कैप जल्दी से हो जाएगा. मास कैप इज इफ आई कैन अंडरस्टैंड इट इज ऑलरेडी अवेलेबल, लेकिन वो 4 घंटे का है तो लोग शायद उतना जाना नहीं चाह रहे हैं. सो क्विकली फॉर्मूले मास कैप के देख लेते हैं, उसके बाद दूसरे चैप्टर पर आ जाएंगे. ठीक है, सो आइए, नॉट ओनली मॉस कैप, मॉसफेट एंड मॉस कैप दोनों पर बात कर लेते हैं. सो पहले मॉस कैपेसिटर पर बात कर लेते हैं. मॉस कैपेसिटर, मॉस कैपेसिटर. ठीक है, बहुत जल्दी हो जाएगा ये. हाफ एन आवर से कम में ये खत्म हो जाएगा. 30 मिनट, हार्डली 25-30 मिनट में ये हो जाएगा. ठीक है, बहुत छोटा सा टॉपिक है. फटाफट करिए. हाँ, फटाफट कर रहे हैं, फटाफट कर रहे हैं. आपका आदेश सर आंखों पर. लेट अस सपोज हम एक पी टाइप सबस्ट्रेट ले रहे हैं. एवरीथिंग व्हिच आई एम गोइंग टू राइट दैट इज फॉर पी टाइप सबस्ट्रेट. सो इट इज पी टाइप सबस्ट्रेट. ठीक, पी टाइप सबस्ट्रेट. इस पर हम एक ऑक्साइड की लेयर डिपॉजिट करेंगे. दिस इज द ऑक्साइड. बेसिकली इंसुलेटर होना चाहिए, बट यूजुअली ऑक्साइड इज प्रेफर्ड, सो यू कैन से इट इज ऑक्साइड लेयर, टी ऑक्साइड. ठीक, और इसके ऊपर एक मेटल की प्लेट डिपॉजिट कर देते हैं. वैसे जरूरी नहीं है कि मेटल ही हो, heavily doped semiconductor भी हो सकता है, but that heavily doped semiconductor also function like metal, and then it becomes. This terminal is known as gate. In short, I will be writing as G. ठीक. So this metal is known as gate metal. It is gate metal. It is gate metal. And this is your insulator, which is nothing but oxide, right? And this is your semiconductor. That's why it is known as MOS, metal oxide semiconductor. Metal oxide semiconductor. This terminal is known as body terminal या back terminal, usually represented as B. Usually this B is kept at ground potential. ठीक, बैंड बेंडिंग डायग्राम वगैरह मैं नहीं बना रहा हूं इसका अभी, क्योंकि that will take lots of time. Few things I would like to tell you here. This gate metal can be replaced by heavily doped polycrystalline silicon. So heavily doped polycrystalline silicon या high conductivity polycrystalline silicon can also be used here. High conductivity polycrystalline, high conductivity polycrystalline silicon can also be used. But since it is heavily doped, so it will be degenerate silicon, and that will be functioning like metal. So every working would be same. You need not to worry about that. You will consider it like metal. So even if it is semiconductor, you will treat it like metal. One important point which I would like to discuss here, I have to discuss few definitions. Let us suppose it is vacuum energy level. It is vacuum energy level. And let us suppose it is the Fermi energy level of it is Fermi energy level of metals. In metals, you need not to represent valence band and conduction band, because metals have valence band and conduction band overlapping. So you just need to represent Fermi level. Let us suppose I am drawing this band diagram at 0 Kelvin. So at 0 Kelvin, Fermi level is that level below which all the energy states are occupied by the electron and above which all the states are empty. So you can say that the electron which is having highest energy, that is equal to Fermi energy electron in metals, roughly. Now if you want to take this electron from metal surface to vacuum, so you have to give some energy. That amount of energy required to bring an electron from metal surface to vacuum, that is known as work of function. So work of function is nothing but this difference of energy. From here to vacuum, you need to take this electron, and for that purpose you need to supply some energy, and that energy is known as work of function. So I am representing it as Q phi m. ठीक, अलग अलग बुक्स अलग अलग नोटेशन रिप्रेजेंट करेंगे, और मेरे ये सारे नोटेशंस लोकल हैं. हो सकता है मैं कहीं phi m से कुछ और रिप्रेजेंट करूं, यहां कुछ और किया हूं. सो दीज आर नॉट यूनिफॉर्म. एवरी हेडिंग में आपको ये समझना होगा कि नोटेशन क्या कह रहे हैं. सो दिस Q phi m इज वर्क फंक्शन ऑफ मेटल. Work function of metal. It is the amount of energy required to bring an electron from the metal surface to vacuum. Work function of metal. Obviously ये electron volt में होगा. Q phi m is in electron volt. Let us suppose आपको volt में दिया है. Suppose कह रहा है कि work function is 4 volt. So Q से multiply कर दीजिए, एनर्जी के टर्म में क्या हो जाएगा, 4 electron volt. If it is given 4 electron volt and you want just for this phi m, so Q से डिवाइड कर दीजिए. That you know, all those things you know. Let us suppose हमारे पास कोई एक सेमी कंडक्टर मटीरियल है. Suppose this is our semiconductor. It is EC and it is EV, right? And it is our intrinsic energy level EI. Suppose मैं N type ले लिया, यहाँ हम लोग P ले रहे हैं तो P type से ही देख लेते हैं. Similarly, everything would be for N type also. So if it is P type, then the Fermi energy level would be somewhere here. It is EF, right? अब एक चीज देखिए, वर्क फंक्शन की डिफिनेशन सेम होगी. इट इज अ डिफरेंस फ्रॉम फर्मी एनर्जी लेवल टू वैक्यूम. ठीक, सो चाहे वो मेटल हो या सेमीकंडक्टर हो, सो दिस वर्क फंक्शन इज सेम. दिस इज Q phi S. Q phi S is work function of semiconductor. This is work function of semiconductor. Work function of semiconductor. Work function of semiconductor, right? And here you are given one more parameter, the difference between EC and vacuum. This is Q chi S. This Q chi S is known as electron affinity of semiconductor. इस पर गेट में क्वेश्चन बने हैं, ठीक, इलेक्ट्रॉन एफिनिटी ऑफ सेमीकंडक्टर. सो कंडक्शन बैंड और बैलेंस, कंडक्शन बैंड और वैक्यूम के बीच के डिफरेंस को इलेक्ट्रॉन एफिनिटी कहेंगे और फर्मी लेवल और वैक्यूम के डिफरेंस को वर्क फंक्शन कहेंगे. ठीक, लेट अस सपोज एन टाइप होता तो ये क्यू काई एस सेम रहता, लेकिन फर्मी लेवल यहां आ जाता तो क्यू फाई एस चेंज हो जाता. सो फॉर द सेमीकंडक्टर इलेक्ट्रॉन एफिनिटी इज कांस्टेंट बट वर्क फंक्शन में चेंज, एंड दैट विल डिपेंड अपॉन टाइप ऑफ डोपिंग. यदि एन टाइप है तो यहां कहीं फर्मी लेवल होगा, उसका डिफरेंस वर्क फंक्शन होगा. अगर पी टाइप है तो यहां कहीं फर्मी लेवल होगा, उसका डिफरेंस होगा. इवन इफ यू अप्लाई वोल्टेज, then quasi Fermi level will come into the picture, and if position of Fermi level will change, then work function will change. So for semiconductor, work function is not a constant quantity. It is not a material parameter. The material parameter is Q chi s, which is constant, right? But if you talk about metals, in metals electron concentration more or less remains same, it doesn't change, right? So if electron concentration is more or less same, then Fermi energy level is more or less same, and if Fermi energy level is same, then this Q phi m will remain constant. So for metals work function is constant, right? So this concept is utilized somewhere in PN junction band diagram वगैरह, पता नहीं है वहां तक कर पाएंगे, आज नहीं कर पाएंगे, लेकिन आपको जानना चाहिए. आइए, यहां पर कई बार ये क्यू फाई एस कैलकुलेट करना पड़ता है क्वेश्चन में, और यहीं पर क्वेश्चन में बच्चे फंस जाते हैं. जैसे आपको अगर पॉलीक्रिस्टलाइन सिलिकॉन दे दिया, ठीक है, अब पॉलीक्रिस्टलाइन सिलिकॉन दे दिया, हैवी डोप्ड सिलिकॉन दे दिया, ठीक है. सो हैवी डोप्ड सिलिकॉन में और आपको मेटल की जगह पर वो यूज कर रहे हैं, तो आपको क्यू फाई एम से मतलब है. क्यू फाई एम इज व्हाट, ईएफ माइनस ईबी. सो वैक्यूम से ईबी के बीच का, ईएफ के बीच का डिफरेंस कैसे कैलकुलेट करेंगे, आप उसका बैंड डायग्राम ड्रॉ करिए और ये कैलकुलेट करने की कोशिश करिए, ठीक है. तो कोई भी हो, पॉलीक्रिस्टलाइन सिलिकॉन हो या कुछ भी हो, आप कर सकते हैं. इस तरह के क्वेश्चन मैंने टेस्ट सीरीज में कराए भी हैं, मैंने वीडियो रिकॉर्डिंग में उसको समझाया भी है. आइए जरा यहाँ मैं अगर क्यू फाई एस लिखना चाहता हूं इस केस के लिए तो कैसे लिख सकता हूं, जरा इस बैंड डायग्राम से देखिए. क्यू फाई एस, क्यू फाई एस क्या है, दिस प्लस ई आई, मैं मान रहा हूं कि बैंड गैप के हाफ पर है, मिड पर है, दिस इज ई जी बाई टू एंड दिस इज ऑल्सो ई जी बाई टू, ई जी बाई टू, राइट. सो आई कैन से दैट कि दिस क्यू फाई एस को अगर मैं लिखना चाहूं तो क्यू काई एस प्लस ई सी माइनस ई आई, दैट इज ई जी बाई टू, प्लस दिस ई आई माइनस ई एफ, राइट. सो आई कैन राइट क्यू फाई एस इज क्यू काई एस प्लस ई जी बाई टू प्लस this plus ई आई माइनस ई एफ, EI minus EF, and these values you can calculate from chapter 1. That's why chapter 1 is king, right? अब ये सारी वैल्यू आप chapter 1 से कैलकुलेट कर सकते हैं. ठीक है. सो यहां से आप कर, अब यहां एक कंसेप्ट हमें जरूरत होती है, दैट इज मेटल सेमीकंडक्टर वर्क फंक्शन डिफरेंस. metal semiconductor work function difference, work function difference, metal semiconductor work function difference. This is represented as Q phi ms, that is Q phi m minus Q phi s. This is your Q phi ms. If you want to cancel Q, you want to write in terms of voltage, then phi ms is equal to phi m minus phi s. Phi m minus phi s. Friends, instead of memorizing, try to understand the concept. It is the difference of metal work function minus semiconductor work function. लेट्स सपोज मेटल, अच्छा अब इसमें लोग ना, मैं देखता हूं कि तमाम सारी किताबों से तमाम सारे कंसेप्ट कि इफ पॉलीक्रिस्टलाइन सिलिकॉन इज यूज्ड देन memorize this relation, if that, memorize lots of absurdities people have done, right? Don't go for that. You need to bother ki rather than metal, let us suppose I use polycrystalline silicon, so try to calculate EF minus E vacuum from for that polycrystalline silicon, or you can calculate Q phi m. आप पॉलीक्रिस्टलाइन एन टाइप सिलिकॉन होगा, क्यू फाई एम आपका यहाँ से, आप यूजुअली पॉलीक्रिस्टलाइन एन टाइप सिलिकॉन यूज करते हैं। सो यहाँ ई एफ होगा, ई एफ माइनस ई आई आपको कैलकुलेट करना है, जैसे मैंने इसके लिए कैलकुलेट किया, ई एफ माइनस ई वैक्यूम कैलकुलेट करना है, जैसे मैंने इसके लिए कैलकुलेट किया वैसे ही आप इसके लिए कैलकुलेट कर सकते हैं। सो क्यू फाई एम की जगह पर आप वो वैल्यू पुट कर देंगे, क्यू फाई एस की जगह ये वैल्यू पुट कर देंगे, आप सिंप्लीफाई कर लेंगे, आपको फाई एम एस मिल जाएगा, ठीक। सो प्लीज फर्स्ट यू गो फॉर दीज रिलेशनशिप्स एंड देन वी वुड बी writing, yeah, summarizing some formulas. मैंने सुबह तो ठंड थी तो काफ़ी कपड़े पहन लिया, अब थोड़ा मौसम ठीक हुआ है तो गर्मी लग रही है। डन डन, ठीक है। आइए नाउ द नेक्स्ट कंसेप्ट इज फ्लैट बैंड वोल्टेज। फ्लैट बैंड वोल्टेज, फ्लैट बैंड वोल्टेज, it is the voltage required to achieve flat band condition. Flat band condition is the condition when mass capacitor does not have any stored charge, or you can say that the bands are flat, means there is no electric field, right? So in that case, what is the flat band voltage? VFB is equal to phi ms, phi m minus phi s, ठीक है, phi ms minus QSS upon C ox. What are these terms? Phi ms, you know. What is QSS? QSS is trapped oxide charge per unit area. Trapped oxide या trapped charge in oxide layer. Trapped charge in a trapped charge per unit area लिख लीजिए, because it is per unit area. Trapped charge per unit area in oxide layer. Trapped charge per unit area in oxide layer. C ox is oxide capacitance per unit area. Oxide capacitance per unit area. Capacitance per unit area. This is oxide capacitance per unit area. Now this C oxide is nothing but epsilon oxide upon T oxide. What are these parameters? Epsilon oxide is permittivity of oxide. Permittivity of oxide. And T oxide is thickness of oxide layer. Thickness of oxide layer. Oxide layer, right? This C oxide would be used in throughout the entire discussion. Let us suppose there is no trapped charge. If there is no trapped charge, then QSS will be 0 and VFB is equal to phi ms. Suppose you want ideal mass capacitor. So in ideal mass capacitor, phi m minus phi s is also 0 and there should not any trapped charge. So for an ideal mass capacitor, flat band voltage should be equal to 0. So for a ideal mass capacitor, note कर लेते हैं यहाँ, अगर क्वेश्चन में लिखा आइडियल मास कैपेसिटर, फॉर एन आइडियल मास कैपेसिटर, आइडियल मास कैपेसिटर, फॉर एन आइडियल मास कैपेसिटर VFB is equal to 0. This is 0. ठीक है जी, this is 0. Please note on this. Very good, याद है तुम लोगों को. ये चल नहीं रहा मेरे तरफ, फिर से बफरिंग तो नहीं हो रही, देख लो। आ गया। Done? Okay. Now, let's define threshold voltage. I'm not following the sequence which I have followed in the class क्योंकि उतनी डेप्थ में नहीं जा सकते हैं. So, threshold voltage. I will represent it as BTH. Some of the books represent it as BT. So, notation is local. जैसा मैंने कहा, मेरा अपना है. What is threshold voltage? It is the voltage required to get the inversion layer basically. प्रॉपर डिफिनीशन इसकी दिया जाए तो आप कह सकते हो, अब बैंड डायग्राम ड्रॉ करो. मैं थ्रेशोल्ड वोल्टेज पर बैंड डायग्राम ड्रॉ कर रहा हूं. अच्छा, एवरीथिंग व्हिच आई एम मेंशनिंग फॉर मास कैपेसिटर ऑन पी टाइप सबस्ट्रेट. सिमिलरली थिंग्स कैन बी चेंज्ड फॉर एन टाइप आल्सो. उसके लिए आप वो 4 घंटे का लेक्चर देखिए. बट मोस्टली क्वेश्चंस, 99% क्वेश्चंस यू विल गेट मास कैपेसिटर ऑन पी टाइप सबस्ट्रेट. दैट्स व्हाई आई एम डूइंग एवरीथिंग फॉर पी टाइप सबस्ट्रेट. लेट अस ट्राई टू ड्रॉ द बैंड डायग्राम. कैसे आया, क्या हुआ, उस सब के लिए रेगुलर क्लास अभी जस्ट देखिए. Like this, right? And it is oxide region, right? So this is conduction band EC and this is valence band EB. ये valence band है. ये इससे पहले आपके पास मेटल है, दिस इज मेटल. इसके बाद आपके पास सेमीकंडक्टर है, दिस इज सेमीकंडक्टर, एंड दिस वन इज योर ऑक्साइड लेयर. ठीक. हियर मेटल फर्मी एनर्जी लेवल इज समवेयर हियर, EFM, metal Fermi energy level. And since you have applied voltage, so you are not at equilibrium, so the Fermi level of metal and semiconductor will be different. So let us suppose it is the Fermi energy level of semiconductor, and this is the boundary where we are interested. इसके बाद का ये जो रीजन है ये बल्क P टाइप है. And if you recall, in bulk semiconductor nothing changes, so we are not interested there. Here what happened, EC is like this. In bulk it will remain same as earlier, it is EI and it is EB, right? Now on the application of voltage, these energy levels will start bending, and this bending happens something like this. I'm unable to make properly. Let's make it again. First to make EC, and everything will be done accordingly. So we are having, this is EI, and on the application of voltage it will keep on bending, and it bends like this. Bends like this. So let us suppose it goes like this, right? Similarly, EC and EI are parallel, so EC would be like this and EI would be also like this. EI would be like this, right? थोड़ा सा इसका और ऊपर बना लेते हैं, just to avoid any confusion. EC कर लेते हैं. You see, my dear friend, this total amount of band bending, let us suppose bulk is at 0 potential, so I am assuming bulk is at ground potential, so it is 0 volt. So this total amount of band bending represents a potential that is known as surface potential. So this phi s is known as surface potential. यहाँ define कर देते हैं, इधर कर देते हैं, surface potential. Surface potential, यहाँ ये फर्मी से कोई लेना देना नहीं, फर्मी पोटेंशियल नहीं है ये, ठीक है। वो क्यू फाइएस से हम इलेक्ट्रॉन का फर्मी लेवल भी शो करते हैं। अच्छा, इसमें अवॉइड करने के लिए, कोई कंफ्यूजन अवॉइड करने के लिए क्या करूं, इसको किसी दूसरे नोटेशन से कर देता हूं। लेट्स सपोज आई डू लाइक दिस, लेट्स सपोज आई डू लाइक दिस। नहीं, मैं यही करूंगा क्योंकि मैं नोट्स में भी यही कराया हुआ हूं, ठीक। इट इज सरफेस पोटेंशियल, इट इज डिफरेंट देन द वर्क फंक्शन ऑफ सेमीकंडक्टर, इट्स नॉट वर्क फंक्शन ऑफ सेमीकंडक्टर, ठीक है। नोटेशंस मेरे लोकल हैं, समझिएगा इस हेडिंग में केवल। क्यू फाइएस इज व्हाट, इट इज सरफेस पोटेंशियल। सरफेस पोटेंशियल इज व्हाट, पोटेंशियल करेस्पॉन्डिंग टू द टोटल अमाउंट ऑफ बैंड बेंडिंग ऑन द बैंड डायग्राम। बैंड डायग्राम में जो टोटल अमाउंट ऑफ बैंड बेंडिंग है उसके करेस्पॉन्डिंग जो पोटेंशियल है दैट इज नोन एज सरफेस पोटेंशियल। यहां से दिख रहा होगा, यहां से लेकर के यहां तक का पोटेंशियल दैट इज सरफेस पोटेंशियल, ठीक। नाउ आई डिफाइन वन मोर क्वांटिटी हियर, दिस इज Q phi B, मैं क्लास में इसे Q phi F कहता हूं, Q phi F, राइट। सो दिस Q phi F इज फर्मी पोटेंशियल, इसका भी वर्क फंक्शन से कोई लेना देना नहीं है, ठीक है। सो Q phi F इज E माइनस EI माइनस EF इन बल्क P टाइप सेमीकंडक्टर, इन बल्क P टाइप, राइट। सो इन बल्क P टाइप EI माइनस EF, आप इसको कैलकुलेट कर सकते हैं। कैसे कैलकुलेट कर सकते हैं? इन बल्क P टाइप P नॉट इज इक्वल टू Na एक्सेप्टर कंसंट्रेशन दैट इज Ni e टू द पावर EI माइनस EF अपॉन KT, and from this you will have Q phi F which is EI minus EF, इसकी जगह पुट करेंगे, so it comes out as KT ln Na upon NF. That you can calculate, right? Depends upon the doping of the substrate. So phi F, which is popularly known as Fermi potential, KT by Q. KT by Q is VT, thermal voltage, Na upon Ni, where Na is doping of the substrate and Ni is carrier concentration. ठीक, so phi F आपके पास available है because doping you know, then you can calculate this Fermi potential, right? This surface potential if become 2 phi F, if phi S becomes equal to 2 phi F, then the applied gate voltage is equal to the threshold voltage. Let us suppose we calculate gate voltage, applied gate voltage Vg is equal to flat band voltage plus depletion charge create करने के लिए voltage, so this plus not 2 phi F, this is surface potential phi S, ठीक, this is the voltage. When you have gate voltage less than the threshold voltage, let us suppose at any arbitrary gate voltage we have this relationship, ठीक? This Q depletion can be calculated as, I am writing the expression for that, this can be calculated as Vg is equal to VFB plus under root 2Q Na epsilon S phi S upon C ox plus phi S. This is the applied gate voltage. To get the surface potential phi S, applied gate voltage, to get surface potential phi S, ठीक। सरफेस पोटेंशियल phi S पाने के लिए जो अप्लाइड गेट वोल्टेज है वो आपको इतना चाहिए। अब अगर सरफेस पोटेंशियल 2 phi F के बराबर हो जाएगा तो जो वोल्टेज होगा उसे थ्रेशोल्ड वोल्टेज कहेंगे। सो इफ phi S इज इक्वल टू 2 phi F, then Vg is equal to VTH, where VTH is threshold voltage. So threshold voltage will become flat band voltage plus under root. अब now phi S is 2 phi F, so 2 to 4. So it is Q Na epsilon S phi F upon oxide capacitance plus 2 phi f. This is the threshold voltage, expression for the threshold voltage. This is threshold voltage, very important parameter. So many questions you will get on threshold voltage, calculation of threshold voltage, right? यहाँ कुछ चीजें देखिए, यदि हम सबस्ट्रेट की डोपिंग बढ़ा रहे हैं, if we increase Na, what will happen? If we increase Na, phi f will increase, this term will also increase, this term increase, BTS will increase. BTS will increase, right? If we increase oxide thickness, so T ox बढ़ा रहे हैं, T ox बढ़ा रहे हैं तो C ox क्या हो जाएगा, घट जाएगा, क्योंकि C ox is epsilon ox upon T ox, और C ox घट जाएगा तो ये entire term बढ़ जाएगा, so BTS will increase. BTS will increase. Let us suppose हम QS trapped charge जो introduce किए हैं वो बढ़ा रहे हैं, QSS is what, trapped charge. So अगर trapped charge बढ़ेगा तो आप BFB देखो, BFB is what, BFB is equal to phi ms minus QSS upon C ox. So if you are increasing QSS, then BFB is decreasing, and if BFB is decreasing, then threshold voltage is decreasing, right? What my conclusion is, by increasing the substrate doping concentration, you can increase the threshold voltage. By increasing the oxide thickness, you can increase the threshold voltage. If you are introducing trapped charges, then threshold voltage is decreasing, right? These are the some points, so which please you note down, then we would be going for the further discussion. कहाँ से? हाँ, इसका screenshot लीजिए. Take the screenshot of this. Is it done? Let's go for this. Done? आप लोग हैं या भाग गए? भाग गए हो तो हम भी चलें, भूख भी लग रही है. अरे सोनम, आप एनआई से एनआई जनरली नोन होता है हमें, आप एनबी से कैलकुलेट करना चाहते हैं एनबी से कर लीजिए. यूजुअली एनआई इज नोन टू अस, सो दैट्स व्हाई वी डिफाइन एवरीथिंग इन टर्म्स ऑफ एनआई, राइट? और वैसे भी हमें यहाँ EF माइनस EI का डिफरेंस चाहिए. अगर आपको EF और EB के बीच का डिफरेंस चाहिए होता तो NB लेकर के चलते हैं, ठीक? सो अननेसेसरी यू आर गेटिंग कंफ्यूज्ड. व्हाट आई नीड हियर, EF माइनस EI. सो EF माइनस EI कैन बी इजीली कैलकुलेटेड इन टर्म्स ऑफ NI, राइट? अब एक चीज क्वेश्चन के लिए एक बड़ी अच्छी चीज आपको बताऊं. रिक्वायर्ड गेट वोल्टेज BG इज इक्वल टू BFB plus under root 2Q Na epsilon S, where epsilon S is permittivity of semiconductor, and phi S, that is surface potential, C ox plus phi S. It is when if BG is less than threshold voltage and phi S is less than 2 phi f and xd is less than xd max. What is xd? Xd is nothing but the depletion region width in the semiconductor. This is your xd. Xd is depletion region width. Depletion रीजन विड्थ, दिस इज xt, ठीक है। अब एक चीज देखिए, सो यदि आपके पास, आपको गेट वोल्टेज कैलकुलेट करना है, ठीक, but you are below the threshold voltage, then use this relationship, and in that case your xd would be less than the xd max. How can you calculate xd? You can calculate xd is equal to under root 2 epsilon s by q 1 upon na into phi s. This is the depletion width you can calculate, depletion region width you can calculate xd by this relationship, ठीक है। एक चीज, here you see my dear friends, let us suppose you are at bg greater than bth. So if you are at bg greater than bth, if bg is greater than or equal to bts, then phi s will become 2 phi f. There is no further increase in phi s, and in that case xd will become xd max. So उस केस में आपके पास maximum depletion region width मिलेगी. So for any voltage which is greater than, applied gate voltage which is greater than or equal to bth, then xd will be maximum, that will not change. So here xd max, इस पर बहुत क्वेश्चन बनता है, it will become phi s की वैल्यू क्या पुट कर देंगे, 2 phi f, so it will become 4 epsilon by q 1 upon na into phi f, and phi f you have calculated. एग्जाम में एक बार इसे phi b से लिखा हुआ था, बल्क पोटेंशियल phi b, so once in exam it was written as phi b. So notations local है, आप मतलब समझिए, it is the difference of ei minus ef represented in bold in bulk semiconductor, right? So you go for this. Please take the pick up this part. Now let's suppose he asks you depletion charge per unit area. Sometimes he asks depletion charge per unit area. If he is asking like this kind of question, so what is this Q depletion? You have Na acceptors per unit volume, each acceptor is having minus Q charge, so it is minus Q into Na, coulomb per centimeter cube, but you need coulomb per centimeter square, so multiply with the depletion region width. So minus Q Na into xd. xd you have calculated from this relationship, you can put this relationship and you can calculate depletion charge per unit area. उसके लिए voltage magnitude of Q depletion upon Cox that you can calculate, वो पीछे मैंने लिखा ही था, ठीक। अब एक क्वेश्चन और थोड़ा सा जो बनता है देख लेते हैं इस पर, एंड देन उसके बाद CB डायग्राम देख लेंगे, फिर ये टॉपिक कवर हो जाएगा. सो इफ आई गो फॉर द नेक्स्ट पार्ट जहां से क्वेश्चन बनता है, लेट अस सपोज दिस इज ऑक्साइड रीजन, this side is oxide, right, and this is semiconductor. Sometimes what he do, he ask the electric field in oxide or semiconductor, right? So if you calculate the electric field here, this is E oxide, and at this surface जो electric field होगी उसे मैं ES से डिनोट कर रहा हूँ. सेमीकंडक्टर के इस रीजन में जो इलेक्ट्रिक फील्ड वेरी करेगी वो x के साथ वेरी करेगी, ठीक है. सो हमें एज अ एक्स फंक्शन मैं लिखाऊं, वो भी लिखाऊं, जरूरत है, चलो लिखा देते हैं वो भी. लेट्स सी द इलेक्ट्रिक फील्ड इन दिस रीजन. So the electric field here in the semiconductor is as a function of x, so E of x. ये बल्क है, बल्क में कोई इलेक्ट्रिक फील्ड नहीं होगी, बल्क में इलेक्ट्रिक फील्ड जीरो है, ठीक, डिप्लीशन रीजन में जो इलेक्ट्रिक फील्ड है, इलेक्ट्रिक फील्ड इन द डिप्लीशन रीजन, दिस इज इलेक्ट्रिक फील्ड इन द डिप्लीशन रीजन, इलेक्ट्रिक फील्ड इन द डिप्लीशन रीजन। मैं पूरा डायग्राम नहीं बना रहा हूं, ऊपर बना हुआ है, आप देख सकते हैं, डिप्लीशन रीजन। ठीक, सो ये पॉइंट क्या है, एक्स डी, और इस पॉइंट को मैं x इज इक्वल टू 0 मान रहा हूं, ये पूरा x एक्सिस। सो e ऑफ x कैन बी written as a function of x, it can be written as minus q na upon epsilon s, minus q na upon epsilon s, x minus xt। xd you can calculate, हम लोग पीछे देख चुके हैं। ठीक, this is the electric field variation with x in the semiconductor। The electric field is varying something like this. It is basically y is equal to mx plus c but with negative slope। और xd पर इसकी वैल्यू क्या हो जाएगी, 0 हो जाएगी। x is equal to xd पुट करिए, it will become 0। क्यों? क्योंकि xd पर you will reach into the bulk semiconductor and bulk is neutral, उसमें कोई electric field नहीं है। Now sometimes he used to ask कि what is the electric field in the oxide। So ES मान लेता हूं मैं, surface पर electric field है। So ES is electric E of x at x is equal to 0। So basically this is electric field in the semiconductor, electric field in the semiconductor, in the semiconductor at oxide semiconductor interface, oxide semiconductor इंटरफेस, इंटरफेस मतलब जहां दोनों मिल रहे हैं, वहां पर जो इलेक्ट्रिक फील्ड सरफेस पर। ठीक, तो इस ES की मदद से हम लोग एप्सिलॉन EX निकाल सकते हैं। यू नो EMT का एक कंसेप्ट हम यूज करेंगे इलेक्ट्रोमैग्नेटिक थियरी का। दिस इज अ बाउंड्री बिटवीन टू डिफरेंट मीडियम, वन मीडियम इज ऑक्साइड एंड अनदर मीडियम इज सेमीकंडक्टर। सो इलेक्ट्रिक फ्लक्स वेक्टर मस्ट रिमेन कांस्टेंट एट बाउंड्री। इलेक्ट्रिक फ्लक्स इज व्हाट, d ऑक्साइड हियर and it is ds here। ठीक, so electric flux vector should remain constant throughout the boundary। So if I use this concept, then d oxide must be equal to ds। So it can be written as epsilon r oxide into epsilon naught, this is permittivity of oxide, into E oxide is equal to epsilon r, that is relative permittivity of semiconductor, epsilon rs epsilon naught into es, not the entire electric field, at the surface, क्योंकि surface पर ही ये flux constant है, at the boundary हम लोग बात कर रहे हैं पूरे material में। So from this if you see E oxide is equal to epsilon naught cancel हो जाएगा, epsilon rs epsilon r oxide into es। This is the electric field in the oxide। ठीक, you can calculate with this relation electric field in the oxide। If I plot these two, एक बड़ा interesting curve मिलेगा। पहले इतना लिख लें तो फिर इसको plot करते हैं। You please note down this, then I will be plotting this। Yes, ग्राफ आप ग्राफ अभी बनाएंगे सोनम। पोटेंशियल प्रोफाइल अगर निकालना भी है अमन तो क्या कर सकते हो, पोटेंशियल इज व्हाट, इलेक्ट्रिक फील्ड प्रोफाइल आपको बता दिया। पोटेंशियल प्रोफाइल के लिए आप उसको इंटीग्रेट कर लीजिए, E इज इक्वल टू माइनस डी फाई बाई डी एक्स, सो फाई इज इक्वल टू माइनस ई डॉट डी एक्स। सो जो इलेक्ट्रिक फील्ड वेक्टर है उसी को आप माइनस साइन के साथ ई डॉट डी एक्स कर दीजिए, इंटीग्रेट कर दीजिए, मिल जाएगा आपको। Is it done? Right. If you draw the curve for the electric field, let us suppose it is x, right? And we are drawing like this. This is the electric field. Okay. This is your x is equal to 0. So before this you have oxide and here you have semiconductor. right? So this line is basically denoting x is equal to xd, right? So it is bulk p type, it is bulk p. So depletion region is only here. Now you see electric field is constant here, E oxide, because ES value is constant and other things are constant, so it is E ox. Then there is a sharp decline, discontinuity. So electric flux is constant, but electric field is not constant, right? So electric flux is continuous, sorry, not constant, sorry, extremely sorry. Electric flux is continuous across the boundary, but it's not necessary that electric field is continuous, right? So this value is ES, and if you go, sorry, थोड़ा और नीचे ले आते हैं, इसे बनाने में इजी होगा. ES. ठीक है? So the curve would be something like this, and here the electric field in the bulk region would be 0. We are assuming that bulk is at 0 potential. My dear friends, the area under this curve will give you surface potential. Surface potential is nothing but area under this curve. Electric field profile. Surface potential is what? Total amount of band bending in the semiconductor at the interface. So total amount of band bending would be corresponding to this electric field. So you can have phi s. That phi s is area under the curve. So area under the electric field curve 1 by 2 into ES into xt. This is the phi s, right? Surface potential can also be calculated like this, area under the electric field curve. अशोक इज राइटिंग कॉम्प्लिकेटेड है थोड़ा सा, हाँ थोड़ा सा कॉम्प्लिकेटेड है. नहीं, वो मैंने एक डिटेल्ड वीडियो है 4 घंटे का, वो देखिएगा, लगभग 4 आवर्स का एक वीडियो यूट्यूब पर पड़ा है, मेरी जी यूट्यूब चैनल पर, तो चीज़ें और भी क्लियर हो जाएंगी. मैं अभी यहाँ तो सिर्फ क्वेश्चन पॉइंट ऑफ व्यू से कि जहाँ से क्वेश्चन बन सकते हैं वो करवा दे रहा हूँ. पोटेंशियल इज व्हाट? एरिया अंडर द इलेक्ट्रिक फील्ड कर्व. सो वहाँ से कैलकुलेट कर लिया. डन. चलिए आगे चलते हैं. Shall we go ahead? Good. Now next heading, inversion charge carrier density. Inversion charge carrier density. This is basically nothing but inversion charge per unit area. Inversion charge per unit area. It is inversion charge per unit area. So Q inversion is equal to magnitude, right? This is oxide capacitance into gate voltage minus threshold voltage. This you can use. This Q inversion can be written as N into Q, magnitude of electronic charge. This is equal to C ox, and it is Vg minus Vth, right? So this one, where N is number of inversion charges per unit area, number of inversion charges per unit area, inversion charges per unit area, per unit area. This is N. ठीक, इस पर भी गेट में काफी क्वेश्चन पूछे गए, so please do it. Take the screenshot. Good. Done. Okay. अरे यार ये तो स्लाइड ही Now capacitance versus voltage characteristic, capacitance वोल्टेज या गेट वोल्टेज लिख लो, ज़्यादा बेहतर होगा, गेट वोल्टेज characteristics for mass capacitor fabricated on p-type substrate. I am discussing everything for p-type substrate. Fabricated on p-type substrate. Fabricated on p-type substrate. Let's see. इसे CB कैरेक्टरिस्टिक भी कहते हैं, कैपेसिटेंस वर्सेस गेट वोल्टेज, यानी C वर्सेस BG कैरेक्टरिस्टिक. बहुत इंपॉर्टेंट, बहुत क्वेश्चन पूछे जाते हैं. ठीक है, हैव अ लुक. दिस इज C, बेसिकली कैपेसिटेंस पर यूनिट एरिया, कैपेसिटेंस पर यूनिट एरिया. अगर एरिया आपको दिया है तो मल्टीप्लाई कर दो, फैरेड में हो जाएगा, अदरवाइज इट इज फैरेड पर सेंटीमीटर स्क्वायर. एंड दिस इज योर BG. This BG is gate voltage, applied gate voltage. Here I am making some segments. Let us suppose this is flat band voltage. Flat band voltage can be positive, negative या zero based upon choice of material. Basically flat band voltage depends upon phi m minus phi s. So if metal work function is less than semiconductor work function, then VFB would be less than 0, negative. If metal work function is greater than semiconductor work function, then it would be positive. If both are same, then it would be 0. So flat band voltage can be anything, positive, negative, 0, कुछ भी हो सकता है. It depends upon our choice, right? Usually the material which we are taking, let us suppose aluminum is taken as gate metal and we are taking silicon as semiconductor substrate. So in that case phi m is less than phi s and phi ms comes negative. So I am taking flat band voltage negative, right? बाकी ये कहीं भी हो सकता है. आइडियल सेमीकंडक्टर है तो BFB की वैल्यू, आइडियल मास कैपेसिटर है तो BFB की वैल्यू 0 होगी. Then we will have this threshold voltage, VTH. Usually the threshold voltage for mass capacitor fabricated on p-type substrate is positive because we are wanting to create inversion layer by applying the gate voltage. So if we apply positive gate voltage, then it will attract the electrons. Electrons are minority carriers and they will create the inversion layer. Although this value will also depend upon choice of material. So if you use polycrystalline silicon, then even on p-type substrate it may become negative. So that also again depend upon phi m minus phi s because VTH is also the function of BFB and BFB if you depend upon material then. But usually the characteristic is like this. So normally if nothing is mentioned, you will assume that the mass capacitor is fabricated on p-type substrate and metal we are using as a gate. So if you are using metal as gate, then VTH would be positive, right? It is threshold voltage. Now we have 3 segments. In the first segment, our gate voltage is varied from minus infinity to flat band voltage. In that case, capacitance is constant. It does not vary with the voltage. And this constant value is equal to oxide capacitance, C ox. This region of operation is known as accumulation mode. It is known as accumulation mode. accumulation की स्पेलिंग भाई बताओ, अंग्रेजी बहुत कमजोर है और भूख लगने के बाद और कमजोर हो जाती है. AC क्या होगा? accumulation, ACUMU, LATION, accumulation mode, right? Okay, now you see Once you go beyond this point, then capacitance starts decreasing because depletion layer is formed and depletion capacitance comes into the picture. This region of operation from BFB to BTH, it is known as depletion mode. Here the capacitor is operating in depletion mode. Right. And then if you go beyond this point, then inversion starts to take place. So beyond this point we have inversion mode. इस point के बाद पूरा ये inversion mode. Right. So if I go beyond this point, the capacitor, but capacitor does not allow sudden change of voltage. If it is ideal, then suddenly the voltage will change, but capacitor does not allow sudden change. We know from basic concepts, so it will gradually change and it goes like this, constant. So up to this point, when it is not becoming constant. Again, you see, my dear friend, when it goes into the strong inversion, then this value is equal to Cox, right? Up to this point, it is in weak inversion. This region is weak inversion mode. Weak inversion mode. And beyond this point, we have strong inversion mode. Strong inversion mode. This characteristic is at low frequency. ठीक? So this we have drawn at low frequency. यहाँ लिख लीजिएगा at low frequency. It is low frequency characteristic at low frequency. अभी high frequency के लिए भी बात करेंगे. Don't worry. The maximum capacitance on this graph which we can get, this is equal to C oxide, and the minimum capacitance we get here, this is C minimum. The minimum capacitance we are getting at threshold voltage, and you see, my dear friends, at threshold voltage XD is nothing but XD maximum. मैंने आपको बताया था कि threshold voltage पर maximum depletion width होगी, उससे ज़्यादा depletion width बढ़ा नहीं सकते. So you get XD is equal to XD maximum. If XD is maximum, then depletion capacitance would be minimum, right? So I can do few things here for your favor. Accumulation mode में, accumulation, अब शायद स्पेलिंग सही है. Accumulation mode, वहाँ स्पेलिंग गलत है accumulation की, सही कर लेना, क्योंकि ये स्पॉन्टेनियसली आई है तो सही है. एक्युमुलेशन ACC होना चाहिए. ठीक है, बाय डिफॉल्ट जो चीज़ें आ जाएं वो सही होती हैं. अब देख लेना यार. In accumulation mode, equivalent capacitance offered by the device is equal to Cox, and that is epsilon ox upon Tox. आपसे कभी भी वीक इन्वर्जन में नहीं पूछा जाएगा, स्ट्रॉन्ग इन्वर्जन में ही यूजुअली पूछा जाएगा. सो इन्वर्जन मोड में भी आपके पास जो कैपेसिटेंस होगा वो यही होगा. इन्वर्जन मोड में भी C इक्विवेलेंस इज इक्वल टू C ऑक्साइड इज इक्वल टू एप्सिलॉन ऑक्स अपॉन T ऑक्स. असली खेल है डिप्लीशन मोड में. सो डिप्लीशन मोड में कैपेसिटेंस, equivalent capacitance. Now we will have two capacitance. 1 upon C equivalent is equal to 1 upon C oxide plus 1 upon C depletion. Or you can say that C equivalent is equal to C oxide into C depletion divided by C oxide plus C depletion. This is the equivalent capacitance in depletion mode. Right? What is C depletion? Depletion capacitance is due to the depletion layer formed. So from junction, PN junction theory, we know that C depletion is XD, right? And C ox हमने पीछे लिखा ही था एप्सिलॉन ऑक्स अपॉन टी ऑक्स, ये इंटायर डिस्कशन में चलता रहेगा, ठीक। दिस इज एक्सटी। नाउ वी वांट टू मिनिमम कैपेसिटेंस। सो इक्विवेलेंट मिनिमम कैपेसिटेंस कब मिलेगा? जब XD, देखो सी ऑक्स तो चेंज नहीं होगा, सी डिप्लीशन चेंज होगा। तो जब सी डिप्लीशन मिनिमम होगा तो इक्विवेलेंट कैपेसिटेंस भी मिनिमम होगा। सी डिप्लीशन मिनिमम कब होगा? जब XD मैक्सिमम होगा। सो सी डिप्लीशन मिनिमम इज इक्वल टू एप्सिलॉन S XD मैक्सिमम, राइट। XD मैक्सिमम किस पर हो रहा? थ्रेशोल्ड वोल्टेज पर। सो आई कैन राइट कि सी मिनिमम, जो मिनिमम इक्विवेलेंट कैपेसिटेंस हमें मिलेगा वो होगा सी ऑक्साइड इंटू सी डिप्लीशन मिनिमम डिवाइडेड बाई सी ऑक्साइड प्लस सी डिप्लीशन मिनिमम। आपसे कई बार गेट में कुछ ऐसे क्वेश्चन पूछा है कि व्हाट इज द रेशियो ऑफ मैक्सिमम कैपेसिटेंस एंड मिनिमम कैपेसिटेंस। सो मैक्सिमम इज सी ऑक्स इज एप्सिलॉन ऑक्स अपॉन टी ऑक्स, मिनिमम इज दिस सी ऑक्स बाई सी मिन। आप कर लीजिए एंड सॉल्व कर लीजिए, यू विल गेट द डिजायर्ड। दिस ऑल इज वैलिड फॉर लो फ्रीक्वेंसी, राइट। आइए यू प्लीज डू इट। पहले इसका स्क्रीनशॉट ले लीजिए, ठीक। एंड देन उसके बाद yes, you will have series capacitance. Done? Good. Do this also. This. अब HF हाई फ्रीक्वेंसी कैरेक्टरिस्टिक्स क्या होंगे? HF कैरेक्टरिस्टिक्स यानी CVG कैरेक्टरिस्टिक्स ही हाई फ्रीक्वेंसी पर आप देखना चाहिए। कुछ नहीं, सेम ग्राफ में थोड़ा सा चेंज आ जाएगा बस, रेस्ट ऑफ द थिंग्स विल रिमेन सेम। दिस इज BG, दिस इज C, ठीक। दिस इज योर फ्लैट बैंड वोल्टेज BFB एंड दिस इज योर थ्रेशोल्ड वोल्टेज VTH, ठीक। So what happens up to this point? You have constant, no change in accumulation mode, C aux remains same, right? So this is your accumulation mode. Then in depletion mode it goes like this. बट इन्वर्जन मोड में ये कैपेसिटेंस पिंड अप हो जाता है। अब थ्योरी उसके लिए क्लास में बहुत कुछ डिस्कस किया है, सो आई एम नॉट गोइंग टू डिस्कस। सो इट डज नॉट इंक्रीज, रादर इट बिकम्स पिंड अप एट दिस पॉइंट, राइट। सो दिस इज योर इन्वर्जन मोड, दिस इज डिप्लीशन मोड। सो यहाँ स्ट्रांग और वीक इन्वर्जन का कॉन्सेप्ट ही नहीं आता है, ये पूरा इन्वर्जन है। और इन्वर्जन में जो कैपेसिटेंस मिलेगा वो मिनिमम कैपेसिटेंस जो डिप्लीशन का है उसी के बराबर रहेगा। सो दिस इज योर C मिनिमम एंड दिस इज योर C मैक्सिमम, राइट। दिस हैपेंस एट हाई फ्रीक्वेंसी, सो इट इज HF कैरेक्टरिस्टिक। दोनों से क्वेश्चन पूछे जाते हैं। 3 बज गया लगभग, 6 घंटे से क्लास चल रही है, अब नहीं पढ़ाऊंगा, हो गया। वैसे मैंने आप कहोगे कि आपने कहा था सारा कराएंगे, हाँ कौन सा मैं सत्यवादी हरिश्चंद्र हूँ कि जो बोल दिया वो करेंगे ही, ठीक है, ऐसा तो है नहीं। सो जितना हो सकता था कर लिया। अब लग गई है मुझे भूख बहुत ज़्यादा, ठीक है। सो मेरे दिमाग में अब रैंडमनेस आ रही है। सो आई एम नॉट गेटिंग एनी डायरेक्शनल थॉट। सो इसके आगे अब कुछ नहीं होने वाला है, आज के लिए बस इतना है। और क्या फ्री में बच्चे की जान लोगे, ठीक है। Now if you want to study anything, then you can see the entire lectures. बहुत सारे चीज़ें हैं, 100 घंटे की सब्जेक्ट है, कितना जल्दी रिवाइज किया जाए. So I am stopping here. ठीक, jokes apart. Last 10 days में क्या किया जाए? What should be done in last 10 days? Right. सर वन स्मॉल रिक्वेस्ट है, आप बाद में बेंडिंग बता दीजिएगा गेट से पहले. ओ माय गॉड, ऑप्टो में क्या होता है? ऑप्टो में सोलर सेल होता है. ठीक है, अब रहने दो, अब मत पूछो क्या क्या होता है. ठीक है, बहुत कुछ होता है. करें सर, आप बाद में बता दीजिएगा बेंडिंग गेट से पहले. मैं प्रॉमिस नहीं करूंगा, लेट्स सी है. अदरवाइज आप मुझे टेलीग्राम वगैरह पे मैसेज करिएगा, कोई क्वेश्चन होगा तो आई विल ट्राई टू एक्सप्लेन. हाँ, खैर आइए. पानी पी ले, फिर एक दो बातें आपसे कर ले और चलते हैं. इंपॉर्टेंट क्या है सर, पूछ रहा हूं. अरे सब कुछ इंपॉर्टेंट है, ये सब फर्जी चक्कर में मत पड़िए. PYQ करिए, प्रीवियस ईयर क्वेश्चन बैंक. जिन जिन टॉपिक से क्वेश्चन पूछे जा रहे हैं वही इंपॉर्टेंट है. ठीक है, और उन्हीं को ठीक से करिए, अच्छे से करिए. फ्रेंड्स, यू हैव टू कीप वन इंपॉर्टेंट थिंग इन माइंड. नाउ रफली 10 days are left, 10-11 days are left for the examination. So you need not to study anything new. Whatever you have studied till now, that is sufficient. Now just keep on revising. लगातार रिवाइज करते रहिए. Also make formula list, make short notes, and keep on revisiting those formulas which you usually forget. Stay motivated. Try to avoid any kind of negativity at this last moment. Appear in mock test. Even if your score is low, don't get demotivated. Try to figure out what are the reasons of low score. There can be some silly mistakes, there can be some conceptual errors, and try to overcome those silly mistakes or conceptual errors. Rather than कि आप इस चीज पर अपना जजमेंट करें, अपना एनालिसिस करें कि आपके नंबर कितने आ रहे हैं, उससे बेहतर है कि आप मॉक टेस्ट में ये देखें कि आपकी रिलेटिव रैंक क्या है. Because if test is difficult, it is difficult for everyone. If it is easy, it is easy for everyone, right? In last 10 दिनों में जो important advice मेरी तरफ से रहेगी वो यही रहेगी कि कुछ भी नया ना पढ़ें. Nothing new you need not to study. कुछ भी नया ना पढ़ें, जो पढ़ चुके हैं उसे ही रिवाइज करते रहें. Be confident. पूरे साल भर आपने मेहनत की है तो आपने इतनी मेहनत जरूर कर ली है कि आप अच्छा स्कोर कर सकते हैं. ठीक, अगर पूरे साल भर नहीं पढ़ा है तो फिर अब लास्ट के 10 दिन में परेशान होकर के भी कुछ बहुत बड़ा नहीं हो सकता है. फिर भी कूल एंड कंपोज्ड रहिए. जितना कुछ आपने पढ़ा है उसके बल पर आप जितना करेंगे वो अच्छा ही होगा. ठीक, ऑन द डे ऑफ एग्जामिनेशन डोंट गेट पैनिक. डे बिफोर एग्जामिनेशन ट्राई टू स्लीप प्रॉपरली. हालांकि मुश्किल होता है, नींद नहीं आती है. ठीक है, एक दिन पहले एग्जाम से नींद नहीं आती है, कोई बात नहीं, इट्स नेचुरल प्रोसेस. अगर नहीं भी आ रही, कोशिश करिए कि नींद आ जाए. अगर नहीं आ रही है तो अगले दिन एग्जाम में इस बात को बहुत ज्यादा प्रेशर में लेकर के नहीं रहना कि अरे मैं सोया नहीं हूं, एग्जाम खराब जाएगा. नहीं खराब होगा. वो एग्जाम से एक दिन पहले सबके साथ ऐसा होता है, यूजुअली ज्यादातर लोगों के साथ होता है. तो आपको भी नींद नहीं आ रही है तो बिल्कुल परेशान मत होइए, कुछ नहीं खराब होने वाला है. खराब तब होगा जब आप इस बात का प्रेशर ले लेंगे. ठीक, तो प्रेशर नहीं लेना है कि सोए नहीं है तो क्या होगा, लौट करके सो लीजिएगा. ठीक, समय से एग्जाम सेंटर पर पहुंचने की कोशिश करिए. समय से पहले काफी कोशिश करिए कि 1 घंटे पहले या आधा घंटे पहले, 1 घंटे पहले पहुंचने की कोशिश करिए ताकि लास्ट मोमेंट पर कुछ हड़बड़ी ना हो, अननेसेसरी पैनिक क्रिएट ना हो. ठीक, जो कुछ भी इंस्ट्रक्शन है गेट के स्कोर कार्ड पर, उन इंस्ट्रक्शंस को केयरफुली रीड करिए और उसके हिसाब से जो जो भी चीजें रिक्वायर्ड है वो लेकर के जाइए. ठीक, सेंटर पहले से लोकेट कर लीजिए कहां पर है. ठीक, एंड जब आप एग्जामिनेशन हॉल में हैं तो जब पहली बार क्वेश्चन कर रहे हैं तो किसी भी क्वेश्चन में अगर आपको 2 से 3 मिनट से ज्यादा लग रहा है तो उसे मार्क करिए और बाद में करिएगा, ठीक है। पहले अटेम्प्ट में, पहले 2 घंटे में आप वो सारे क्वेश्चन कर लीजिए जो 2 से 3 मिनट में आपसे बन जा रहे हैं, एंड लास्ट 1 आवर में उन क्वेश्चंस पर आप ट्राई करिए जो लेंदी हैं, जो डिफिकल्ट हैं, ठीक है। उनमें से जितने निकाल पाइए उतने निकालिएगा। क्वेश्चन सिलेक्शन बहुत इंपॉर्टेंट, वैसे तो 65 के 65 आपको करने हैं, लेकिन अगर आप सारा नहीं भी कर पा रहे हैं तो किसी ऐसे क्वेश्चन में मत भिड़ जाइएगा जो 15-20 मिनट का समय खा जाए और उसके बदले आप वो क्वेश्चन भी ना कर पाए और बाकी के भी आपके तमाम सारे क्वेश्चन गलत हो जाएं, या टाइम ना मिले, या हड़बड़ी में गड़बड़ हो जाए। तो ऐसा कोई क्वेश्चन चूज ना करें। क्वेश्चन देख करके पहले एक माइंड मैपिंग करें कि ये जल्दी बन जाएगा या नहीं बन जाएगा। अगर आपको लगता है कि नहीं ये स्टेप करके और ये सॉल्व हो जाएगा, गो फॉर इट। अगर आपको लगता है कि नहीं ये लेंदी होगा तो अभी उसे होल्ड करिए, बाद में समय बचे तो करिए, अदरवाइज छोड़ दीजिए, ठीक है। बी कॉन्फिडेंट, बिलीव इन योर कैपेबिलिटीज, यू आर गोइंग टू परफॉर्म वेल। आपने पूरे साल बहुत मेहनत की है तो ऐसा हो ही नहीं सकता है कि आप कुछ गड़बड़ करें। अननेसेसरी प्रेशर नहीं लेंगे अगर, तो आप अच्छा ही करेंगे, ठीक है। तो इसलिए एग्जाम इज ऑल अबाउट प्रेशर मैनेजमेंट। सो यदि आपने प्रेशर मैनेजमेंट अच्छा कर लिया, उन 3 घंटों में अपना बेस्ट परफॉर्म कर दिया, तो पूरे साल भर आप अच्छा पढ़े हुए हैं, डेफिनेटली आप अच्छा करने वाले हैं एग्जाम में। बेस्ट विशेस फ्रॉम माय साइड, good luck to everyone. I will pray to the Almighty that you get success in this examination, and I will pray कि आपने जितनी मेहनत की है उसके हिसाब से आपको बेहतर रिजल्ट मिले, बेस्ट रिजल्ट मिले। So best of luck to everybody, and thank you very much. Have a wonderful time and have a wonderful day on the examination day. Thank you. ठीक है जी।